Hello everyone, welcome to this DSA full course by Intellipaat. According to a recent Hacker Earth survey, over 70% of recruiters say that problem solving and algorithmic thinking are the top skills they look for in candidates. That's exactly what this course will help you build. But first, let's address a common question that most learners have. Why DSA and why Java for learning it? Well, data structures and algorithms form the backbone of computer science. They're the key to writing efficient, optimized, and scalable code. Whether you're cracking interviews at top product companies or writing back-end logic for real-world applications, a strong grip on DSA is a must. And when it comes to Java, it's one of the most widely used programming languages across the globe. According to Oracle, over 9 million developers use it. Moreover, tech giants like Google, Netflix, and Amazon rely on Java for its speed and clean syntax. By the end of this video, you won't just understand the concepts, you'll think in terms of DSA, break down problems like a pro, and solve them using Java in the most optimized way. So make sure to stick around till the end because this course is going to level up your coding journey in the most practical and job focused way. Now let me walk you through the agenda for this course. We'll begin by getting started with the introduction to data structures, followed by time and space complexity along with asymptotic analysis. From there, we'll move on to linear data structures where we will cover arrays, array list, and linked list with hands-on practice. Next, we'll explore stacks and queues and then dive into trees where we'll implement binary trees and cover traversal techniques like in-order, pre-order, and post-order. After that, we'll jump into graphs where we will focus on both directed and undirected graphs and implement DFS and BFS in Java. We'll then cover heaps and priority queues and finally wrap up with core algorithms including search algorithms like linear and binary search along with an introduction to greedy algorithms. Now that we are done with the agenda, let's get started with the very first topic on our list.
We are going to start with two topics, introduction to data structures and very preliminary data structures called array and linked list. Okay, so we will cover a very basic introduction to data structure and array and linked list data structure. So first question that comes in mind is what is data structure? Okay, so let us take a small example. There will be other examples also. Let us say I give you a set of numbers. This is a small toy example, but take it with simplicity because this is everything. I mean, there are more complex examples can be designed. So let us say the example is like this. We have a set of numbers from 1 to 100, but 1 to 100 means not exactly which numbers are given. I don't know. Okay. So I'm given, so let's say 10 numbers in the range 1 to 100, but what are those numbers exactly? I have no knowledge. Okay. Now I have to store those 10 numbers in such a way that I can solve some problem in a very efficient manner or in a quick manner. So what do you mean by efficient? We'll discuss later. So then I need to store those 10 numbers, okay, in a specific way. Let's say the job is to find the maximum value of those 10 numbers, okay. Then I would like to store those numbers in a specific way so that while answering the query, I can answer it as fast as possible. Okay, so that is my target. So what is the main thing to solve different problems using computer? I may oftentimes need to store the data or the input in a certain way. The input, the user may give input in a very mundane way, in a very straight way. But whoever is writing the program to solve a particular problem, he may need a specific organization of the data so as to give the answer in a very efficient manner. Okay, so that is the purpose of data structure. Let us move ahead. So what is a data structure? As I said in a very introductory manner, that data structure is essentially an efficient way of storing the data. Okay, so if we think of the definition, we can see that that a data structure is a way of organizing and storing data in a computer so that it can be efficiently accessed and manipulated. See, if I just say that I can store and data in an organized manner, that alone is not a data structure. Okay. So that means a data structure means I must have a data and certain operations, okay, that should be performed on the data. So that's the last part of this sentence, which says that it must be efficiently accessible and manipulated. Okay. For example, I mean, even before going into the depth, I can give you a small example. Let's say I have 10 integers. Okay. So these 10 integers, any 10 integers, let's say within one up to from 1 to 100 or say 1 to 1000, take any 10 integers. Now you can store these 10 integers in numerous different ways. Okay. Which way is suitable for you or you will do depends on the choice of application. Okay. What kind of problem you are going to solve. Okay. For that, you will specifically require that data structure because you will need certain operations to facilitate your application. Okay. So that's why always remember when somebody talks of a data structure, the data structure means storing of data in a certain manner, but just storage is not the important thing. Must have certain operations. Okay. That we should be able to perform on that data structure. So a data structure or storage without an operation is not at all usable. Okay. So what is the importance of data structure? As we see that it provides a systematic approach to manage and organize data. This manage means that operation part coming. Okay, to manage and organize the data, making it easier to perform various operations like insertion, deletion, searching, and sorting. Of course, here specific operation names are given like insertion, deletion, searching, sorting. But there may be other operations as well. Okay, not in every data structure we will have searching, sorting. But of course, in some commonly used data structure, we will have this kind of operations. But there are much more complicated data structures where the operations are none of these four. They are totally different. Okay. But there will be operations. For example, if you take integer values, okay. So integer is a data structure, very basic data structure. And what are the basic operations we perform over integers? The addition, subtraction, multiplication, division, or modulo. Okay, various kinds of very simple operations. Now, data structures serve as building blocks for designing algorithms and solving complex computational problems efficiently. Okay, so this we must remember uh, that data structure without data structure also we may be able to solve problem. Okay, there is no doubt, but it may not be as efficient as we'll be able to solve using a particular arrangement of the data or the data structure. For example, suppose in an office you have files, you store the files in a certain way so that later whenever applications come, you can pick up the files properly. Okay, so that your next set of operations becomes easy. Okay, so it is just like that. So, so what are the different types of data structures? Okay, so there are many different types of data structures. As I said, integer, float, these are very specific and very basic type of data structures. But we have more involved and more higher level of data structures, which are oftentimes used very frequently in computer programming. So number one is array. Okay, array is a sequence of elements. We'll see later. So array is the name of the data structure. So when we learn what is an array, we will see what kind of operations we allow on an array. Then the second one can be linked list. So it is similar to an array, but there are great differences. Okay, and if it is similar to array, then why we need such a data structure? Okay, that will explain. Okay, so linked list is a slightly different. It has some similarity to array, but it is also vastly different than array, and it has its own advantages and disadvantages also. So linked list is another very famous data structure. There is another data structure called stack. Okay, and so queue is also there. Trees and graphs, they are totally different kinds of data structures. And there are heap data structure, and hash table is also another special kind of data structure. So these 8 names are there. In addition to these 8 names, there are many other much more complicated data structure. Just to name a few, there is something called uh, binary tree. Okay, different kinds of uh, trees, like binary tree, binary search tree, okay, B tree. There are 2-3 tree. So various different kinds of data structures are possible. Okay, so we may not go into all of them, but these are just a few names you should remember. Okay, so with that, this big O notation is coming. So let us spend a few minutes with this big O notation. So this will help us to understand the calculating or measuring the efficiency of a data structure with its operations. So when I say big O, uh, big O symbolically is represented as a big O sign and then with certain inputs. Okay, so big O notation is a mathematical symbol, okay, used to describe the upper bound or worst case time complexity of an algorithm in terms of the input size. Okay, so this we must understand. So what do I mean by the upper bound? Upper bound or worst case. So that means, so suppose you ask me to sort a set of numbers, okay, in a particular order, let's say increasing order. Then if you give me 100 numbers, then I may require some amount of time, which is dependent on 100. Okay. If you give me 1000 numbers, then of course I will require some amount of time, which is a function of that 1000, not 100. Okay. Similarly, if you give me 1 lakh numbers, it will be a function of that 1 lakh. So the time requirement depends on the different sizes of inputs that is provided to me. Okay, so one question is how the time requirement, which is time requirement is one usual parameter of measuring the efficiency. So how the time varies with respect to input. So let me just draw a picture here just for a better understanding. Yeah. So if I see this 10, say 20, 30, in this way, I go to 100, okay, like this. So if my time requirement is like this, Fn, so that means at 10, the value goes here. At 20, the value goes here. At 30, the value goes here. At 100, the value goes here. So if this is my Fn, so this is the value of Fn. Okay, what is the value of Fn? This is the dotted point where it touches the y-axis. So x-axis is essentially n and y-axis is Fn. So then I will say that the time, which is a function of n, is actually big O of Fn, okay, if actually Tn is less or equal to some constant into Fn when where n is greater than some n0 and c is some constant. So that means for all n greater than some number, the Tn value takes a value which is less or equal to c times Fn. Okay, c is a constant time Fn. In that, if that be so, then I mathematically write Tn is equal to O big O of Fn. Okay. Similarly, the curve may be actually for a, so this may be for one particular case or one particular application or one particular problem. Let's say with respect to input, the Fn, which is essentially the Tn, okay, the Tn varies like this. So for another application, the variation of the Tn or Fn may be totally different. It may be like this. It may be like this. So in that case, I say n, here this is Tn, and I may find that Tn is actually of the order of, let's say, n log n. Okay? So so in how to make a comparison, so how the n log n looks like. So if it is n log n, this curve is an n log n curve, then that means the product of n and log n. So where is n then? N is slightly lower than this, slightly lower. N log n is slightly higher than n. And what is log n? Log n is actually even lower than n. So this is n, this is log n. Log n curve is like that. Actually, it's not a straight line. Log n curve is slightly different. It should be, it is very slowly growing. Maybe it is like this. Now, square root of n is again something between n and log n. This kind of thing. This is square root of n. Okay. So for different values of n, my functional dependency may be different. So we should also not feel that, okay, is there any function between root n and log n? Of course there is. Okay. By properly setting the function, one can find out. Let's say root n is essentially n to the power of 0.5. So if I say something like n to the power of 0.4, then that, or 0.3, so that will be something like this. Something between, something below root n, something like that. So I hope you can understand the relationship between the input size, which is n, and the time required to complete the job, that is the Tn. So Tn is dependent on n, okay? And worst case dependency is represented by this relationship Tn is big O of Fn. That means for all n values greater than some specific n0, the Tn is actually upper bounded by C times constant time Fn. Okay, so that is the mathematical notation that we generally use to define big O. Okay. So now, with respect to big O notation, there are some specific notations. So when I say big O of 1, okay, I write big O of 1. What does it mean? It means it requires some constant amount of time. That means it doesn't have any dependence on the input size. Okay, for example, suppose I give you a sequence of elements, okay, let's say 10 elements, and my job is find the first element from the sequence. So for that, it is independent of the input size. If you give me 10 elements, then the time that I will spend to get the first element is the same time that I will spend if you give me 1000 elements or 1 lakh elements or many more. Okay, so that means the time requirement for the job is independent of the input size, or it's a constant, it's a fixed quantity. So that kind of requirement we represent by this big O of 1, that is constant time notation. Okay. For example, the example given here actually prints the zeroth, the first element of an array. Okay, so that's independent of the array size. That is the idea. Okay, so similarly, if I say big O of log n, okay, so that means that it has some dependence on the input size, and the dependence is actually logarithmic. That means if the input size is say 100, then the time will be logarithm of 100. That means roughly, if you take logarithm base 10, then it is roughly 10. Okay, 10 to the power of 2 is 100, so it should be 2, just 2 steps. If it is logarithm base 2, then it should be roughly 7. Okay, some 7 steps. Okay, 6 or 7 steps. So that is some kind of idea. And so if you ask, okay, what can you give me an application where I really need order of logarithm number of steps to solve some problem? Yes, this is given in the particular problem called binary search. Okay, so what is the binary search problem? Let me go a little bit on the binary search problem. So let us say I have a sequence of numbers. Okay? Binary search. So I have a sequence of numbers. Okay, let's say 1, 5, 2, then 3, then 7. Okay, and in this sequence, so there may be a larger sequence also, but in this sequence, suppose the job is to say whether the number 3 is there in this sequence. This is the question: is the number 3 there in the sequence? Is number 8 in the sequence, or is number 8 is there in this sequence? Okay, so one normal approach for this is, okay, you have the sequence and this is stored in an array, so you just compare the question value. So this is called the key value that you are interested to search. Okay, so what you do, you compare your key value with the first element, and if they match, then you say yes, it is there. If it is not, then you just keep on moving further. So you move to the next element, which is 5. So you try to check whether it is the key value. So if it is yes, then you say yes, it is there. If it is no, then you just move ahead until you reach the end of the sequence. So in this way, you can understand the 3 is there or not. So I need to move, I need to check and compare with the first 3 elements, and all of them are failures. And at the fourth element, I will make a success, and I will discuss, I will announce that yes, 3 is there in the sequence, and I will say that is a positive output. Then again, if I look at the second question, that is 8 there in the sequence. So if you see that I will compare with all the elements, all the 5 elements in this sequence, and at the end of 5 comparisons only, I will declare a negative result that it is not present in the sequence. So that means in the case of success, I may have to consider or compare with all the elements in the worst case. Suppose the um, question is 7 in this sequence? Then probably if I do one by one, left to right, searching and comparing, then I may have to compare it with this, all the elements. Okay. And if it is an unsuccessful search, I mean, if the element is not there in this list, remember why? Because I have a very big list, and when somebody is giving me the key, I really haven't seen these elements, what are given in this list. Okay, so the list is to some extent unknown to me. Okay, and only the key is given. So I really need to compare with everyone, potentially everyone, to solve this problem. So this is called binary search. This is not binary search. This is some kind of search which one by one. So I go from 1 to 5, then so this is in a linear manner. I move from left to right. Okay, so this is called linear search, and it requires a time which is proportional to the number of inputs. So we write it is order of n. So it is proportional to the input size. So if you have say 1000 elements and you have to search a particular key, so you will spend a time which is proportional to n, that is proportional to 1000. Okay. Similarly, if you give me 1 lakh elements, if I design a procedure like this, I will search one by one, and at the end only, I may in the worst case have to go till the end to declare irrespective of whether it's a positive or negative result. So that is one way of doing things. Now there is a better way of doing this. Okay? There is a better way of doing this. The better way is, if somebody gives me this sequence 1, 5, 2, 3, 7, if somebody gives me, instead of this random sequence, if somebody gives me a sorted sequence, sorted means a particular order, like increasing order or decreasing order. Okay. So somebody gives me a sorted sequence, suppose in the increasing order. And now I am asking whether the key element 3 is present in this sequence, or the key element 8 is present in this sequence. The same question I'm asking. Then I can, of course, apply the same earlier method of linear search to solve the problem. But I have a better approach. I can do it better. What is the idea? I divide this thing into almost 2 equal halves. Okay. So I have this, I define what is called something called mean. Okay, this is my mean. Okay, and I compare it with the mean. Okay, I compare the key that I have to search with the mid element. If it matches, then I'm sure that it is there in this array, and I just declare that it is found. But if it is not, if it is not matching with the mid element, then because this sequence is sorted in an increasing order, I know where this key element is going to exist. Okay, where, in which region this key element is probably I may found. So if the value of the key element is actually less than the mid value, then probably there is no point in searching to the right side of the mid element. Okay, I can just confine my search to the left side of the mid element. Okay, similarly, if the value of the key is greater than the mid element, then probably I can confine my search to the right side of the mid element. Okay, so that I can do, and this technique I can actually repeatedly apply. That means while doing the searching in the left half or the right half, I can again divide it into 2 almost equal parts, or I can again divide a second level of mean. Okay? I can divide a second level of mean. So this is the first level of mean. This is the second level of mean. And then my key, I need to probably search between mid 1 and mid 2, or right of mid 2. Okay, so it is like at every step I am reducing my search space. Okay, initially I need to search among n elements probably, and from that I reduce my search space to n by 2. And then in the second step, probably I am successful, I find the element, or I reduce my search space to even further, like n by 4. Okay. And in the next step, I reduce my search space to even further down, like n by 8. Right. So in this way, it goes on. And ultimately, after k steps, I can reduce my search space up to this n by 2 to the power of k. Okay. So when this quantity is roughly one element, okay, So in this case, I probably can do, comparison in a one-to-one manner. And in this case, I see that k is actually of the order of log n, basically log n base 2. Okay, so that is the way binary search works. So I hope this is roughly clear. So this is the kind of code that is written here. If you see the binary search, the array and the target is essentially the key. Okay, so I have left and right assigned to 0, and the length of the array uh, is len array -1. So the array actually ranges from 0 to len -1. So when left is less or equal to right, so I define a mid value that is left plus right by 2, and then if the mid value is essentially the target or the key that I'm looking for, then I'm just done. I have been successful. The element is there in the list. Otherwise, I just remodify my left to mid plus 1. Okay, or actually it should be right. Okay, my left index or right index. So if it is less than the target, if the mid value is less than the target, then what does it mean? That means the target is probably in the right side. Okay, so left is that the left, that is the index, is now mid plus 1. So after the mid, from that till the end of the array, I should search. Similarly, if the mid value of the array is essentially greater than the target, that means my target is essentially to the left of the mid value. So my right position, right point array, or right pointer, or right indicator index should be just to the left of the mid, and then I should just do the repetition of this procedure. Okay, so every step I am reducing the search space into half. Okay, so that's why the time complexity here becomes logarithmic. So similarly, I have linear search. As I told, linear search here I ranges from 1 to the length of the array. I will compare with every element whether the array index AI array I is equal to the target or the key. If it is matching, I just declare yes, I have found the element in the sequence, and I return the index, which index contains the element. Okay, and otherwise, if I search till the end of the array and I do not find any valid index which contains the element, I just return an invalid number -1, which indicates that my search is unsuccessful. Okay, so this requires a time which is proportional to the input size. So this is called ON, big O of n, or also known as linear time. Now, there is something called a log linear time. Log linear time. So n log n. So it's a product of n and log n. Okay? So where generally this kind of complexities happens, some kind of sorting algorithms. Okay, if you have heard sort, there are various sorting schemes we may see later in the course, that there are sorting algorithms like merge sort, quick sort, the special sorting algorithms, which are very famous, and they require n log n time complexity uh, on an average and as well as in the worst case. Okay. Now there may be other time complexities also, like n square. Okay. So that's called quadratic time. So you can see that there are some sorting algorithms which require quadratic time. For example, bubble sort, etc. See, we are familiarizing ourselves with the complexity, time complexity, how it varies with respect to input size, and we are studying very basic data structures. Why this is required? Because when we'll start manipulating, start learning some very basic data structure, we will require this kind of notations. Okay, so that's why we need to understand these very basics of big O notation. Okay, so as you can see that we can that we need to analyze algorithms efficiently and how the algorithm performs with respect to the input size. Okay, so regarding complexity, there are terms, there are ways of defining the complexities. One popular notion is the time complexity. Another popular notion is the space complexity, and both are measured in terms of the input size, which is n. Okay, so mostly we use the time complexity measure because that is more important. Sometimes we use the space complexity measures, but for most of the cases, the space complexity measure is ignored because space today in today's world, space is not a limitation. And also most of the problems, we don't require much space. So what is important, we how much time we require, how much fast we can solve a problem, that oftentimes is the main concern. Okay, so that's the issue. So one small example is given, that array traversal. So I want to suppose I'm given an array. So we have different data structure, as we told, that uh, array data structure and linked list data structure. So for array, suppose we are given a problem like I have I have an array, and I want to sum up the values of all the elements. Okay, so it requires big O of n time. Okay, and we say that the complexity of the problem is big O of n, or it's called linear time complexity. Okay, so why it is so? Because the algorithm iterates through each element of the array once, performing a constant time operation, that is the sum. Okay, as the number of elements increases, the time increases proportionally. Okay. Similarly, we have linked list data structure, as we'll see as soon as possible. So linked list data structure, uh, there may be some operation called searching of an element in the linked list. Okay. So I have a very big linked list of, let's say, n elements or 100 elements or maybe 1,000 elements, and I have to search an element in that linked list. So in the linked list, I don't have the luxury actually to use the concept of binary search. I have to use linear search kind of technique. So the complexity of searching will be big O of n in the worst case. Similarly, as I said, that if the binary search technique is used, and remember, binary search can be applicable only with some array. Okay, with linked list, we may not be able to do binary search. So with a sorted array, if I do binary search, the complexity will be order of log n. So we say logarithmic time complexity. Okay, for hash, there are other data structures. These are just for your information. Okay, the how, why it is so, probably requires more involved mathematical techniques we are not doing at this point, but just for informative information purpose, uh, hash table is another important, very important data structure we will see later. And hash table, as you can see, that searching an element in a sorted, searching an element using linear search requires uh, order n time. Searching an element in a sorted sequence or sorted array requires, I mean, order of log n time using binary search. A natural question comes, is it possible to do searching in constant amount of time? That means irrespective of the input size, can I do it in constant time? I mean, independent of the input size. Okay, so that is possible if I store it at a specific location. For example, I mean, suppose I want this how a courier service system, how they locate an address. Okay? in whole of a country or in the whole world, there are innumerable number of addresses. So how they find those addresses very quickly, where they need to route the data or packet. So they really do it very quickly. And that is because where the house is located, that is very much predetermined. Okay. So hash table lookup is just like that. If you initially store your data in a very organized manner, okay, in a very specific manner, so that from the data itself, you are able to get a get some intelligence that okay, for searching this item, I need to go only in those places. I do not need to randomly search some random places. Then probably the time complexity is independent of the input size. Okay. So you require constant amount of time, which is represented as big O of 1. And this is mostly in the average case. Okay. So it requires a well implementation of the hash table concept. Okay. We will see later. In the worst case, there may be it is slightly more, but most of the cases it becomes constant amount of searching effort. There are other complexities like square time, as I said, bubble sort, etc. We may require square time complexity. So this is a small piece of code written in Java language, public void print numbers n for I equal to 0 to n, 0 less than n I plus plus, system out print I plus. Okay, so this means it prints numbers from 1 to n, okay? 0 to n. Okay? So the first those sequence is print. Okay, so this is a linear complexity and space requirement is also 1. Okay, so what is space complexity we will study soon, but these are just some examples problems where we can analyze our time requirement as a function of the input. So there is some kind of problem for which we may apply brute force algorithm. Okay? So brute force algorithms are not very much practical, but they are very easy to design. Okay? So let's say I have a sequence of elements and I need to sort them. Okay? I need to sort them in increasing order. So what can be a brute force approach? The brute force approach is I have all the n numbers and I can permutate all the n numbers in using n factorial permutation. And I try with all the n factorial permutation. And in out of all the n factorial permutations, only in one permutation, every element, I'll see that every element is placed a little before its next element. Okay, that means an element is smaller than its next element in the sequence. So that permutation I take as at the sorted sequence, but it may take a large amount of time. So brute force algorithms are of not much interest. But what is important is that it is very easy to design, but it may not be efficient actually. Okay, so we need to just this is for your information that brute force algorithms are certain kinds of techniques we can design, and there the big O notation also captures the brute force complexity, but that may not be of desired value. So one example that is given here is the suppose I have an array, I need to find the maximum element in that array. Okay, so the same problem I can do it in using brute force manner, and I can do it in a little intelligent manner, and it may require different kind of approach. Okay, so there are different kinds of complexities uh, which we may see later. One is called the best case complexity. See, all these complexities are essentially dependent on the input size. So best case complexity, worst case complexity, and average case complexity. Best case complexity means that means when the input size may be large, but the input is actually favorable. Input is organized or given in a favorable manner. We may require some time that is minimum. Okay, so it is the minimum time complexity when the algorithm performs optimally. Okay, usually it represents the lower bound of the algorithm's efficiency. So best case is one case, but it may not always be the case because who is giving you the input? He may be an adversary. Okay, and the adversary may or may not give you the input in the best possible way. Okay, but when he gives it, suppose you have to sort a sequence. Okay, and the sequence is already sorted. So the sequence is already sorted. You do not know, but the adversary is fooling us to some extent and gives a already sorted array. Then, even then, in that case also, if your algorithm is so that it can solve the problem in a quick time, let's say linear time, or let's say better than square time, then we should say that your algorithm has a best case complexity. Now, worst case complexity is just the opposite. When your algorithm requires maximum amount of time, when the algorithm performs on a specific input, and it is least efficient. Okay. So, and it generally represents the upper bound on the algorithm's efficiency. And this is the mostly used term in the analysis of algorithms, the worst case complexity, because we generally don't have any idea of how the input is going to come. So somebody is asking to give us a sorting algorithm or sort a sequence of numbers. I have no idea how the numbers will be given. It may be sorted, it may be half sorted, it may be a random sequence. I don't have any idea. It may be just reverse sorted. Okay. So irrespective of the input size, if I can design an algorithm and I can say that it requires some amount of time, okay, irrespective of the way the input is given, whether the input is given in a favorable way or non-favorable way, I will no more require than that certain amount of time, then that is my worst case time complexity. And this is the mostly analyzed term in the algorithm analysis. And average case complexity is essentially something between best case and worst case. The average case is some average analysis, like it may vary between best case and worst case. So when we have more knowledge about the problem, we have more knowledge about how the input can be. So if I can utilize that, then probably I can do some average case analysis. And in many cases, the average case complexity is as bad as worst case, essentially. But sometimes it is good also. So that's why average case complexity is another important measure. But most of the time, worst case complexity is the measure that we deal with. And with respect to how we measure the operations, as I told, that time and space complexity. So time complexity means that how much time it is going to take. Time means how much basic operations. Okay, for each basic operation, I spend some time. Okay, so how many basic operations I need to do to solve a particular problem in terms of the input size. Okay. So for example, a single loop is there. I I may run a single loop n times. So I say that big O of n is the running time of the loop. I have multiple nested loops. Okay. So then I may require n into m times, where m is the outer loop or inner loops. Okay, if inner loop runs n times, outer loop runs n m times, then overall the two loops, overall they will run n into m, and vice versa. Okay? Constant time complexity means no loop. It is just a fixed amount of time that is represented by big O of 1. Okay, so these are various measures of time complexity. There can be other complexities also, like we said that order of log n, order of n log n, order of n square. There are often algorithms which are not presented here, which require order of n cube. Okay, there are algorithms or problems which require more than n cube. Let's say n to the power of 4, n to the power of 5. There are problems. So we should not feel that there are no problems which do not require n to the power of 5. There are, but probably they are more involved and complex problems. We may not discuss them here. But remember, as long as something is n to the power of constant, okay, constant may be as large as, let's say, 100 or something, n to the power of c is a constant. We say the algorithm is good, essentially. It's called a polynomial complexity. Okay. So similarly, we have the term space complexity. So space complexity means uh, how much additional space you require. Okay. So this is the definition of space complexity. See, any problem you want to solve, you require the input to be stored in a particular way. Okay, and if the input size is n, then you require at least order of n space to store the input data. But that is not the space complexity. It says how much, in addition to that input size, how much additional memory you need to solve the problem, and how much that additional memory requirement varies with respect to the input size. So if the input size is n, how the additional memory requirement varies? Is it proportional to n? Is it logarithm of n, or is it constant independent of n, or is it square of n, or is it some what it is? So on that depends on the space complexity. So if I say constant space complexity, that means the additional memory requirement is essentially independent of the input size of the algorithm. So it's some constant amount of additional memory that is required. So regardless of the input size, algorithm requires some constant amount of memory. Logarithmic space complexity means the additional memory requirement actually increases, but it increases in the logarithmic size of the input. Okay, here logarithmic space complexity is probably not there. It is called linear space complexity. Linear space complexity is there, so the additional memory is proportional to the input size. Okay, so we say logarithmic space complexity if the additional memory requirement is proportional to the logarithm of the input size. Similarly, we may have something called polynomial space complexity. Okay, it is often famously known as P space, okay, polynomial space complexity, which means the additional memory requirement is something big O of n to the power of k, where k is some constant. So that means anything like n or n square or n cube, all of them belong to this polynomial space complexity. There may be some rare cases where the space requirement is maybe exponential as compared to the input size, which is called exponential space complexity, which may not be of that interest to us. Okay, so and of course there can be space complexity of constant size. So with this, I think the very basics of data structures is introduced, and that concept of time and space complexity is introduced. So data structure, we should understand that it is a particular organization of data and a set of operations, and how the operations are done and how efficient the operations are. They are measured using these complexities, this big O notation and the time and space requirements. Okay, so I will try to explain the big O notation with a simple example once again. So let's do that. So let us take an example, then it will be better understood. Suppose I am given an array. Okay, this is an array. Okay, this array is often represented in a C language or Java language. It's like this: int array name is, let's say, store st store. Okay, then this number is 100. So I have all these elements here, although it may not. So it is the 0, it is the 1, it is the 2, 3, and etc up to 99. So we will write store 0 has some value, let's say a. Store b, store 1 has some value like b, and like that, and store 99 has some value, let's say x. In between there are values, some values. Okay, so this is the input. Okay, so now problem, what is the problem? The problem, let's say, find the max value present in the array. Find the maximum value present in the array. Let's say that is the problem or the question that I am asking. So I can write a small code like for I equal to 0. Let's say I initially say max equal to store 0. Okay, so I assume that the first element is the maximum. This is the max. Okay, so for that, of course, I have to define max somewhere. I have to define max somewhere that I assume that you know how to define, and then I write for I equal to 0, I less or equal to 100. Okay, of course I should be less than 100 because I can vary from 0 to 99, and I say I plus plus. Okay, I what I do is I write this. I say if store I, of course, because 0 is the max, so I can keep comparing from the next element. So I just compare from the 1. Okay? For 1 less than 100. So if store I is greater than max, if this is the case, then I will write max equal to store I. Then that is the element I set to max. Okay, so in this, what will happen? So I is initially set to 1 and max is initially store 0, first element. What I check, store 1 is greater than max. If it is so, then naturally store 1 is the new max. So I set the new max as the store 1, and then it again goes to the for loop. This I plus plus increases the value of I, so I becomes 2 now, and I again keep checking that store 2 is greater than the new max. That is the thing that is originally the last maximum values that is stored. If it is not, if it is same or if it is same or less, then there is no point in changing. Okay, if it is really the new max, then only there is a need for change the max. So what I do is I for 2, suppose it is depending on whether it is greater or less or equal to, I set the max accordingly, and then I just do it. I keep on doing it. So after doing this till the I reaches 99, so of course 99 is checked with the current max, and if it is more, it is set. If it is not, then it is not. Then I set to 100. As soon as it is 100, it the for loop actually cannot go. So it comes out of the for loop because now I is no more less than 100. I has reached 100. So now I can declare that the maximum value I know is now stored at this max. Okay. And what is the index? That index I do not know. So to know the index, I need to store the index actually. I can say here the target index equal to I. I can just define something called int max. Just like int max, I can define like int target index. Okay. So target index. So after coming out of it, I can write that, okay, printf. Okay, I can write %d. Okay, what is max value? Or I can also write target index. That means if I now search, I can, if I just return store target index, that will essentially give me the max. That is essentially the max. Okay. So if I have this code, then this solves this problem. Now, for this way of solving the problem, what is the time complexity? That is the question. Time complexity. How much time it is needed? Okay. So if you see that for I need to this max equal to store one, I need unit time. Okay. I need constant amount of time. So that is called big O of 1. Okay. Then for I equal to 1 to 100, okay. So I actually will require this for loop. That this for loop will run 100 times, roughly. Okay, 100 plus minus 1. So roughly 100 times. And inside this for loop, see, depending on this checking, this condition, some constant amount of time will be required. Whether if it is the constant, if this condition is valid, then these two operations will be done. Okay, so it is actually 2 times big O of 1, which is essentially big O of 1. So it is 2 times some constant is also a constant. So that's why it is a big O of 1 time. And otherwise, if this condition is invalid, then it just ignored, and the loop just goes back. Inside this loop, I will always require some big O of 1, some constant amount of time. So how much overall? And this part, again, I need constant amount of time, and this part, I need constant amount of time, printing and storing, etc. So overall, the major time requirement is by this loop. Okay. Or overall time requirement is sum of these individual action times. But the major contribution is the time required by this loop is essentially 100 times big O of 1. Okay. So now one can say this is constant, but this is not. See, because I have mentioned the array to be 100, okay, that's why I say 100 into big O of 1. But if the input size is a variable on n. Okay, input size is a variable on n. So that means it's a abstract thing. I can set n appropriately. Okay, so it's an abstract thing. Then what should be my time complexity? That time complexity now can be a function of the input size, that is n. So this for loop will run n times. So I will write n times big O of 1. So this thing I generally write with this big O of n. That means the time exactly will be less or equal to some constant into n. For n greater or equal to n0, some n0. N0 is here maybe probably 1, and c is some constant. Probably 1 here. Probably c is equal to also 1. Okay, so this is the explanation of time complexity. So if you think of this problem, what is the space you require? You need, the input is stored already in an array store, okay, which is proportional to the input size. But in addition to the store, you need additional variables like max, you need this target index, okay, and probably no other thing, okay. So using these additional variables, one or two extra additional variables, you can solve this problem. So additional space is you require, additional space memory required, within bracket I can write other than the input size is constant. Here it is actually two variables. So constant. So which I can also technically write big O of 1. Big O of 1 means constant. So the additional space requirement or memory requirement is independent of the input size. So if your input size n is 100, I will also need additional two variables. If your n is 1 lakh, I will also need the same two variables. That's why it is independent of the input size. Constant means it is independent of the input size. Okay. This big O is this symbol. This is big O. Okay. Big O is just a big O and then bracket 1. Or there are some notation like big O of n. There are notation like big O of n square. Okay. Now one can say big O of n log n also. Okay. So this is big O means the capital O symbol of the alphabet. Okay. That's why it's called big O. Now there are notations which are related, which are called small o notations. So this is the small o symbol of the alphabet. Okay, that has a different meaning. The meaning is slightly different. Let us not go into that at this point. Okay. Okay, it has some mathematical details, a slight difference between big O and this is called small o. Okay, there are other mathematical notations like this is called big omega, there is small omega notation, then there is called big theta notation. So all those notations are there, but these notations are mostly discussed in algorithm course, but this is not an algorithm course. So let us not uh, make ourselves involved in those things. Just one big O notation is good enough for most of the cases. Okay, what is log n and what is n log n? So as I explained in the binary search, okay, in the binary search problem, see, binary search is not a problem basically. The search is the problem. How I solve is the binary search technique. Okay, so there the idea is I have a sequence and the sequence must be sorted sequence, the sorted array. Remember, we must have a sorted array. Okay, sorted array A, let's say. Okay. So if the array is sorted, then only I can apply binary search. If the array is not sorted, then binary search at all will not be successful at all. Okay, it will not work. So what is the idea? Just believe in the idea. In this case, suppose the key is the element. I need to search in this array. And this array is sorted. So what I do, I have a notion of mid. Okay. So mid is essentially, mid is equal to, this is my left and this is my right. Okay, mid is essentially L plus R by 2. Okay, these are some mathematical symbols, ceiling. If you don't know, let it go. L plus R by 2. Then what I do, I compare the key with the array of mid. If it is mid, is if it is equal to mid or not. So that's why it is equal. I mean, maybe in the C language, I will use this if. Okay, then I just return this index mid, return the index mid, because mid is the particular point, okay, index point where the element key is stored. So that's good enough if I just return from this procedure. But if that is not the case, then there is only two possibilities. One is key is strictly greater than mid, a mid, that is the mid element, or key is strictly less than a mid. These are the two possibilities. There is no other possibility. So if key is greater than, so it is written like else if. Okay, if key is greater than a mid, that means key is somewhere here in this region. So if key is greater than a mid, then it is a futile or useless effort to search in this region. So if somebody wants to search the key in this region of the sorted array, then that's a useless search because it will not be there. This region contains only elements which are smaller than the a mid. So it is just useless to search it there. So what I do, I just confine my search. Okay, I just confine my search in this right side by doing proper setting of my left and right. So my new left is set to mid plus 1 and my right is same as right, and I just repeat this by calling my binary search procedure with this array A, left and right. With these three parameters, I just restart the searching procedure. Okay. On the other hand, if key is strictly less than made, that means key is in the left side. So then I do not need to modify the left. I just need to modify the right part, R index. So I just say R equal to mid minus 1. And then I just call this binary search with the new set of index, that is left and right. Okay. So this is roughly the code. Okay. But analyzing the time in case of binary search is slightly more involved. Okay. How people may say how log n is coming. So it is represented mathematically in terms of recurrence equation. So to do a search over a sequence of n element, I need to do one search. Actually, after comparing it with the mid value, that comparison is done in constant time. This big O is the comparison with mid. Comparison with mid. A mid, basically. Comparison with a mid. So for this, I require a constant amount of time. Okay, so that constant is represented by big O. And after doing the comparison, I either just do binary search in the right side or do the binary search in the left side again. But this height, left side or right side, the search space is roughly half of the original. I do not need to do it 2 times. I just need to do the searching only one segment of the half. 2 halves, only one segment. So that's why it is 1 into n by 2 plus this. This is the recurrence relation. This is the mathematical relation, recurrence equation. So you can search. It is called recurrence relation or function. Okay. Now there are techniques to solve this, and if somebody solves this, it amounts to like this. It can be shown that Tn is of the order of log n. So why of the order of log n? Because if you practically you take 100, okay, and this log is base 2 basically, okay? Log base 2. So if you have say 100 element, so you basically you can show that you don't need more than 6 to 8 steps. Why 6 to 8? 2 to the power of 6 is 64 and 2 to the power of 7 is 128. So 128 is slightly more than 100. So roughly you require 6 to 7 steps. You don't need any more than that. By 6 to 7 steps, you will be sure that whether the key is present in the sequence or it is not at all present in the array. You will be 100% sure. Okay. Similarly, there are problems like sorting problems. Okay. Sorting problems like merge sort. Okay. For merge sort, the complexity There is an algorithm which I am not telling now, but believe me, I can design for this, just like for binary search, I explain the time complexity in terms of a recurrence equation like this. For merge sort, I can also express my time complexity as an equation like this. Tn, now instead of 1 times the half size, I need to do 2 times the half size, 2 times Tn by 2, plus here I was doing big O of 1, there I will require big O of n. Okay. So basically, I need to merge two half sorted arrays. So let us say two half arrays, and each is individually sorted, and then I need to merge them using some procedure. So this is the merging time. This is the merging time, and this is the recursive sorting of half half arrays. Okay. So if this equation, if you solve this equation mathematically, then you can show that this roughly comes big O of n log n. Okay, big O of n log n. Okay, let me tell you the assignment in a graphical manner. So let's say I have an array. Okay, I have an array like this, array 100. So that means I have an array, 0 is the index to 99. Okay. So odd numbers, what are the odd numbers? So 0 is essentially, so anything with index, say index is I, so I can vary from 0 to 99. Okay, so I can say I plus 1 varies from 1 to 100. So now you know that my odd positions are 1, 3, 5, 7, 9, 11, blah, blah. And my even positions are 2, 4, 6, 8, 10, etc. Up to some maximum, not more than 99. Okay. So what you will do, you will just add up your all even positions in this array, and you will add up all odd positions, because see 0 to 99 is same as writing 1 to 100. Okay, just this is the way of storing. Okay, in the computer you cannot, in the C world you cannot, your index only ranges from 0 to 99 instead of, so you can think of 1 is mapped to 0, and you can do the mapping. So then you can add the values in the odd places, and you can add the values in the even places, and then let's say you get the value t1 is the sum at the odd places, t2 is the sum at the even places, and what you do, you take the absolute difference between the two, or you can say what is the max of these, max of t1 t2. Okay, or you can think of mean of t1 t2. So these are a couple of things you can think of. Then another couple of statistical parameters that you can think of. It is called average. Average of all the values you can calculate. Okay. You can calculate sum of all the values. You can calculate SD, standard deviation of all the values. What is the standard deviation? So to calculate the standard deviation, you probably need the average. Okay. So once you have the standard deviation, you can calculate something called variance. Okay, so these are statistical parameters related to the different values that you can calculate. Okay, so you can practice one by one. Okay.
Okay, we will do quick revision of arrays. What is an array? What are the, you can say, disadvantages of array? How we can overcome that? Some questions on array. Okay, and then we will move to linked list. Okay, what is a linked list? How many types of linked list? Okay, there is not just one type of linked list. There are many types of linked list. So we'll be learning that. For the implementation, we will be using only single linked list. I will tell you all everything about these things. Okay, we create a new project and let's name it as today's date, that is 29th October. DSA batch. Okay, I think that is it. We have our project ready over here. Let's create a package where we will be having our classes. Okay, let's call it as test. Under here, we'll be having a class. Let's call it as learning arrays. Okay, so we have our class named as learning arrays. We have our main. Now, what is the difference between a data type? So this is a data structure class, right? What is the difference between a data type and a data structure? Data type is like, what is a type of data? Integer data or string data or character data. Okay, characteristic about the data. What is the characteristic about data? Data structure is a way of storing data. Way of storing data so that we can easily retrieve it. We can do some manipulations on the data. Okay, and there are many data structures available. So data structure is nothing but how you store all those data together, so you can easily retrieve it, easily manipulate it in your computer. That is the simple definition. Okay, now let's talk about arrays. Let's talk about arrays. What is an array? What is an array? Array is a continuous data together. Okay, like this. Contagious. These are contagious blocks in your memory. What is the meaning of contagious blocks? Meaning they all are put together. This is how your array looks like, right? You have, let's say this is an integer array, meaning this will have integers inside it. So it will be like this, right? Okay. So this is your, let's say, array. Now, in this array, all these in memory without having space in between them. So there is no space in between them. Okay. If this is your, this whole thing is in your computer memory, so all of this will be put together only. Okay, it will not be like that 3 is over here in the memory, 5 is over here, 6 is over here. No, these are contagious blocks. Contagious. These are all together, put together. Okay, so all these data are put together. All these data are put together. Now there are several advantages of arrays, several disadvantages of array. Okay, now let's understand that also. Now, what is the disadvantage of array? What is the disadvantage of array? First disadvantage of array is that once, yes, it is not flexible. Once you have declared that 1, 2, 3, 4, 5, 6, 7, that there will be 7 elements, that there will be 7 elements inside an array, 7, then you cannot add the 8th element. Okay, cannot be like, okay, I want to add 11 over here, please add. No, that will be wrong. You cannot do that. That is an disadvantage of array. Now let's say we are saying that is fine. If I declare an array, okay, like this. Now the thing is, if I have to add any element inside a middle, okay, there are some elements over here. I want to add an element inside middle. Okay, let's say I have space, but I want to add an element inside middle, in the middle of an array. That is a difficult, because you will have to maintain, you will have to shift this side. Let's say you want to add it here, you have to shift this side of the array to the left hand side, this to the right hand side. That is a little bit of chaos thing, right? You cannot do that, like shift this memory block over to the right hand side, this to the left hand side, so that you can add one memory block over here. That is wrong. Okay, these things can be done, but these are difficult to implement. Now we don't want that. But one advantage of array, one very big advantage of array is there. Okay. Okay. So now one very big advantage of array that other data structure don't have, and why we still use array and not other data structure somewhere, is let's say you have this array. If I write the name of this array is ARR. Name of this array is ARR. Okay. If I write ARR of 2, if I write ARR of 2, what will I get? This is 0th, this is first, this is second. So if I write ARR of 2, we are able to access the second element, right? Now, tell me one thing. Are we going like this? Oh, first element, you are 0. No. Second element, no. Then we are moving to third element. Are we going like this? First this, second this, third this. Are we traversing? If I, let's say, have to do 0, 1, 2, 3, 4, 5. If I have to access 5, are we going first this, second this, third, fourth, fifth, sixth? Are we doing like that? No, we are not doing like that. If I just write ARR of 2, I will get the value 8. I will get the value 8. Okay, I do not have to traverse whole array. Yes, fast in accessing the elements. See, in other data structure, if you have to find a particular, if you have to go to a particular index, you have to traverse through that data structure. Traverse is the word, meaning you have to travel through the data structure to get there. But in array, you don't have to do that. You just write ARR of 2 and you will get 8. Let's understand a little bit about big O notation and with respect to what this is. Okay. Now, let's say this was not an array. This was not an array. But in other data structure, we don't have to travel. In trees, graphs, you have to travel. You cannot directly access those. Okay. This is an advantage of array. Now, let's say this is an array. This is an array. Okay. And there are n elements inside it. There are n elements inside it. How many elements? N. There are 5, but let's say we call the last number as n. Okay. Now, to travel to the last number, and if this was not an array, and we have to traverse, how many times we have to traverse then? If we have to get the last value, and we have to traverse, how many times will we have to traverse? N is the answer. Okay. Yes, 5, or you can say n times. Last value is n. We will have to traverse n number of times, right? N times. So this you can relate with the big O notation. Let's say I have to find the last number. Then how many times will I have to travel? N times. So what is the complexity? Time complexity is O, that is big O of n. This is n. And this is big O notation, meaning how much time it will take. So how much time will it take? N. So what is the complexity of finding an element? O of n. But if we are talking about arrays, and if I want to get the value 2, I can just write ARR of 2 like this, written over here. I can just write ARR 2 and I will get value 8. I don't have to traverse 0, 1, 2. I don't have to do that. Meaning that complexity of this is constant. It has constant time complexity. You don't have to traverse complexity. Okay. See, in O of n, you are traveling through the whole array n times. Okay. You are traveling from here to here to here to here. So you are traveling. Okay. So n times you are traveling, right? You are traveling n times. So the complexity is O of n. Okay. O of n. But in array, you don't have to travel. In array, you don't have to traverse through the array. You can directly land on any element you want. Let's say I want to access this element. So what I will do, 0, 1, 2, 3. I will just write ARR of 3. I don't have to use a for loop. Are you understanding? I don't have to use a for loop that for int I equal to 0, I less than array of length, I plus plus, and then iterate. Are you index number 3? No. Are you index number 3? No. Are you index number 3? No. Are you index number 3? Yes. So I don't have to travel. I don't have to traverse. I can get the value in array in constant time. By just writing ARR of 2, I don't have to use any for loop. So that is why complexity is 1. O of 1. Okay. Now, the thing about big O notation is it always calculates the worst case scenario. It is used for calculating worst case scenario. What is the worst case scenario and what is, you can say, best case scenario, average case scenario. Let us little bit understand about that. Let's say you have some numbers over here, 8, 10, 15, 20, and 25. Okay. Now let's say you have to find number 8. You have to find number 8 in this array. You have to find number 8 in this array. Okay. Your task is, you have been given one array and one num equal to 8. The task is find out where that 8 is in the array and return its index. Now you will be like, okay, I will traverse through the array one by one and I will find out number 8. Okay, going from here to here. But when you use the for loop, what you find out that on the very first place, on the very first case, you have 8. You have 8, right? So this is your best case scenario, right? That in best case scenario, you will find number 8 on the very first position of the data structure or array, right? If you find an element on the very first place, then you don't have to travel all these and don't have to waste time, right? We'll say, okay, this is equal, I will break the loop and we are out, right? So here, that is fine. This is called as best case scenario. Best case, that is O of 1. We took constant time only, found it on the very first try. Okay, now what will be the average case scenario? Average case scenario will be if you find out an element over here to here. Okay, this will be average case, meaning it was found anywhere over here. That will be average case. And what will be the worst case? Worst case meaning if it is found on the last element. Okay, that means you will have to travel all the way through the array to find out a particular number, or it is not even available in the array. Okay, let's say you are finding 88. In that case also, you will have to travel all the way to the last, and then only you will be able to tell that this number is not available in the array. Okay, so you have to travel all the way, right? Even after that will be your worst case. In worst case, time complexity will be O of n. It will be O of n, right? Now, what will be the complexity in the average case? What will be the complexity in average case? Now, understand this part. We can say that, let's say you are finding, okay, if the element is over here or over here, okay, over here or over here, we can say that n is, what is n? 5. It is available at n minus 3 or n divided by 3, something like that, right? N divided by 2, sorry, n divided by 2. That will give you 2 and minus 3 minus 2. Like, you can get my point, right? It is available at n divided by 2, this location, or n minus 1 location, or n minus 2 location, or n minus 3 location, right? In average case, where they're located. So you will be like, okay, then you can say how many elements are there inside are called as n. How many elements are available inside this are called as n. Okay, I will repeat, don't worry. In best case, it is O of 1, element found at the very first beginning. So O of 1, you don't have to travel all the way. O of 1 is found at the very first position. For worst case, you will have to travel all the way through the array, all the way through the data structure. But you can say in a way definition of like how many operations. O of 1, O of n. But if it is available over here, it is available over here. Now, how many numbers are there inside this? 5. What is 5 divided by 2? 2.5. In integer, we take it as 2. Right? We take it as 2. So, we can say that if number is over here, it is at n divided by 2 location. N divided by 2 location. You can say that this 20 is available at n minus 1 location. Okay. This is at n minus 2 or n divided by 2 plus 1. Same thing, right? N minus 2 or n divided by 2 plus 1. Same thing, right? The thing is, you don't write that. Big O notation is used to find out, you can say, time taken by a algorithm. Time taken, okay? In worst case. So This O is, you can say, a symbol. It is just a symbol, nothing more. Okay, it is a symbol to represent an algorithm, how much time it takes. In best case, it takes O of 1 time, meaning constant time. Worst case, in this algorithm, it takes O of n. And in average case, you will be like, okay, it takes n divided by 2 or n divided by 2 plus 1, right? No, 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 no. What does big O notation says? If there are any constants, now 2 is a constant, right? 2 is a constant here. If I do O of 2n also, it is also a constant. 2 is a constant. Okay, so, or even if I do this thing, n plus, let's say, 3. Okay, this is also a constant. Big O note constant numbers. Okay, in mathematics, normally constant numbers whose value cannot change. 1, 2, 3 will remain same, right? Okay, so these are constants. So big O notation says you ignore the constants. If you ignore the constants from here, what will be the average case complexity? O of n. What will be the complexity over here? O of n. That's it. So in average case also, the complexity is O of n. Okay, because it says the data is so big, we don't care that if you reach to the last, even if you are middle, your complexity will be O of n only. Okay, unless it is the best case, you found it at the very first, well and good. Even if you're finding it anywhere in the middle, we don't care. It will be O of n only. Ignore the constants. Okay. Okay. Let's take it this way. In a very simple understanding, if I want to tell you something. Okay. If in an interview you are there in an interview, you were able to solve any question, an interviewer asked you what is the complexity of this. What is the complexity of this? When we are talking about complexities, it is meaning of big O only, meaning you will have to say O of this or something like that. Simple way of calculating. Okay, very simple way of calculating. If you are using a loop, okay, to traverse this, you will have to use a loop like this for int I equal to 0, I less than array dot length and I plus plus, right? So in a simple way, if you want to understand now, if you want to understand, you can say that if one loop is used, okay, here I'm using one loop, right? If one loop is used, complexity is O of n, meaning your generally a loop is used for traversing over there, right? So you can say that if one loop is used, complexity is O of n. Even if there are two loops used, one loop over here, other loop over here, for from here to here. Okay, now the complexity will become to O of 2n, O of 2n, right? Two loops are used, but we ignore the constant, so complexity will remain O of n. O of n. Okay, even there are two loops or three loops, it will become 3n, and we ignore the constant, and that is it. Right, Suyash. But the complexity increases. Complexity increases if there is a loop within a loop. If there is a loop within a loop. Okay, let's say I'm traversing this first, and while I'm traversing this, I'm again traversing this first. Meaning, let's say for int I equal to 0, I less than array of length and I plus plus. First, 0 will be iterated, then I'm iterating this again. Then again. Okay, for every number, I'm iterating this array once again. Okay, then the complexity will be increased to O of n square. O of n square. If there are loop within a loop within a loop, it will change to O of n cube. That is the simplest explanation you can understand with a big O notations. Okay, this is the simplest way. If there is one loop, then O of n, loop within a loop, n square. That's it. Okay, and nobody uses loop within a loop within a loop. Okay, it can be there O of n cube, but that will be really, really bad code. When you're talking about big O notation, Okay, big O notation is used for calculating, like, let's say how much time an algorithm takes. Okay. In most of the cases, when you talk about big O notation, you always say about worst case scenario. We always assume the worst case scenario while we are doing programming or while we are making a software. Okay. We don't say for the best case scenario. Okay. We always assume worst case scenario. Okay. Let's say you go to an ATM and you withdraw out some money. You won't, as a software developer, it will not be like that. You add some numbers and you will get the cash out, right? There will be some people who try to bypass that, right? So always think about the worst case scenarios, right? So big O notation, we all while we are dealing with algorithms, we deal with big O notation, and big O notation deals with worst case scenarios. Okay, so whenever an algorithm is asked, or like to find out the complexity of an algorithm, let's say uh, an algorithm is written to you, so you will always assume people are asking you for worst case scenarios only. They do not ask for best case scenarios. Who cares for the best case scenario? Best case scenario can happen to everyone. Same case with average case scenarios. You always assume worst case scenario. So what is the complexity of this algorithm? It will be O of n square. Okay, O of n square. Even if you have to find a number, even if you have to find a number and you are using for loop, you will still say that the complexity is O of n, even if you are able to find the number on the first go. But the, you can say, algorithm takes O of n time. Algorithm takes O of n time. Okay, in worst case, it can be over here also, right? Number can be over here also, number can be over here also. That is the best case, but we do not assume the best case. We always assume the worst case. Okay, that was a little bit of introduction to arrays. Okay, now let's say you have an array. I think everybody here knows about what an array is. Array is a contiguous block of memory location, and ARR, let's say, equal to, write some numbers. Okay, how to print all this array? This is an array. If you have to print the entire array, how will you do it? If you have to print all the numbers in this array, how will you do it? Okay, if we have to print all the numbers inside this array, how will we do it? For int I equal to 0, I less than, what is the length of the array? ARR dot length will give you the length of the array, and I plus plus. This will give you from your moving from 0th index to array dot length. Array dot length will be over here, less than array of length will be last index value, right? And you can just go on and write array of I. Okay. So in the first iteration, it will print 3. In the second iteration, it will print 6. Third, 9, 4, 10, and 12. Okay. Okay. What is the time taken for this? It is O of n time. Right. The logic behind this is simple. This is 0 index. This is first index, second index, third index, and fourth index. There are these index values. Now, if we move from 0 index to array dot length minus 1 index, okay, I less than array dot length. What is the length of the array? 1, 2, 3, 4, 5. And 1, 1, 2 is at index number 4. 0, 1, 2, 3, 4. So we are printing array of 0. What is array of 0? 3. It is printed. Array, then I plus plus to array of 1. 6 is printed. Then I plus plus 9 is printed. Then 10 is printed. Then 12 is printed. Okay. Okay, let's do 1 or 2 simple questions with array, and then we will move forward to array list and then linked list. Okay. We were on how to get input from the user while we are in the array. So you declare an array int ARR equal to new int. Now the thing about array was you have to give it a while you are declaring an array, you have to tell how many elements should be there inside this array, right? So you write over here 10. Okay, meaning this array can contain 10 elements at most. You cannot change that later. So you have created an array, a blank array with 10 elements inside it. Space for 10 elements. Okay. A blank array with 10 spaces. Now with the help of a for loop, you can iterate through it like int I equal to 0 from 0 to array dot length. You can iterate through it. Okay. This is okay. One way of declaring an array is you write the values over there only. Okay. Right? Int arr equal to 2, 3, 4, 5, 6. Other way, if you have to take an input from the user. Okay. Now, taking an input from the user, you have to tell first Java that how many elements are you going to put inside now? How many elements you want? So we have to tell that array, I want 10 elements inside my array, not more than 10. Now we can say that at array of I. What is the value of array of I in the very first iteration? 0, right? So array of 0, meaning at the very first, we will have sc dot next int. Now, what does this sc dot next int does? What does sc dot next int do? It takes an input from the user. This line you will have to write. This is an scanner class with sc object, and with the help of that sc, you are taking input from the user, and whatever the input user is giving you, it is being given to the array. Okay. So array of 0, it takes input from the user. Array of 1, it takes input from the user. 2 from the user, 3 from user, 4 from user. Okay. Now, in the very first for loop, we are taking input from the user. You have declared one array. Okay. An array of 10 space has been created with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So at array of I is 0. 0. User will give some value. Let's say 9. Then again, array of 1. Over here, user will give some value. Again, at array of 2, user will give some value, and this process will go on till last. Okay. Now, once this is done, our array is filled now. If our array is filled, how do we print the array? We print the array the same way. We write a for loop for int I equal to 0, I less than array dot length and I plus plus. And we print out array of I. Let me just clear the drawing. Yeah. Okay. I can print it in the first loop. Now, how will that go? Okay, if I have to print in the very first, in the same loop only, it will go like it takes an input from the user and it immediately prints it. It takes an input from the user and immediately prints it. Takes an input from the user, immediately prints it. Yeah, what I will be doing is I am first taking input from the user. And filling all my array. Okay, filling all my array, my blank array. With the help of this for loop, I am filling all my blank array. So this array will be filled. Once my array is filled, if I have to print the values of it, I use another for loop for that. Using this, I will print out the values now. Okay, let's run this code. It is asking me for input. Let's give 3. Another input, 12, 5, 19, 28, 10, 88, 5, 4, 7. Okay. After I have given 10 values with the help of this for loop, if I have to print those values inside the array, these all values will be set in the array. With the help of these for loop, I am just printing it the same way. 3, 12, 19, 28, 10, like this. I don't want 10 values. Let's do only 3 values for now. Okay, let's give 5, 4, and 3. See, it is giving the memory location. It is not printing the array if I print system.out.println and ARR. Okay, we don't want that. So to print an array, we always need a loop. Okay, let's do one thing. Let us actually understand one algorithm. You have a number and let's say num, int num. Okay, what I will do, I will take an input from the user only. Scanner sc equal to new scanner system.in. Let's say you have one num. Okay, int num, okay, equal to sc dot next int. What you are doing is, what I'm asking to user is user enter a value you want to find in array. Enter a value you want to find in array. Okay, and user is giving a value which is being stored inside num. Now we have one array of our own, int arr equal to, now you can ask user to give an array, you can like user to give values of array you want, you can do that. I'm not doing that because it will take only time. So I'm making my own array 3, 6, 8, 10, 18, and 30. Now your task is to find whatever the number user is given na, whatever the number user is given, if that is present inside this array or not. Okay, user will give you a number and your task is to find whether that number is available inside the array or not. Okay, hold on. Okay, your task is to do this. Now, and if that number is found, you return its index value. You return its index value at what index number you found it. If it is not found, you say that number is not found. So what you can say is we can iterate through the array int I equal to 0, I less than arr dot length and I plus plus. Okay. Now we can say that if the number which you have given to us, which the number which user has given to us is equal to the current number which we are on, let's say 0 or 1 or 2 or 3 or 4, whatever we are on, if it is equal to that, meaning if it is equal to arr of I, okay, I being the index value and arr of I is the actual element, and if number is equal to arr of I, then we can say that number found at index, what is the index? I. At index I. Number found at index I. And as soon as we found a number, let's say user give a number as 655. At 5, if it is equal to I, no, then you move forward. If it is equal to 3, move forward. If it is equal to 655 and user is also given to 655, if number is equal to number, then number found at index number I, we found it, and we don't need to check any other further. We don't need to check any further because we found our number over here only. We don't want to continuously, you can say, go to the end. There is no need. So we will break the loop. Okay. Now, if I run this code, it is asking me enter a value you want to find in an array. Okay, let's say I want to find 1000. Okay, no, 1000 is not available. Let's say I want to find 18. It is saying number found at index number 5. So 0, 1, 2, 3, 4, 5. So number found at index number 5. Let's run it again and give 30 this time. 30, number found at index number 6. Now if number is not there, what we can do? What we can do if number is not there? Okay, if I just write at the end number not found, it will actually be wrong. It will actually be wrong. I will tell you why this will be wrong. I cannot just write after the loop. If number is not found, you can write number not found. If I, let's say, write 655, which is there inside this, it will first print the index number. After this, it will break out of the loop and it will print number not found. We don't want that. See, number found at index number 2, it is saying number not found. It is good. This writing outside is good if number is not found. If number is not found, it is good in that case. Okay. So it is good in case if number is not there. But if number is there, how do you do that? We can say that let's declare this int I outside. Let's declare it over here. Okay. Int I. I'm declaring it outside. I'm using it inside. Why am I doing that? Because now the scope of this I is for this whole main. If it was declared inside this for loop, the scope of this I would have been till here to here only, right? But if I'm declaring this I outside, the scope of this is now in the whole array. Okay, I'm declaring it outside, using it inside, and after the for loop. Now, if number is found, you are breaking. Now, if number is not found, number is not found over here, number is not found over here, 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 not found over here. Okay, meaning the value of I, that is I equal to 0, I equal to 1, 2, 3, 4, 5, 6. If number is not found, it will be equal to array of length. Am I right or wrong? Right now, we are moving our loop from less than length, and our condition will, you can say, get false if our value of I is equal to array of length. At that point, our for loop will break, right? So we can say that if I is equal to array dot length, just like we did in prime number, if you remember. Okay, if I is equal to length, meaning we have iterated through the array, and number is not found. Value of I will only be equal to array of length when number is not found, right? If number is found, we will break over there only. But if number is not found, our value of I will at the last will be equal to array dot length, right? If it is equal to array dot length, we will say number not found. Let's try to run this, and let's say if we want to find 3, it is saying number found at index number 1. It is not printing this now, number not found. If we have to find 1000, it is saying number not found. Okay, understand this. You have declared one I. Now the scope of this I is in this whole main, right? This I can be used in the whole main, not just in the for loop. In the for loop, it can be used, but not in the main, or like everywhere in the main it can be used. When does the for loop break? If you have written a break statement, then only it breaks. Otherwise, when this value, this condition becomes false, right? When the condition becomes false, then it breaks, right? Then only we come out of the loop, right? Now, if we have been given a number, let's say 1000, you have been given a number 1000. For int I equal to 0, value of I is 0. If number, that is 1000, equal to error of I, error of 0, no. So we will not go inside this if block. And we are still inside the for loop only. Then I plus plus. Okay, over here 3. 1000 equal to 3, no. 655 equal to 3, no. 8 equal to 3, no. 10 equal to 3, no. 18 equal to 3, no. 30 equal to 3, no. And we are still doing I plus plus. Okay, because our code doesn't know that we are at the end of the array. Okay, it will do I plus plus. We are moving till less than array of length. Less than array of length. Okay, now it will become, value of I will become I plus plus, that is equal to array of length. Okay, now it will, meaning we will come out of this loop. Value of I become array of length. This becomes false. I less than array of length, because value of I is equal to array of length. Array of length is not less than array of length. So we will come out of this for loop, right? This condition will become false. And as soon as this condition become false, I'm saying that if value of I is equal to array of length, meaning you have iterated through the whole array and your number is not found, and you have moved one step ahead of it, then you print number not found. Got it? Okay, now if you write 10, see, number not found, number not found, number not found, number not found, number found at index number 4, number not found. This is bad, right? Because it is printing number not found for every number, but we don't want that. Number not found should be only be, you can say, printed when you have traversed through the whole array and number is still not found. Number is still not found, then only you will write number not found, not for every number. Okay, that is why we are using if at the last. Okay, now the thing which we did right now, it is called as linear search. This thing is called as linear search. This is an algorithm only. Linear search algorithm. If you have to find a number or find an element inside an array, this is called as linear search. You first go to the very first, found, you give it, otherwise you go to second, go to third, go to fourth, go to fifth, and go to sixth. Okay, this is called as linear search. Linear search. Okay, I'm very bad at writing with this mouse. Okay, linear search. I hope this is clear to everyone. And the complexity of linear search will be then O of n, meaning it will take n amount of time to find an element. That's it. In best case scenario, it will be of O of 1, but we don't care about best case scenario. Okay. In average case scenario, it will also be O of n only. But when complexities are being asked, you always say for worst case scenario, that is O of n. Okay, always assume the worst, that is O of n. Okay. Now the next topic which we are going to cover. It will be array list. Yeah, once we learn array list, then we'll move to linked list and know the difference. What is the difference between array list and linked list? Okay. Now, what is an array list? Now, array list is an implementation of an array only. Array list is an implementation of array only. Okay, it is nothing different. Only one change is there. Okay, only one change is there with array list and array is it is dynamic in nature. Array list is dynamic in nature, meaning you don't have to give a prior size. That size of the array will be 10, right? We give size of the array is 10. That is not the case with array list. Array list has a dynamic size. It has a dynamic size. Oh, if you have one more element, no problem, you can be added here. Now you have a list like this with elements inside this, numbers, or let's say any other data type, and you have another, let's say you want to add another number. So what will happen? With the case of array, it says no, you cannot add any other number. That is not possible. I won't allow you to do that. So it is not possible. But with the case of array list, what can happen? It can say, okay, no problem, you can add one more here. Okay, you want to add one more, you can add one more here. You want to add one more, you can add one more here. That's easy, right? Because array list is dynamic in nature. It can increase or decrease its size. Without any problem. Okay, but the case with array list also, it is also in contiguous blocks. Meaning these all are together in memory. Okay, contiguous blocks. These are not separate. Okay, these are continuous blocks together. Okay, you can delete like this. You can delete from starting. You can delete from middle. Although in the case of deleting from middle, it is again difficult. Why it is difficult? See, if you are deleting an element in the middle, then this will have to be removed. Then this will have to be shifted this side, or this will have to be shifted this side, right? To make it contiguous once again, right? Are you getting my point? So it is still a disadvantage of array list that it is a little bit difficult to delete elements, but its main advantage is it is dynamic in nature. I will repeat one more time. So this is an array list. It looks just like an array. Now the difference is you can add an element which is not allowed in the array list, which is not allowed in array. You can delete an element, this will be removed. You can delete an element from the starting also. You can delete an element from the middle also. Okay. Now advantage of array list is you can add elements. It is dynamic in nature. But disadvantage is if you're deleting an element from the middle, and these are continuous memory blocks. Okay. If you want to delete this one, which I'm on right now, then this will have to be removed from here, and this side will either have to shift this side, taking like this will be shifted over here, this will be shifted over here, this will be shifted over here, or this will be have to shift over here, this will have to shift over here, this will have to shift over here, this will have to shift over here. Are you getting my point? This can happen, but it is difficult, right, to do that, to delete an element from the middle. Are you getting my point? You will have to adjust to right hand side or left hand side. Okay, now let us first, you can say, declare one array list. Okay, array list implementation of array list is already there. We don't have to create our own, you can say, array list. You will understand what is the meaning of that. Meaning Java has made array list for us. How array list is defined, all its methods, all the methods of array list. You can declare an array list like this, array list. Okay, Here define what type of elements you want inside the array list. I want integer element inside this, so you will write integer. Give your array list a name. Give your array list a name. Okay, let's like we give an array our name like ARR, so we'll name it as list. Equal to new. Okay, we have declared one array list. Okay, now we have to import it. Okay, import it from java.util. So we have declared one array list. Okay, now if you have, you can say concept, if you have learned oops little bit, then you will understand that this is a class. This is the name of the class, right? And this is how you declare its very, you can say objects, right? So that means there is one class by the name of ArrayList inside Java, and we are creating its objects. And with the help of that, we can access its methods, different methods. That is known to everyone, right? This is important because once we move to linked list, it will be very important to know that. Okay, so we are creating with the help of this array list that is there inside our java.util. We are creating one list, and inside this list, you can add different elements. You can write list.add. Now, this add is one method, inbuilt method of array list, which is created by Java only. Okay, list.add, what you want to add? 9. It will add 9 into your list. So, it will be like 9. Okay, now we want to add anything else. Can write list.add 10. List.add 90. So it will be like, yeah, 9, 10, and 90. It will be like that. Okay, it will be added at the last of it. First is created, it is then added to the last of it, added to the last of it, like this. Okay, now we can print our array list directly, not like an, I can say, we don't need a for loop. Although with the help of for loop also you can print individually, or you can just directly like write list, and that will also do the job. That will also do the job. If you just write list, it will print the entire list. You can say 9, 10, 90. Okay, it is created. If you add another thing, it will be added to the last of it. Now, let's say you want to get any particular element at a particular index. Okay, let's say you have 9, 10, 90, and 100 along with it. If you want to print 10, you will write list.get. List.get. Okay. Now, with the array, you used to write arr.length. With the array list, you will write arr.size. arr.size. Size will give you how many elements are there inside this. How many elements are there? 4. Right, it is 4. Okay, now let's say you want to remove, then you will write, let's say not print. If let's say 9, 10, 11, 9, 10, 90, 100 are given, and I remove an element, list dot remove, list dot remove. I want to remove this element. Is that what index number? Index number 1, like, so right, 1. List dot remove 1. Now this will be removed, array will be adjusted accordingly, and if I just print list now, it will print without 10. That is 9, 90, and 100. Got it? 9, 10, 90, 100 was added. Then we removed first index value, and we have first index value removed, and the rest of the array is printed. Now, in array, you don't have any such method, right? In array, it would have been difficult if you wanted to delete anything, right? How would you delete an element in the array? Okay, so in array, if you have to sort the array, in ascending order, how would you do that? If array was given and you wanted to sort it, how would you do that? Let's say 3, 19, sorry, 3, 19, 4, 90, 27, 44, 2, 6. Okay. We have this thing, if you have to sort this array. Okay, if you want to sort this array in ascending order, if you want to sort, you can sort it like arrays dot sort. It will sort the array in ascending order, right? ARR, it will sort the array. Okay. If you have to see the result, we will have to use for loop. That is a disadvantage. I cannot just see. Okay, and we can write. Okay, you can see that this is sorted way. 2, 3, 4, 6, 19, 44, 77, 90. The array is now sorted. This is clear now how to sort an array. Okay, this was our array list. If you have to sort this array list, this is already sorted right now. Let's say we have 900, 900, 190 and minus 7. Okay, if I have to sort this, how will I sort this? I will write collections dot sort. Collections dot sort. Okay, and I give the name of my list. This will sort my list and I can print it. Okay. Okay, if you want to sort it in reverse order, although I would not recommend that you use all the inbuilt methods only, but if there is a need and you want to sort it in reverse order, first simple thing what you can do is sort it in ascending order, then reverse it. Okay, but if you are like, no, I don't want that, so what you can do is you can write the name of the list, comma, you can write comparator dot reverse order. Okay, this will sort your list in reverse order, okay, or descending order. Got it? If you want to sort your list in descending order, you can do that using collections.sort comparator or reverse order. It will sort your array list in reverse order. Although I would not recommend that you use inbuilt methods only for doing every task. Okay, make something of yourself also. Okay, we're done with the array list. Okay, now the difficult topic. Not actually difficult, but a little bit tricky topic is linked list. Okay, maybe you will not be able to understand what I'm writing in the code exactly. Okay, but try to reason with it. Okay, so try to reason with the code which I have written. Maybe you will not be able to understand in the first go, but try to write the code which I am writing as it is later yourself. Try to write it once, try to write it again, try to search from the internet, try to find it from the chat GPT, try to find the meanings. I will be telling you in detail what is the meaning of everything, but still, I know that linked list is not being like you will not be able to understand linked list. I'm telling you in one go, you will need practice and you will need practice on your own. Okay, this is my caution to you, but don't lose hope. You will be able to understand it. Now, let's talk about linked list. Theory you will understand. Theory you will understand in one go. Okay, when we talk about array, what is an array? Array is like this. You go like this, right? Okay, this is a array. This same is an array list, but with one change, that is, it can increase in size, right? It can increase in size or it can delete some elements, right? Now, what is a linked list? Linked list is used to do the same thing. It is used for doing the same thing, but with a little twist. Now, a disadvantage of array is that it is in continuous blocks, right? It is in continuous blocks. Maybe some block is not available over here. Okay, then it will give you some errors, right? If let's say memory is getting over here, so you will get some errors, right? Now, what is a linked list? Linked list is like this. You have one block. Okay, this is called as node. Okay, while we're dealing with linked list, definition should be correct. This is called as a node. This is called as a node. Another node, another node, another node, another node, another node. Okay, the difference between linked list and array list is that it is not a continuous block. It is not a continuous block. These are different memory location. These are different memory locations in your computer. Okay, one is over here, 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 one is over here. Okay, this is not continuous. This is not continuous. Now, this node will contain two things. This is called as singly linked list. What I'm teaching is called as singly linked list. Singly linked list. Okay, now this is called as node. These all are nodes. Nodes will contain two things. One is the data which is inside it. Let's say 8. Okay, same way 10, 15, 25, 4 and 2. Okay. Linked list contains two things inside it. One is data. One is data that you write your data normally, right? That your list contains 4, 5, 6, 7, 8, right? What is the other part? Other part is used to join two lists. Other part is used to join two lists. Okay. In C++, it is called as the pointer. In Java, we use a reference variable. How? This thing, okay, mostly it is called as next. Okay, and there's no fixed name. You can call it anything you want, but we generally say it as next. What it is called as? So what are the two things that link your node contains? Data and next. This is data and next. Data and next. Everyone clear? What is this next? This next is, you can say, points towards the next node. This next refers, or you can say address towards the next node. So this next will have the address of this node, node number 2. This next will have the address of memory address of node number 2. Okay, so if this has the address of node number 2, they will be connected. This next will have, let's say, address of node number 3 over here. So they will be connected. Memory address. This will have memory address of the next node. We call it as next, but you can call it anything you want. Okay. This points to the memory location or memory address to the next node. This will point towards this. Let's say, is memory fixed? No, Pratik. Let's say this points towards this now, and this points towards next. Okay. These are not, you can say, linear in nature. These are not together. But they still form. If you have this, you can go to 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 this, and you can go to this. Okay. One more thing. This whole thing is called as a linked list. This whole thing is called as what? A linked list. So linked list is made with the help of nodes. Linked list is made with the help of different nodes, and nodes will have two things inside it: data and next pointer. So what it will be pointing to the next thing. Okay. Now, you can say the starting of the node. Okay. You cannot just start in the middle of the node. You cannot just start in the middle of the node. Starting is to be preserved. If you have to go over here, you will have to go from here to here to here to here. Node is just a memory address. No, the next pointer, next is the memory address that points towards the next thing. Node contains two things, that is the data and the where it is pointing towards the next, Okay. Now, if I have to go here, I have to go from here to here to here to here. Last thing. One more thing, the very first thing, okay, like this is pointing to this, 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 and this is pointing to this, right? So if I have to start, there is something called as head, which will not have the data, Okay. Head points towards the first node. What points towards the first node? Head. Head points towards the first node. Okay. And we start our node from the head only. Okay. We start our node from the head. Okay. The last pointer, there is no other thing apart from this. So last will be pointing towards null. What will be last pointing towards? Null. First node will be pointed towards head. Last will be pointing towards null. Okay. Now, one more thing. Head should always be pointing towards the first node. Let's say you were traversing the linked list. You moved your head from here to here to traverse, and you move your head towards here. Okay. Then you print, it will print only this part. Okay. Because you start from the head points toward the first element, it will consider that these elements does not exist and it will delete them. Okay. So head should always point towards the first element. Okay. And if you have to traverse the array, linked list, my mistake. If you have to traverse, you can say that heads points towards this, the next points towards this, points towards this, we can say that while the value of whatever from which we are traversing, that is head dot next, while the value of head dot next is not equal to null, is not equal to null, this points towards null, right? So while the value of head dot next, head dot next, head dot next point towards this points towards this points towards this points towards this point towards this point towards this. Sorry, right? Null should be here. So while the value is not null, we will traverse. We will traverse. I know this is a little bit confusing, but again, try to understand. Okay. So we have one singly linked list. We have one singly linked list. First part is called as head, which points towards first node. That point, the next part of this points toward the second node. I will just make it a little bit clear now. Okay. So head points towards the first node. Its next pointer points towards this. Its next pointer points towards this. Next towards this. Towards this. Towards this. Now, I will tell you why linked list is of advantage. Why linked list is of advantage and where it is disadvantage. Okay. If you have to get any particular element, let's say this is index number 0, 1, 2, 3. This is index number 3, right? If you have to get index number 3, you have to first go to here, then go to here, then go to here, then only you can get the index number 3. There is no direct access like this or dot get function. You have to traverse. You have to traverse using a loop. Okay, that is a disadvantage. But there is an advantage. There is an advantage, that is manipulation, or you can say addition or deletion of elements inside a linked list. Addition and deletion of elements inside a linked list is much more easier and much more practical than that of array or array list. How do I say, why am I saying that? Okay, let's say you create another node. Okay. What we can say is, let's say this nodes need to be, I can say this node has to be the very first. This has to be inserted at the very first position. Okay, over here. How we can do that? We can say that the next pointer of this points towards this memory location. Points towards this memory location. What is this memory location? Head only, right? Head is pointing towards this, so this will point toward this memory location. Now, head and this is both pointing towards node number 1. Now what we will do? We will point head towards the first memory location. So head is pointing towards this is pointing towards this, and you have added your node to the very first position. Okay. So this is inserting an element at the very starting. How will you insert an element to the very start? You will point the next of your new node to the head location, that is node number 1, and you will point your head towards your new list. So head will be pointing towards your new element, and rest is the same. Now, let's say it was not the very first, Okay, let's go for the last. Last is also easy, right? Going towards the last is also easy. You will say that traverse through the array, traverse through the linked list. Okay, until I found the next, the value of next pointer is null. Until the value of next pointer is null. Whose next pointer is pointing towards null? Only the last element, right? Last element's next pointer is pointing towards null, right? So I will say, while the value of next pointer is not equal to null, traverse, go to the last. While we are here, I will say that this node's next part, that was pointing towards null should point towards new node now. And new node's next part should point towards null. Although by default it is already pointing towards null, so don't need to write next, like new node's null should point towards null, but you can write that. But you got a point, right? How to add an element at the last, right? Okay, now let's say this was pointing towards null. Forget this for a moment. Let's say you want to delete an element from the last. Okay, how would you delete an element from the start? from the last. From start, you can do that. You can move one pointer towards here and point head towards here. If you point head towards here, it will automatically be the new list, because head is pointing towards here. This will already be discarded. Okay, point the second last pointer towards null. Point the second last pointer toward null. If I point this to null, this we will like there will be no link between this one and this one, so this will automatically be deleted. How do I do that? How do I do that? We say that while next dot next. See, next is pointing towards this, its next is pointing towards this. So if I'm traversing, I'm saying that while next dot next. Okay, while head, you can say any temporary variable dot next is equal to null, meaning this is equal to null. No, but yes, if I have to delete the last element, I have to point this towards null, meaning I have to traverse till here. Okay, I have to stop over here. Okay, when will I stop in over here? When I say the next pointer of this, yeah, I am telling you, when the next pointer of this is pointing towards this, right? Next pointer of this is pointing towards this, and next pointer of this is pointing towards null. When I say next dot next is equal to null, when next dot next, okay, is equal to null, I have to stop over there and point next towards point that node equal to null. Okay, let us start with the coding part only. See, now you will say what is the why we learned all these things. See, the one thing is you can make a linked list. You can make a linked list that is already given to you by Java. Okay, you can just write linked list of type integer, just like you make an array list. Call it as list equal to new linked list. Sorry, type integer, and there you go. Okay, you can import the linked list, and your linked list is created. But this is, you can say, already given to you by Java. Whenever top companies ask you, they don't allow you to create the linked list which is already made by Java for you. They say that you create your own linked list implementation. Okay, you create your own linked list implementation where you have your own methods, not the linked list which is given in Java. You can create a linked list. You can say list dot add 5, list dot add 90. Okay, you can do that, and then you can go and print the list also. Okay, we'll say that this was easy. Why we were learning all those about pointers. Okay, this is the internal implementation which Java has already done. They have already made the data and everything, and you can just write their linked list. Okay, and you can add. Okay, this is their thing. Okay, you can add, you can delete, and add list dot remove. You can easily remove also. Okay, say first, so 90 will be removed, just like an array list you were doing, right? Just like an array list you were doing. But this is not the internal implementation. Internal implementation is only the difficult part, which I was telling you. Okay, the pointer, the next pointer, where it is pointing. Okay, tell me what are the two things that is contained inside a node? Data and next part. What I'm doing, I'm creating a class called as LL. Okay, I have not named it as linked list because that is already a class that has been created by Java. So I named it as LL. Okay. Now, linked list contains what? It contains nodes. Right? Linked list contains nodes. Right or wrong? Linked list contains nodes. So I created a class, private class, inside that class only. Inside a LL class, I created a private class called as node. What are the two things that is contained by nodes? Data and next. So I'm giving int data because data will be of type integer, right? Data will be of type integer, and node next. This is the name of the class. Node next. Node will be pointing towards the next element. Node will be pointing towards the next node. Okay, this will contain memory location. memory location of the next node. Got it? If I will call this node, that is node equal to new node, a new node like this will be created. Okay. And here is one constructor, that is whatever value you will give inside the data, that will be given over here. I hope everyone is clear about that. So whenever you call this data, like whenever you will call node equal to new node equal to new node and give some value, that value will come over here. From here it will go to here. Okay, because this is private. So a node will be created with whatever data, let's say 7. Why use node as type for next? Because that is the name of the class. China, that is the name of the class. That is why it is an object kind of. Okay, private is just a data type. Sorry, private is just you can say nobody can access it directly. Node next. Okay, that memory location will be of type node. The next memory location from this to this, what it will be pointing will be of type node only. Okay, node is created. Now we will create our linked list. I have already made all these things so that I don't have to type everything again. We have made our class called as linked list. Now, what are the things that are contained by linked list? What are the things that are contained by linked list? These are different nodes. Okay. One thing that linked list will contain, one thing that linked list will contain is the size. Okay. As you move an element, you increase the size. As you delete an element, you decrease the size. So one thing will be size. Other thing will be head. You have different nodes. Okay. But you don't know the starting part. If you don't know the starting part, you are lost. So it has to has one head. Okay. Head. And we are talking about memory locations. So head will also be of type node, because it will point towards the memory location of the very first node. Okay. So let us create some methods. First is add start. What is the meaning of add start? Meaning, if a list has already been created, okay, assume that there is already a list. There is already a linked list created for you. Okay. If you want to add an element at the start, how will you do that? Head is pointing towards here. Assume for now. Head is pointing towards here. How will you add the element at the start? Okay. First, what we need to do? We need to create a new node over here. Okay, we will create a new node. A new node is created by writing node, give it a name, node equal to new node, and give some data. Right? Give some data. We will be implementing when we actually write. Okay. This new node has been created. It has next. What we are saying? The new node has been created. Node dot next. What is node? This node. That is node dot next equal to head. Where was head pointing? Assume that this is already created list. Okay. It is pointing towards the first node. Right. So we can say that node not next. Node's next part will be pointing towards head. That is, it will be pointing towards here. Now, head equal to node. Head will be pointing towards node. And you will be saying that it is connected now. A new node has been created at the start of the linked list. Okay. Now we will learn about if a list is already created. Like this is head pointing towards here. This is pointing here. Okay. Create another one pointing here. Now this is one linked list created. If you want to delete this element, how will you delete this element? Okay. First, we are writing that if head is not equal to null. What is the meaning of head not equal to null? If head is equal to null, meaning there is no list, right? If head is equal to null, meaning there is no list. So we will write linked list is empty, no first element exists, right? If head is pointing to, because head points towards the very first element, and if it is pointing towards null, that means there is no list. right? Clear to everyone? Okay. So we are saying that if head is not equal to null, if head is not equal to null, what we are going to do? We are writing that where is head pointing? Where is head pointing? First node, right? It is pointing towards the first node. If we write head dot next, where it will be pointing then? Head points towards the first node, dot next will point towards second node. Head dot next will point towards the second. So we are saying that head, value of head is equal to head dot next. Head dot next was pointing towards the second node. So you can say that it is like this now. Head is pointing towards here. And there is no relation here. So that means list is starting from here. If list is starting from here, this is automatically deleted. So size minus minus, if the size of array was 1, 2, 3, 4 earlier, size minus minus will get you to 3. Size is equal to 3 now because we are deleting an element. Okay, let's do one thing. Let's implement these two things. Okay, now we have main. Okay, how do we write our linked list? We write ll, the name of our class, then the name of the list equal to new ll. Okay, and a list has been created with ll. So we have created. Now we can say that list dot what we learned add start, right? We learned add start. So at the start 10 will be added. At start 10 will be added. Okay, let me write list dot add start only. Okay, let's say 20. Now understand this thing. It will be like 10 is created from the scratch and we are starting in front of it. This will assume that this is the already created list and it will be like 20. So list will be like 20 and 10. Okay, add start because we are not writing add end. It is adding at the start. Now if I have to display, I made my own method display list dot display, right? So if we display it, it will be right 20 and 10, right? Not 10 and 20 because 20 is being added at the front. Okay.
Just a quick info, guys. Intellipaat offers a full stack web developer course in collaboration with iHub IIT Roorkee. Through this course, you'll learn tech stack like MongoDB, Express.js, Angular, Node.js, along with HTML, CSS, JavaScript, and more from the IIT faculty. With this course, we've already helped thousands of professionals transition into high-paying developer roles. You can check out the success stories on our Achievers channel, whose link is given in the description below. No doubt this course can take your career to new heights. So check out the course page link in the description and take the first step towards becoming a certified full-stack web developer.
So the first thing that we want to study is the array. Okay. So what is an array? So arrays are basically, you should think them as a sequence of numbers. Okay. Sequence of identical items or sequence of similar data items. Okay. So here, for simplicity, we represent the items as integers, but in a complex or more involved array, it may be a sequence of real numbers, or it may be sequence of uh, fractions, or it may be a sequence of uh, records or structures. Okay, those who are familiar with structures in C, they can understand that it may be a set of it may be a sequence of records or structures. And normally we believe that the arrays has a set of values, and the values can be accessed by the corresponding indices. So here, if you look at the picture, you see there are numbers like 0, 1, 2, 3, 4. These are called indices of the array. So in using that index, you can check the corresponding element. So at the index 0, the value stored is 25. At the index 1, the value stored is 45, and so on. Okay. So it's like you should feel that the indices are basically some address, and if I just access the array name with the index, the value can be obtained. Only the difference is that the addresses or indices are side by side, and I can access any element of the array with that index only. Okay, I mean I don't need to go to the first element and then go to the corresponding index. It's not like that. So that's why array is a some sort of it's a constant time access. Okay, so suppose I have a big array. So in this picture there are only 5 elements. So if in a practical situation in a computer program, if you are dealing with an array of size 100 or maybe 1000, then you can actually access any element of the 1000 element array just by giving the index. So suppose the index is 177. Okay, so and the index array name is, let's say, student. Okay, so if I just say student within third bracket, say 177. Okay, then I should get the corresponding element. Okay, so it can be done in, the element will be obtained in constant time. It is not that if I ask the 177th element, it will take more time, or if I ask for the 0th element or the first element, it will take a different amount of time. It is not like that. Everything I access by the index, it takes uniformly same amount of time. Okay, so each element in the array is that's what is written in the box, that is identified by an index, which represents its position in the sequence. Okay, and arrays have fixed size, meaning you need to specify the size while creating them. Yes, that is one of the biggest things to remember, that you cannot say that, okay, now I have an array of size 100, and later I want to have an array of size 1000. You cannot do that. But probably if you really want to do that have that kind of size like 1000, then probably you have to create a new array of 1000 and then have to copy the data from these shorter array. Okay, that is the only possibility. So this array, once you have defined, you cannot probably increase its size. So there are different ways to implement array. In either you can do it in C language or C++. Also, you can do it in Java, okay, which is oftentimes used by many people. So as you can see, this is an example implementation of an array, which says public class array example, and then the main function, and then inside that the array is defined like int within second bracket, then array int new int 5. So then it assigns the values corresponding to the indices. Okay, and then it just prints the array elements from 1 to the length. Okay, so if you run this program on a Java compiler or an IDE, if you will see the printout is shown in the right side. One minor thing that I'd like to say, that the way the array is declared in this case is slightly different than that in another language like C or C++. Okay, so you should be aware of that. It's not just int then third bracket then array. It's rather int array then third bracket, and within third bracket itself the size. Here actually using the new function you are creating that array. Okay, but in C There is no such need. You just declare the array, int array, and then within third bracket you put 5. That means the system understands that there should be an array of size 5. Okay, so slight change of construct of the language, but otherwise the meaning remains same. Okay, declaration. So let me just go through declaration a little bit. So as you saw the declaration in the Java, but in C it is declared like this. Int say it's not. I mean, it's like int. Those who know the way, int main, and then inside you write a lot of things, and there probably you write an array. You are playing with an array. So int say marks, and then say 100. It's like that. So that marks is an array. It's the array that you use, and it's int means actually the type int. The array elements are of type integers, and this 100 means you have a you have an array, or you have a memory space that can accommodate, okay, that can accommodate 0 to 99. That means a total of 100 integers it can accommodate. Okay, so you represent these array positions as marks 0, that is the first location, and mark 99, that is the last location. Okay, so overall you have 100 such memory space. This is the way you declare this. This is called a declaration of array in C, the seal, this part. Okay, just let's say I want to increase the value of some particular element, let's say 50th element, by some number. So I will write, say, marks 50, or actually 50th element will be represented by 49 index. So marks 49 is equal to marks 49 plus 10. So let's say I want to increase the mark of the student which is indexed by the value 49. 49 means 50th in 50th student basically. So because it starts with 0, first student's record or mark is stored in 0th index, so one less. So 50th student's index will be 49. So marks 49 is equal to marks 49 plus 10. So 10 will be. Now one question may come, okay, once you create an array by this kind of declaration, then what are the values stored? So by default, you should assume that normally default the value that is stored, that is ordinarily 0 in a particular language. Okay, and what is the value that is by default? It depends on the language. Okay, for example, in C language or in C++, the value is essentially 0. Most likely in Java also it is 0, but sometimes you cannot 100% say what is the value. So it's better to initialize. If you suppose want that mark everybody should pass and everybody should get a minimum marks, so you can actually give them all of them minimum marks, say 30 out of 100. So I can write a code like this. I can write a code like this for I equal to 0, I less or equal to 99, I plus plus, marks I is equal to 30. So suppose in a subject everybody is appearing and they should get a minimum score of 30. So I initialize everybody to 30 because that is the minimum marks I have to give. And after that, based on the assignments that I give, somebody scores some marks. Okay, let's say 10 marks for each assignment. Then those students, let's say just like 50th student, I can actually enhance their marks to more by adding say 10 or 5. So I can give them more marks. Okay, and after that, if I print the array, I will see that they have different marks basically. Okay, so that is how it is happening. Okay, so if I want to say array of float, okay, float, so it should be something like float. I have to declare something like float, float, float marks, say 100. But remember, I mean, this is something wrong I'm making, because I cannot have two variables with the same name. So it should be marks, f marks. I say f marks. So float, I cannot define marks to be an array of integer, and I cannot again define marks to be an array of floats. So I have to give it a different name. Okay. So I give it f marks. Okay, and then of course I can actually set the f marks, say 49, 50th student equal to, let's say, 41 and half. I mean, I cannot like write like that, but just for, I can always write like 41.55. This kind of value I can. Okay. If I have big data, then I use ON, then take me one element or the last element. Okay. Yeah. So what I mean is that I mean, suppose this is an array. The time taken by, I mean, if you say marks, say f marks 0 equal to 30.5. Suppose you assign this, okay? And then you actually, let's say, print them. I'm using the C logic, printf, say percent float is percent f, okay, or percent g, okay. So you can write like percent g, then again percent g. You write two things: f marks 0, f marks 49. This kind of thing you write. So that means it will successively write the marks of the f marks of the first student and the 50th student. So it will print like that. So this is how you access the individual marks, and both will require, I mean, it is not that to access 0th first student's score will take less time, and to access the 50th student's score it will take more time. It's not like that. It will take identical amount of time. This is the thing that you are doing. So a code defines a Java class named array example. Yeah, that's where inside the class the main method is declared. Starting point of the program, and integer array named array is created. So the basic way how it is done, that is being said. Okay. So what is the code? So this loop is actually printing the value. That's what it is writing. Okay. Tell you one little problem with array that will give you some problem with array. Okay. So let me go back to black. Problem with array. So what is the problem with array? So the problem is like this. Let's say you have an array of size 100. Okay. 0 to 99. So 99 being the last element, A0, index is this AI. Now suppose you have up to say 60, okay? So 59. Up to 59 there are values, and this region is empty. Okay, this part is empty, and here are values. A0 to A59 are full. Full means some marks, etc. Now, suppose you want to, you understand that there is some mistake, okay, and you probably missed some mark, okay, and actually you missed some marks. That means some data should be put, some data should be put in the middle in here, say suppose at 29, at the index 29. So A29 actually should be something new, something different. Okay, that's a new data which probably you missed. Okay, so at A29 you placed some data, but probably the placement was wrong. Okay, so that is not a really A29, it should be A30 and so on. That means only A29, this location should be filled with a new data. Other things should not change. Okay, that is the target. So what probably you have to do is you have to, because here you cannot insert anything, because if you write something in the current A29, the current value will be overwritten. So what probably you have to do, you have to shift these 29 to 59 one place to the right. Okay, you have to shift all of them one place to the right, and that will create a temporary vacant space in this location of 29. This position, it will still have a value 29, but it doesn't, it contains the previous value. Okay, and here just to its right side also, the same value will be there now after shifting one place to the right. And now you can place your new value in this apparent vacant position, which is A29. Okay, this is the apparent vacant position after one shift. So that means if you want to insert some new value, okay, new item in the array, which is not there, which is already not there, then you need to actually change the position of many elements in the array. Okay, and potentially you have to change almost the length of the array. That means number of elements that are already there. So for example, something you put 0 to 59 and you now know that your 0th element was something wrong. So you have to place some new value at A0, and rest things will not change. They will not change. So you will shift them one place to the right. Okay, you have to actually. So the amount of work done will be actually you will have to spend linear time. This is called ON time. Okay? So just to insert a new element or new item or new value, new record, okay, into the array, you may need ON amount of time, because to not disturb the other elements, they must be shifted to the right one place. Now again, another problem will come. Okay, there are multiple problems may happen. Suppose the array is 100, 0 to 99, and the array is full. And at this point of time, you are probably asking to insert a new element, like in the middle, somewhere in the middle. The problem is that you intend to shift the, say, those elements, okay, another the right part, that you want to shift one place to the right. But now, if you want to shift one place to the right, you cannot accommodate 101 elements, because the array size is just 100. Okay, so your one element will always be dropped. Okay, so probably you cannot do that in this particular array. Okay, so I put a question. Okay, I put a question that how to insert an element, new element in an array when the array is already full. So that is the question. So how to insert a new element when an array is already full? This is another question, important question. What are the difficulties? So now suppose I give another problem. Okay, it is just the opposite problem. Opposite problem means earlier I introduced the array. So suppose the 29th record, so this is 29. So A29 is the record or marks that is of some particular student who probably have left the institute or college or something. So I want to delete this data. Okay. So what I do, I just fill it with 0 maybe. Okay. But is it going to work? Probably no. Then it will not be an array. Okay. So it will be vacant, that place. So you have to shift the remaining all the elements one place to the left. So basically you have to shift this one here, then this one here, like this. You have to shift all of them. Okay. Blah, blah, blah. So in that case, the actual array size will decrease, and probably it will become one less than the earlier size. So potentially insertion or deletion of a new element from an array, insertion of a new element or deletion of an existing element from the array is actually troublesome, and it requires linear amount of time. Okay, in the worst case, linear. Okay, linear means on. Why on? Because see here I may have to shift actually how many elements I do not know. So let's say L. I have to shift L positions. So L actually minimum can be 0. I do not have to shift anything. L maximum can be actually order of n. Okay, maximum can be n. N number of elements I may have to shift. So that's why worst case we say that L equal to big O of n. So big O of n actually comprises worst case behavior, and it may be that worst case I may have to shift half of the elements or something more, but it is always a function of n, proportional to n in the worst case. Remember, when I say big O, you should always mean that there is a worst case scenario that we are talking about. About to start linked list. So what is linked list? So let us go through the slides and then we'll take up a real practical notion. So linked list is essentially, so the array limitation is that it's a contiguous set of location. Okay. So that creates the problem. So in linked list, that contiguous location, that concept is removed, and we can store the elements in different location. Each element we can store in different places, and still we can have a sense of connectivity. Okay, so that is what is a linked list. So, but because of putting the elements or the items at different locations, we need to just the data or the value is not good enough. Some more information is required, and that is the next information or the address. Okay, so I know the address of the starting element, but I should also in the content of the starting element, I should also get the address of the next element. So it's like I do not know the address of my friend. I do not need to store. So what I do, I know I store address of one of my friend, and I ask, okay, can you please give me the phone number of that person? He gives me that number, and from that number I collect the address of the next person. So it is just like that. Okay. So I have data and next for every record. Okay. And they are connected like this. And at the end, it is null. Null means the next is null means there is no further element in this list. Okay. And because every item now contains a data and an address part, so it becomes a little more complex. But this complexity is what because it introduces some advantages also that we'll see. So linked lists are dynamic data structure, meaning they can grow and shrink as needed. Yes, that is one of the biggest advantages of linked list that we will see shortly, and it removes those disadvantages of the array that we just saw, that inserting a new element in an array or deleting a new element, existing element from an array, both require linear amount of time. But in case of linked list, it can be done in a constant amount of time. Okay. So unlike arrays, linked lists do not require a fixed size when creating them. So that is another advantage of linked list, is that the list can grow actually dynamically. So initially you do not need to tell what should be the size. So initially your size is actually 1. As more elements come, your size grows to 2, 3, 4, and 10. And as more elements come, you can increase it to say 11, 12, 13. As the number increases, you can also increase your size, increase the size of the linked list. So there is no need to specify any specific linked list size. But of course, I mean, so what can be the size? The size is as much memory you have. Okay. So if unless there is a memory limitation in the system, you can keep on growing your linked list. Okay. So a real world example of linked list can be found in the management of music playlist. Yes. So playlist, if you have seen that playlist in YouTube, so you will see that one video you see, and at the end of the video there is a link which gives the link to the next video by that particular singer or that particular speaker or something. So linked list, that playlist. Okay, playlist is also a specific kind of linked list. And also there are other practical problems we will see. So here one example is given in terms of song data. Okay, linked list representation of songs. So at the end of one song, you get the address of the next song, just like that. Okay, so yeah, traversing the playlist. So I think you know all these things. So even before common operation on the linked list, we must understand how things are created. Okay, so let's do it. So how linked lists are implemented? Okay, so basically in C, struct node, you will create such structure, and you will have an integer val, and you will have something like struct node star next, and then this entire thing will be is the type. So this is the node, C declaration of node struct type. Okay, where it contains one value integer, and the next is an address of what type? That is a pointer on address to another box, which is of type struct node. That's why I cannot just say it is a pointer to an int. It's a pointer to struct. Okay. So once I have this, then I can actually create the first one as, let's say, I have inside the main function in the C, I have this main function, integer main or something. So there I can write that struct node star h. H is the head probably. So what I do is I create a new head. I create a new head. Head is equal to, how do I do? It's called malloc. Malloc, how much? I need to create a space, a single struct node type. So I will give malloc within bracket. I will give size of, there is a size of function, and within the size of I will give a struct node. Okay? It is a struct node type. Size of if I say size of int, then it will give me size of integer. But size of struct node will give me a size of struct node, which is essentially the sum of the size of an integer plus sum of the size of a pointer to a struct node. Okay, so this thing will give me an address, and then probably this address should be an address to the such node. So that's why I have to cast this beginning. I have to put something in the beginning. This casting is done by, it's like struct node star. So this thing should be put here. Okay. So once I do this kind of code, then this kind of thing will be created. One location will be created, one box will be created, and it will have two parts, the eval and the next. So next will probably be, the value will probably be initialized to 0, okay? And the next will have some arbitrary random values. We should not trust these values. So after that, I'll probably say head arrow val. Okay, head arrow val is equal to, let's say, 10 head arrow next is equal to null. So these two things I write. So what happens after that? The status changes of the box. 10 is here and this part is null. That means it is something like this. Null is essentially represented by a grounding. Sometimes it is notified by this grounding, or it is written null. Okay. So this kind of structure is created. Suppose you want to add another box. Okay. Temp. Okay, so what you do, you create another box temp like this. Just like head, you create a box, another box temp. So here I say head, I will say temp. Okay, then this thing should be just comma, and this is semicolon. So I will create another thing called temp. So this is head, this is temp, this is temp, and the next is null. Okay, so what after that? So this is my temp. So suppose that after that I want to create a list of these nodes, a linked list of these nodes. So what I do, I just say my head arrow next is equal to 10. As soon as I execute this or write this code, what happens? This arrow changes. This arrow here changes. So this as if points to this. It becomes effectively a list like this. A head first is 10, then points to another box where the value is 20 and the next is now. Okay, so it becomes like this. Okay, temp you essentially forget, or you can remember temp, up to you. Okay, so in this way, if you repeat these steps, then you can essentially create a linked list like this. A very big linked list is possible. Okay. What is head? What is head? Head is essentially a pointer. Okay. We say, if you look at the code, what I wrote, first I created one structure like this, struct node. Okay. In C, there is a structure concept, and in Java also, I believe there is this structure can be defined, but I believe in Java things are more like class. So you will define class, and inside the class you can access these as private or public variables. Okay, and through class pointers. Okay, so you can use the corresponding similar declarations, no problem. But head, as you say, inside the main, I have used this. I have defined what is head like this. Okay, it should be star temp basically. So struct node star, that is the type I am interested in. Okay, struct node star. So what is, if you remember, normally if int represents an integer, but if I write int star type, that means it's a pointer to an integer type. Okay, so I have to write int star x, comma, int star y, something like that. So here also I write struct node star head, comma, temp or start temp. You have to check what is the correct way of declaration. Okay. So head is a pointer to this structure. Okay. I cannot say I want to have a variable of the structure. That is also possible, but normal practice is I maintain the head pointer, and at every node I have the address of the next. Okay. So there are two operations in the common operations in the linked list. Okay. So as I said, in the array, there are some operations. What are the operations in an array? I can access the individual elements of the array by passing through the array indices. Okay, let's just like AI or AJ, something like that. And also I can actually return those values. I can insert values at specific locations of the array. That is what is possible. Or I can actually retrieve the value at a specific location. Now, also I can add something, I can modify something, those operations possible. So just like that, in a linked list also, there is a set of operations. So one common operation is called the insert operation. Okay, so inserting a new value. So in a linked list, remember, just a value cannot be inserted. So whenever you have to insert a node like structure or a box like that. Okay, so inserting at the beginning, that means you will insert a new node at the very beginning of all the nodes. So that is possible. That is an operation. Insert at the end. You want to insert a new node at the very end. That I just showed. So suppose you have only one node list like a head, and then you create a new node temp and you put it at the end of the list. So that is also possible. Then insertion after a specific node. Okay, you can insert after a specific node and insert before a specific node. Okay? That is also possible. Quite like that, you have deletion procedure. So we will deal with each of these procedures. So deletion is possible. Deletion you can do at the beginning, at the end, and also at a specific node. That is, remove a given node from the specific position. Okay. So there are other common operations like traverse, search, length, reversal. All these things are there, and linked list implementation in Java is given here. Okay, so as I said, that it is just data and then node next. Okay, so anyway, let us go and understand what is the basic technique behind this insertion thing, and then it will become more interesting to us. Okay, so let us take this example. Okay, so in this way I can create a list. Okay, I can create a list of multiple elements. Okay, so let's say I have head, I have many elements like this. Okay, this is the head. Head is the first, which is points to the first element, and then it points to the second element, and so on. And there, let there be n elements, n nodes in this list. And n is actually greater than hundreds. It may be possible. There are hundreds of nodes. In fact, as you can see, that list do not need the size to grow. You do not need to give any size. It can grow dynamically. So that is also precisely the reason that you don't need to know, or somehow the length of the list should not be given. It can be determined or computed as and when we need. Okay, so length is not generally given. So now the first operation, as you said, somebody said insert at the beginning. So you have to insert some value at the beginning, so even before head. So what you do, you create a new node called pointed by temp, which has a value part. This is the value part, and this is the address part. Address part, you generally keep it null, okay, or you keep it unchanged. Then what you do, you just write these two operations, these two code you write. You write like temp arrow next, that is my head. See, I do this without changing the current head. So this is my first line, okay, first line, temp arrow next equal to my head. Once I write this, immediately there, this value, I put a link like this. That means the address in the next field of temp contains the head address of the head. And then I do the second step. I change the head equal to temp. That means now I remove the head position here, as if I remove the head position here, and I allow the head variable to also point to temp. Remember, temp variable is still there, but it is no more contributing. It is just an intermediate state, intermediate auxiliary variables, you can say. Okay, I may or may not like. Now actually head and temp are two different variables. They both point to the starting location of that. So this is the way I can insert a new node at the beginning of at the beginning of a linked list. Sorry, at the beginning of a linked list. Okay, like that, I can also insert something at the end of the list. So let's say I do the same thing. So I just erase this part. Okay, and I have this is my head, and this is my temp only, and the next of the is null. It is not pointing to anything. I have properly set temp, and then I want to, the job is slightly different now. I have to insert the element at the end of this list. Remember, end of this list is not at the head. Okay, end, to add at the end of the list, that means this element must be. So let's say I mark this address of the last node as end. Okay, so I essentially need to get this end. I do not know what is end. Okay, so right now in the picture I am saying that let this be the end, but I have to get the value of it from this list. So how do I get that? So I just write that end equal to head. I initially set end to be pointing at the head. Okay, this is my end. Okay, then what I write, while end not equal to null or head, I do slightly different. While end next not equal to null, end is equal to end next. This is the kind of code oftentimes used with some bit of sanity. Why I say sanity? Because some things you need to check. When so suppose it's a single element array, then probably in the first step itself it stops. Okay, like n dot next is not equal to now, this fails, because if it is a single element array, then it just stops there. It just doesn't go, and that is probably required. So if you think it's a long array, then if I repeat this while loop, what happens? The end actually moves, just keeps on hopping. And after the hopping, eventually it comes at the very end of the list. Okay. So once it comes at the very end of the list, then end is essentially not pointing to the head, it is pointing to this location. Okay? This is called end. So to do this thing, to find this end, you need to go or find the end. To find the end, you need actually order n operations, because you need to go one by one, and it is the proportional to the length of the array. Once you go there, then you can write this piece of code, that is end arrow next equal to temp. What is that? End arrow next means now this arrow next, which was grounded, now this arrow is redirected to point to the temp. And what you do? You write temp arrow next, which is probably already null. If you specifically write it, it is null. That means you specifically say that is the end of the list. So now, if you think the element pointed by temp, that is now in the end of the list. So to do the insertion at the end, you need to essentially find a pointer to the end node first. That is the first job. And if the list is not, if the list is non-empty, then it is proportional to find a pointer, that is the address at the last node of the list. It needs some operation like this while loop, and it needs big O of n. As I said, big O of n. N is the length of the list. Okay, so that is to be remembered. Okay, so these are the two cases. One is in inserting at the beginning. We saw inserting at the beginning is easy, constant amount of time, but inserting at the end is not constant, it is linear amount of time. Okay, now inserting somewhere in the middle. Okay, somewhere at the middle or at a specific location. Let's draw it. Let's say I have an array. I'm saying this in an array again and again. This is essentially a linked list. I have a linked list, and it's a very big linked list of n elements. Okay, so this is head. This is head. Now it is said that so there are n elements, n may be very large, 1,000 or 1 lakh maybe. So now the question is insert below. What are the operations of the insert? If you remember, insert was insert after a specific node, insert before a specific node. So if we understand what is the specific node that we are talking about, what do we mean by insert after a specific node or insert before it? So what is that specific node? That specific node is represented by a pointer, basically. Okay, so let's say a specific node, I draw it by a red mark. Specific node is some node here. Okay, some node here, because somewhere in the middle, so it must be something like this, and it must be something like this. This is the specific node. Okay, so what you should know about this specific node? What you should know about this specific, because you have to know the specific node. Now, one possibility is you have to insert before the specific node, or you have to insert after the specific. So let us first look at, let's say the specific node is represented by a pointer called spec. Okay, remember spec must be given. Okay, spec must be given. If spec is not given, then at least the value inside the spec must be unique, must be uniquely determined. So if the spec is given, the problem is easy. If the spec is not given, the value inside the spec node, that is special node, must be given. That is spec.val. That is the element I'm talking about. So if spec.val is not unique, and the list or the set of nodes have multiple copies of the same element, then it will become a problem. Then it will become a problem, because which value, if there are multiple, say, fives, then which node containing 5 you are talking about? Then you have to clearly tell that. Is it the first node containing 5, or is it the second node in the repetition of 5, or is it the third node in the repetition of 5? What exactly you are talking? So that should be clearly stated. So let's get rid of all those problems. We say a spec node. So the first task is insert something after the spec node. Okay, so what I do, the first is inserting after the spec node. So what I do, I create a new node, just like that, using malloc and etc. I create something called temp, and its next is null. Okay, now to insert it after the spec node, I have the spec pointer. So I'll execute this code. I'll execute this piece of code. Spec arrow next. See, if I write spec arrow next is equal to temp, then it will be a problem. Because if I say spec arrow next, then immediately what is going to happen? This link that is currently pointing to the right of spec, that will be lost. And I have no way to remember that. So what I do, I will rather create a temporary variable. Okay? I will have another temporary variable, which is called, say, Z. Let's say Z. I will say Z equal to spec arrow next. I will remember the Z. So what is Z is essentially this thing, Z. Where spec next is pointing, I remember that as Z. Then what I do, I say spec next equal to temp. That essentially changes this link, okay? And it now points to like this. Spec next is my temp. And then I have to set temp next is equal to my set. So once I do that, then what happens? This null changes. Temp next is set to Z. That means it is pointed to here. So this, if you now look at the addresses, it comes up to spec, and after spec it comes to temp, and after temp it goes back to there where earlier spec was pointing probably. So this is what is called inserting after a specific node, spec, given by spec. Okay, so you can say like that, struct, you can define a node like this, struct node, and inside that you can write this. I mean, you can write void star val, you can say. Okay, void star val and struct node star next. So this kind of thing you can do. So this has a long implication. What is that? The value now is not anything specific. Okay, it's of type void star. Okay, so once you have a void star, then you can actually convert it into anything, a pointer to anything. So suppose you want to store integer. So what you do, you have this int val is casted. Casting is done by this, like int star. Okay, this within bracket. Within that you cast val, it becomes an integer type one. If you cast it with say float star, it becomes a floating pointer to a float type. Even it's possible, that can be possible, that if you point to, you can point to something different, which is called, you can even point to some struct, say special node. You define a special node, which is itself a structure or some complicated data type. You can cast that. Yeah. So theoretically, you can do all those things, but you have to be careful. Now let us move on to insertion at the beginning, before. So this is the case, spec node. If you take this picture, and I'm erasing this picture again, editing the picture again, just for something. Let's say I have this arrangement that there is a special node, and now the job is to insert something before the special node, the second operation before the special node. Okay, so how do I do? Remember, to insert something before the special node, I normally I have to come to the node before the special node. Okay. I know the special node, but I do not know what is the address of the special node. So I have to come to the node which is just sitting before the special node. See, from the special node, there is no direct way, one hop way to reach the node before special node, because the links are one directional and direction is towards the right. So probably using because it does not have. So later when we'll study, it does not tell how to go back. It only tells how to go forward. Okay. So what you can do is you can only go to the right side. You cannot come to the left side. Okay. So how to do that? So you need to come here. You need to come at this location. So how to do that? You probably do like this. Let's say I say Z equal to head, while Z not equal to spec. No, not Z not equal, Z next. While Z next not equal to spec, you increase Z. And how you increase Z? You Z equal to Z next. So initially the idea is you set Z here at the very beginning, and until Z next not equal to special node, you just hop Z. So first it comes here, then probably it comes here, and in this way you come here. That is now Z. So after this while loop, you come to the node just sitting before the special. Okay. Now suppose you create another node temp like this earlier code, you have this temp. Okay. So you have this temp node, temp variable pointing to a new node. Then probably you do this. See, you have to remember, you now remember Z, Z next is automatically spec, and you just need to insert something after Z and before spec. That is your job. So what you do, and that is the temp. So what you do, you just write Z next is equal to temp. So if that is done, then what will happen? Z next will be temp. So this is my temp. So Z next. So as if it will do like this. Z next is temp. So Z next is temp. So this will point to this. And after that, what you will do? Temp next to spec. Okay. So you write temp next is equal to spec. So if you execute these two lines of code, then temp next is equal to spec. You point like this. Okay. So if you do like this kind of arrangement, then it obviously comes that some new node temp is placed before the special node. So we have discussed both the cases where this a node is placed, a new node is placed right after a specific node, which is given by pointer spec, or it is before or after that special node. Okay. And in both the cases, it may take actually linear amount of time, big O of n amount of time, because you need to search. You need to search. Okay. So once so in this case, if you have any questions, you can tell me. But I just give you a small quiz, kind of small tricky question, that insertion after a spec, it is done in constant time, because I know spec definitely, and after spec I can insert in constant amount of time. In constant, I mean 1, 2, 3 spec, constant amount of spec. But if you have to insert before spec, then probably you do not know the before address, and the before address in a singly linked list like this, you do not know. So you have to come to that before address by hopping from head, and that number of hopping may be as large as the proportional to the number of elements. So you may require linear number of elements. But a natural question is, can you insert before special node in O1 time? So the question is, can you insert before spec node in big O of 1 time, constant time? The question is this: can you insert before spec in constant time? Z next equal to temp, yeah, and temp next equal to spec. Yes, yes. So that is the way I insert before. But see, when somebody will say, okay, compute how much time you spend to do this insertion before the special node, you will probably say that I need, if you say constant time, it will be wrong. You have to say I'll take proportional to the size of the array, size of the list, because you need to get to Z actually from the head, because without that Z is not given. Are we doing any assignment or project in C? Probably not, but I don't know there is anything, but I will ask you to do these things in Java. Then in Java also it is doable. Some exercises are there, some in the in the notes, some exercises will also be there. So I believe you can do that in Java. It is doable. Okay, question is this. Let me go back to the question. Question is this, that if you remember inserting after the spec node, this picture is probably not showing properly because that picture is erased, overwritten. So inserting after the spec node, spec is a special node in the list. Okay. Inserting after the spec node requires constant amount of time. But inserting before the spec node requires linear amount of time. Okay. Now the question is of this form. Can I insert before the spec node in constant amount of time? Okay. That is a little trick. That is a little trick. It may be doable, but you have to understand the trick.
Let us start with the implementation of linked list. This was the implementation of linked list. Yeah, so we have our list, we have our node implementation over here. That node contains two things. This is your node. Node contains two things. First is int data over here and node next. Okay, the thing which will be pointing towards the next node. Okay, and this is just, you can say, a constructor which is just initializing the values, which will taking the data and initializing it. That's it, nothing else. Then next is a type of node. Next is a type of, you can say, object. Next is a type of a variable which points towards the next of the next node, which points towards the next node. Okay, since both are of type nodes, that is why. Okay, address of the next node. Okay, address of the next node. Okay, two nodes are there. Address of this node will be stored over here. Okay, address of this node. Okay, let's say address of this node is A13C. So that will be stored over here. Okay, something like that. We didn't give address. We will be giving that. It is for now. This representation is only for the node. How node is created. Okay, a single node is created. Okay, not of linked list, of just a node. Okay, so in node there are two things. That is, first is data. Okay, we have not even given data yet, right? We are just telling what will be over here. First is data, other is node next, which will be pointing towards the next node. Okay, that's it. Now, if we talk about node is a keyword to declare nodes, node is not a declare. You can call it node, you can call it ABC, anything you want. Node is not a keyword, it is just a class name. Okay, with the help of this class name, you create this thing. With the help of this class name only, you create this thing. Okay, so in order for this pointer to point over here, you need an object of this node only, right? Are you getting my point? With the help of this node, you create this. With the help of this node, you create this. To point this to this, you need an object of this node only. So node next. That is why you write over here node next. Can we write next dot data? Yes, we have that concept. Head dot data or next dot data. On which node we currently are on, we can print its data. Yes, I will be coming to that option, that thing also, Ash. We don't want, it can be public, but the thing is we don't want our node to be directly accessible. Okay, node should not be directly accessible. It should be accessible with the help of linked list only, or with the help of methods. So that is why we have made it private. When you will create a node, right? Okay, node equal to new node. In the constructor, you will pass a value, let's say 30. Okay, node new node will create a node like this, and you will pass a value 30. That 30 will, and that will be initialized. Okay, and it will be put down in the data over here. Okay, and because there is no need of next over here, you can write next also, but there is no need. Okay, earlier I used that, but there is no need, because next we are using in the methods only directly above. You will get to know as we move to the methods of the linked list. Like how a node is made. How a node is made. Node is made with the help of two things. That is data and next part. Right? Private node next, as I have said, next is the part which point towards the next node. The you can say next points towards the next node. It is a reference variable which points towards the next node. It is made private so that it is not directly accessible outside the class. Okay. Now a linked list is made with the help of nodes, right? A linked list is made with the help of nodes. Am I right or no, wrong? Connection of nodes. Where does last node points towards? Okay, the next of the last node points towards null. Okay, next of the last node point towards null. To start, you can say this, the next of this point towards this, next of this point towards this, next of this points towards this, and that is how we are connected, right? So how do we know from where we are starting? Where is the starting of this? Starting of this is from head. Okay. Head is, you can say, a type of, you can say next point towards, next is a memory location, right? Next point towards the next memory location. This point towards the next memory location. This point towards next memory location. So head is kind of that memory location only without the data part, which point towards the very first node. Head point towards the next, I can say very first node. Head points towards the very first node. Okay. So this is how a linked list is. Linked list is the first node is head. No, first node is not head. First node is not head. First node is this one. Okay. A pointer pointing towards the first node, a variable pointing towards the first node is called as head. It does not have a data part. It is just, you can say, memory location which point towards this one. Head will not have any data. Okay. Data part is not there in head. Okay. It is just a memory location. It is not even a node. For a thing to be called as a node, it has to has a next part or a data part. Okay. Head does not have a data part. Okay. So it is not called as a node. It is just a reference variable which points towards the first node. Okay. So a node contains two things: data next, data next, data next. A linked list is made with the help of nodes and a head and tail of the linked list is pointing towards null, and it also has a variable called as size. Okay, of type integer, right? Of type integer. This is not compulsory, but it is good to write int size also. Okay, to check how many nodes are there in this. In this linked list. Okay, As you add a node to it, you can say that size plus plus. You can say size plus plus. As you delete, you can write size minus minus. Okay. I hope this is clear. Talking about the concept of size. Size concept is nothing. See, in linked list, we declare a variable called as size, int size. Okay. As you can say, we declare it that size of the linked list initially is 0. Okay. As soon as a node is created, you update the size of that integer by adding size plus plus equal to 1. As soon as you create another node, attach it, you write size plus plus, it is equal to 2. Another node, size equal to 3. Okay, you delete this, you write size minus minus, so it is again equal to 2. Okay, that is just an integer. You update so that you can know how many values are there in your linked list, nothing else. Okay, so we have declared one thing over here, that is int size. We have made one class linked list. Inside this class only we have made a node class. Okay, a class within a class. Now int size, we have declared one size. Initially it is set to 0 only. Now public node head, there was head also, right? Two things were there inside a linked list. One was head. Head, you can say, points towards first memory location, right? First node. So it will also be of type node. It will also be of type node, right? Next is of type node. This will also be of type node only. Node only, right? Node head. And it will be pointing towards the first thing. Right now it is pointing towards null because there is no value inside. There is no, I can say, node created. Okay, as soon as a node is created, it will be pointing towards it. Okay. Okay. Now the first method which we are going to create is called as add start. Add start. Okay. Add start, you can say, in a way you can say that assume that there is already a linked list. Assume that there is already a linked list. Okay, for now assume that there is already a linked list and head is pointing towards the very first linked list. Okay, it is like this. Okay, now you have to add a node towards the start of the linked list over here so that it will be pointing towards like this. Okay, you have to do that. How will you do that? Just tell me. Forget the code, although Rishit's code is right. Yeah, he has created node code. How will you write the code to forget the code, sorry. What should be the implementation? What should be the implementation if I have to add a node to the start of the linked list? A linked list is already there. If I have to add it to the start, what should I do? Tell me in plain English. What should I do? Point head to that node. Okay, see, if I point head towards this node, okay, if I point head towards this node, that is a problem. We should not do that first. That should be our second step. If I point head towards this node, that means head is not pointing towards here now. Head is pointing over here. This is not yet pointing over here. And we do not know where this node is because head was pointing towards the first node. This should point towards over here, but we do not know where this is now. And this whole list is lost. This whole list is not lost. Head is pointing towards this. A new list is created with head over here, this over here, but we do not have an idea where this list is. Right? Are you guys getting my point? Why we should not point head towards a new node first? We have a new node over here. Okay. So we should not point this head towards this node at the very first step. At the very first step, because head only tells from where our list is starting. If head points towards here, then we do not know from where our previous list was starting. Okay, we do not have a connection over here. Head is pointing towards here. Now we do not know where this list is. We do not have an idea where this list is. Okay, head should have been pointing over here. Now how do I know where this list is? So how will I point this point towards over here? Okay, I have no idea now. So this is wrong. This is wrong. Instead, what we should be doing? What we should be doing is we should point the next part of this. We should point the next part of this. See, head is pointing towards here. We can say that the next part of our new node, which we created, it should be pointing towards here. Okay, head was pointing over here. So we can say that the new node which we created, its next part should point towards head. The new node which we created, its next part should be pointing towards head. Head is already pointing towards here. So we can say that this new list will also be pointing towards head. Next part of the new node will be pointing towards head. Head is already pointing towards here. Okay. After that, both the things are pointing towards the first node. After that, we can say that head should point towards the new node. Now, same thing is done over here. We created a new node. Okay. To insert at the very start, there is already a linked list. Okay. To add at the starting of this linked list, first we need a node. So we create a new node. Node equal to new node and some data inside it. Okay. Some data inside it which will be going at the down and initializing itself. Okay. Right. So we created a new node. New node has two things, that is next part and the data part. Okay. Now we are saying that node.next. This is the node which we created, new node. Its next part, meaning this part, should be pointing towards head. When I say it should be pointing towards head, where is head pointing? Yeah, it is pointing towards the first node. So if you point next part, node.next parts towards the head, you make the value of this equal to head. You make next part equal to head, and head was already pointing over here. That means this will also point towards the first node. Am I right or wrong? This will be like this. Okay. Now we can say that head you should not point towards this. You should update yourself, and head you should point towards the node now. The node which we created. So head will be pointing over here, and we have a structure. This is lost. So head, first node, second node, third node, fourth node, and it is pointing towards. Part is only the memory location. This whole node contains two things, next part and the data part. This whole thing is called as node. Head only contains the memory location, which is equal to next part. So we can say that address of the first node goes to next point of the new node after do node next is equal to head. Yes, we can say that this. When we write node next equal to head, that means this part over here points towards the first node. Okay, this part points towards the first node, original first node. Okay, so now next will carry the address of the previous head node. So this is how you can say add start is implemented. Okay, now let us actually see how this is working. Okay, I will be using a method which I have not. We make a linked list, ll, name it as list and equal to new linked list. Okay, ll, this was the class which we created, right? Ll. So we create a linked list equal to new linked list, and we call the method list dot add start. We created add start only, right? So add start we write, and we write, let's say 10. Then list dot add start again 20. Okay, let me just copy this. We have 30, we have 40, and we have 50. So how will this be printed? It will be like first a new node will be created. Okay, if there is no list, a new node will be created like this. Okay, then what we are doing is add start. It will consider this as the node and add start. If this will have value 10, and it will be like, okay, first a node will be created like this. This points towards null. Okay, it will have 10 inside it. Okay, then 20 node we have created. Okay, its value is 20, and this next part points towards this node. Okay, then a new node will be created like this with 30 inside this, value 30, and next part will be pointing towards, next part will have memory address of this node. Next part will have the memory address of this node. Then same with the case of 40 and 50. Okay, we have add start. Every new node which is being created will be added at the start, not after, not after this, how we usually go. No, it is added before. Okay, so if I have to print this, I have not taught you how to print it yet, but I will be teaching you just for the representation. I am just using that is list dot display. Display method, I will be telling you how display method is created. Head dot display, what will be, we will be having, yeah, 50, 40, 30, 20, and 10. Okay, 50 at the starting, then 40, then 30, then 20, then 10. Okay, if we want to add at the opposite, then we will be using add end. We will have to create a method. For the same, to add at the end of the list instead of adding at the start of the list. Okay, if we want to add at the middle also, then also we will have to create a method add middle. If you want to add at a particular, I can say particular index value. We want the index value, and then with the help of that, we can add in the middle. Okay, now the method which we are going to learn, yeah, delete start. Anybody has an idea how we can implement delete start? I want the answer in plain English only. Okay, plain English with technical terms, no coding. Plain English with technical terms, because if you are able to understand plain English, then coding is just matter of days. Today you are not able to understand the coding part. Tomorrow you will be able to understand the coding part. That is just matter of practice. Main thing is, you can say, logic. How you have to write the logic. Okay. Okay, delete first node. Yes, how will you delete first node, Rishabh? Move head to null. Reverse process of adding. How? Assign head to first node next. Yes, Yakun, right? Move head to next. Yes, Shubham, right? Delete start is the method which, with the help of which we will delete the very first node. Okay, point head to next. Size minus minus. Size minus minus will automatically be happening, but how to actually delete the first node? Move head to null. See, you move head to null. Was it? And if you move head to null, then whole list is lost. We don't want that. We only want this to be not there. Okay, this thing should be deleted. How do we do that? This next part is there. Okay, this next part has the memory address. Of which node? Second node, right? Second node. This next part has the memory address of which node? Second node, right? So we can say that if head is not equal to null, meaning if there is a list, okay, yes, if head is not equal to null, meaning there is something in the list. Okay, the list is not blank. Then what we will do, head is pointing towards the first node, right? The very first node. It should point towards the second node. It should have the memory location of the second node. It should have the memory location of the second node. And how we can get the memory location of the second node? Memory location of the second node is available in the next part of the first node. So we can say that head should have head dot next. Head dot next. Head is pointing towards this. Its next part this. Okay, which is this. So head should point towards the next node. If head is pointing towards this node, this whole list is gone. Okay, this part is gone now. Okay, that means head starts from, like, wherever head is pointing, that is the start of the list. So start of the list is from second node now, not from the first node. Okay, so first is removed. Instead of pointing towards the, it should point towards the second node instead of to the first node. And where is the location of the second node? In the next part. So head is equal to head dot next is point only for node. Node dot head dot next also you can write. Node dot next also you can write. Okay, head is pointing towards this node only, right? So this node dot next, it is, we can say, same meaning is same only. Okay, head is pointing towards this first node only. So first node dot next, head dot next, is like meaning of that is the same. This node dot next or head dot next. Okay, let us actually implement this thing also. Let us delete at the start. It was delete start, right? So list dot delete start. List dot. So we have wrote the method delete start. Delete start will delete which of these? Delete start will delete which of these? Yes, it will delete 50, right? Because 50 is at the very starting, right? 50 is at the very starting. Earlier it was 10, then 20, then 30, then 40, then 50. 50 is at the very starting, then followed by 40, 30, 20, and 10. So if I write delete start, it will delete the 50 part, and we will have 40, 30, 20, and 10. I hope this is clear. Okay, so delete start and add start we have learned. Okay, delete start and add start we have learned. Then first of all, before going to delete end or add end, but where we will give head location in the code. That is just the implementation, right? Display I will be telling you as. Are you saying like that? What will happen? Yeah, nothing is there, right? It deleted it. It deleted it. Now, let's understand that. So let us understand how is this display method. I've been calling display method a lot. How is this display method created? How is this display method created? Okay, which will display all the things. Okay, so in order for us to write display method, let's say there is a list like this. So this is one list, and what we have been asked to print the entire list. Okay, print the entire list. Okay, if you write where is head pointing, I want everybody to answer now. Where is head pointing? Where is head pointing? It is pointing towards the very first, right? It is pointing towards very first. That is right. You are right. So if it is pointing towards here, if I write head dot data, okay, let's give data also. Let's say 1, 2, 3, 4. If I write head will point towards this node dot data, what output will I be getting? What output will I be getting? If I write head dot data, head points towards this node dot data. This node dot data will give you what? Head dot data will give you the value of that node, right? Now its next part, that is this thing, have the memory location of this block, right? Next part has the memory location this has the memory location of this block, this has the memory location of this block, and it is pointing towards null, right? If I say that originally head is pointing towards here, and we write head dot data and we get the value 1. Okay. If I write head is equal to head dot next, head is equal to head dot next, where will it be pointing? Where will head be pointing towards now? Where will head be pointing towards now? Head dot next, meaning this part, meaning it will be pointing over here, meaning it will be pointing towards here, right? Right. So again, if you write head dot next, again, if you write head dot next, what value will you be getting? Head dot data. First you write head is equal to head dot next, then you write head dot data, print head dot data, then what will you be getting? Value of second node, right? Value of second node you will be getting. Then again if I say head is equal to head dot next, okay, then I write head dot data, then what will I be getting? So one thing we can all agree on is that if I write head is equal to head dot next, it will be pointing towards the next node, right? We will move one node further, right? Head is equal to head dot next, we move one node ahead, line by line. Okay. See, the problem with this is if I write while head is not equal to null, last node is pointing towards null, right? So if I write while head is not equal to null, we print head dot data, and then we move head is equal to head dot next, we move one process, like one node ahead. Okay, so if we have 3 nodes, let's say this is pointing towards null, this is head. What we are saying is until the value of head is not equal to null, we are printing data, then we are moving one ahead, one process ahead, one node ahead. Okay. So head equal to head dot next, we move one node ahead, then again we move one node ahead, then again we move one node ahead, we have null. So we will break out of loop and it will print all the data. That you will lose the entire list with this, right? We have what we used to delete, how we used to delete a list, right? We point heads towards here, right? And we lose this thing, right? And we only have this thing left, right? So what we can do is never change the position of your head until or unless you want to delete an element. Do not change the position of head. It will create a chaos. If you want to iterate a list, you make another variable. Temp, and inside this temp, you have the value of head. Okay. Inside this temp, you have the value of head. Then temp is also pointing towards here, right? And you move the temp all along and print the data. Head will already be pointing over here only, but you can move here, print its data, move here with the help of temp, print its data, move here, print its data. Clear? Create another variable whose value will be equal to head, and with the help of that, you print the data. Okay, this is how. Okay, this is the code. Let me just explain the code one more time. Temp equal to temp dot next. Instead of head equal to head dot next, it will be temp equal to temp dot next. Okay, temp value is equal to head only. Okay, you create node temp. Yeah, you create another node. You do not create another node. You create a reference variable. Okay, a memory location, just like head. okay, and give its value equal to head. So it will be temp dot data, right? And we say that while value of temp is not equal to null, while the value of temp is not equal to null, okay, we print temp dot data, and we move one node ahead. We move one node ahead. Okay, this is how. Is this clear to everyone? How to display a list? How to display a list? I mean, head dot data will head dot next will also work, but that will delete the list after one printing. Okay, and we don't want that. So this is clear. Now let us understand. Okay, and this is head. Yeah, my question is now, how do you delete the last node? Okay, first, how to add at the end of the list, how to add at the end of the list. Okay, you want to create another node and how to add it to the end of the list. How do you do that? Just in pure English, I want the answer. Okay, the question is, how do you add at the end of the list? Earlier we added at the starting of the list. How do you add at the end of the list? Okay, how do you add a node to the end of the list? New node points towards null. If new node points towards null, okay, what's next? New node is already pointing towards null. New node already points towards null only. Okay, no need to write that. Next value of last node, and now add address of the last node. Okay, and how do we reach the last node? How do we reach the last node? You all are saying is we should be pointing the next of this which was pointing towards null. Instead we should point it towards the new node. How do we do that? Yes, give memory location of last node's next part others to new node, right? Okay, can anybody write a code for this? Sample method of this. How the method will be looking like? Right, Yakun has written the, I think the last line is a little bit wrong, Shahina. Check that thing. And please, like, beforehand tell me what is current. Okay, I get what is current. That is temp only. So tell me before that. Okay, where is it? Yeah, add end. Where is that method? Yeah, add end method is over here. Okay, add end method says if head is null, add head is null. Okay, that means there is no list. In that case, create a list. Okay, if there is no list, that meaning you will not be able to add at the end of something. That means create a list at that point. Head is equal to node. Okay, whatever the new node has been created, head will be pointing towards that. That is the very first node. But that is not the case. We are assuming that there is already a list created and we have to add at the end of it. So what we will do, first we will obviously we have to go to last of the list. We have to traverse right to the last. How will we do that without losing our original list? We will create a temp. Right? We will create a temp and give its value as head. And with the help of temp only, we will traverse. Okay. We are saying that if there is nothing, that means there is no list. Okay. And we want to add at the end of the list. What we will do? Instead of adding at the end of the list, that means we are creating the list. In that case, add end will do nothing but create a list. That means a node has been created by writing node equal to new node. Okay. And that that head will be pointing towards the new node now. Okay, node will be created, or list will be created now. Okay, in that case, if there was nothing in the list, but now the case is when there is a list already, okay, When there is already a list and we have to add at the end of it, we have to traverse to the last element. We have to traverse to the last element. Okay. And we have to say that, see, if we have to traverse, we cannot traverse with the help of head. We cannot traverse with the help of head. We need a temporary variable. We need a temporary variable so that the list is not deleted. So no temp equal to head we have written. And then what we are doing? While temp dot next, this is not equal to null. 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 This is equal to null actually. We will traverse the list. While temp dot next is not equal to null, we move one step ahead. We move one node ahead. Okay. And as soon as we, after the while loop, temp dot next is pointing towards null, what we will do, we will say that temp dot next part, that is over here, it should point towards the new node which we created. Instead of pointing towards null, it should point towards the new node which we created. So it will be joined. Okay. So traverse the list, and where you get a null, its next part should be pointing towards the new node which you created. We don't need to add temp list to our list. Okay. Temp is just a variable which is used to traverse, because we cannot move ahead. Okay. So we create another head. Called it as temp, and its value is equal to head. It is pointing towards here. Its next, we write temp dot next will move here. Okay. We are moving the value of temp. The list is same only. See, with the help of temp dot next, we have reached last. Right? Temp is equal to temp dot next. We have reached last. Okay. This is our new node. Okay. Forget this. We are saying that temp dot next is this part. Temp dot next is equal to node, the new node which you created. So instead of pointing it towards the null, last node point towards null, right? Instead of pointing it towards the null, it will point towards the new node now. And new node will point towards null. We're not writing new node equal to null, because that is obviously, when you're creating a new node, it automatically points toward null only. So that is how you're doing it. You can write size plus plus. Obviously, when you add an element, you write size plus plus. Now, one last thing. How do you, wait a minute. Okay. Now the question is very important. How do you delete the element at the last? How do you delete an element at the last? Make third node next null. How do you go to third node? Nilesh, how do you go to third node? How can you tell? I'm telling you to delete the last element. Okay. Traverse until node next is null. We have traversed over here. No. That will point head towards over here, right, Anshu? We don't want that. One thing, instead, what we should do is we should point this to null. If this is pointed towards null, that means this is lost. Okay. But now my question is, how do we traverse only till here and not till here? How do you traverse till only here, not till here? Okay. Yes. Sukhpal has given the correct answer. Create extra buffer to null. Okay. If we write, okay, temp dot next is not equal to null, while temp dot next points towards the next, and next dot next points towards this. Okay. So if you write temp dot next is not equal to null. It will stop over here only because temp.next is pointing towards null, right? Temp.next is pointing towards null. So it will stop over here. If you write temp.next to next, while it is not pointing towards null, you move ahead. You move ahead and you move ahead. Okay. Let me show you the code. Okay. While temp.next is not equal to null. Yes, obviously it will work. It will work, Priya. While temp.next is not equal to null. In this case, our loop will break at this second last element only. It will traverse till second last element only. After that, you write that second last elements next part equal to null. Second last elements next part is equal to null. And we are done. We are done. Is this clear? Is this clear? Instead of writing temp.next, we write temp.next. Okay. In that case, we will move until the second last element only. Why this? That is not equal to. Not. This is not simple. Not equal to null. Okay. Until this is not equal to null, we move one step ahead. Okay. Then last node will automatically be discarded, right? But if the list is this is not for finding the middle element. This is for deleting the last element. Last, not the middle one. For middle, we need to know the index value. Okay, then we will be using a for loop. So, okay, let us actually implement these things which we have done till now. Add start. Okay, after add start is a little bit confusing. Let's add at the end. Okay, we have had one start. Let us actually implement these things. So list dot add end and we write 20, list dot add end 30 and list dot add end 40. Let's make a little big list. Okay. Okay. So it will display 10, 20, 30, 40, 50, 60, 70. Okay, 10, 20, 30, 40, 50, 60, 70. Let us implement some of the things. If we write list dot delete start, okay, then it will delete the starting element. What is the starting element? Okay, so the answer will be 20, 30. Okay, after this, if I write list dot delete end, what will be deleted? Right, 70 will be deleted and 70 will not be there in the list now. 20, 30, 40, 50, 60. Anything else with which we did? I don't think, right? Okay. This is the implementation. Now is the case for adding in the middle and deleting in the middle, right? Adding in the middle and deleting in the middle. Try to delete 50. We have not yet implemented the method to delete any middle element. 50 is in the middle, right? To delete 50, we will have to delete 70, 60 and then 50 or 10, 20. To delete middle, I'm telling you the logic. I'm telling you the logic to delete the middle element. Okay, and I will be giving you the code also. So first we will understand how to add in the middle. Okay, we have to add in the middle. Let's say this is 0, 1, 2, and 3. Okay, I want to add over here. Okay, so first what we'll need, we are adding an element, so we will need to create a list. Where we will create by node equal to new node, right? With the help of that, we will be creating a list. Node equal to new node, and we will be creating a list. That is fine. Then what we want is See, if we want to add in the middle, find middle the add. I don't understand your question, Shubham. If we traverse, yeah. See, it is not about traversal list divided by 2. To add in the middle, we need two things. First is the index. Okay. First is index. At what index you want to add? When we deleted 70, it was at the last. We added at the start, like this, 20. And then we write add end. At the end of 20. Over here, sorry, we added at the start 10. Then at the end, we added 20. And at the end, we wrote 30. At the end, we wrote 40. At the end, we wrote 50, 60, and 70. If we write add end, 70 will be deleted. If we write delete, sorry, if we write delete end, 70 will be deleted. If we write delete start, 10 will be deleted. You getting my point? It is not like we need size or anything like that. Okay, nothing like that is needed. We need two things. Okay, that is index value. We need index value. Okay, at what index you want to add, and we want the data, that is the node only. Okay, at what index you want to add? Let's say you want to add at index number 1 or index number 2 over here after index number 2. Let's go for index number 2. Okay, we want to add at index number 2. What we will do with the help of for loop, traverse till here, till 1 index minus 1, traverse till here. With the help of for loop, we can traverse, right? Temp is equal to temp dot next, number of loop till for loop is moving, right? Till index minus 1, move till here. Okay, till index minus 1. So move till here, 1 index minus 1. Then the next part of this, what we were doing, we were deleting or we were adding? We were adding, right? Right. So I thought we were deleting. We cannot do this. We cannot just say that the next part of this should point towards here. Because if we say that, and then our data is lost. Okay, the rest of the list is lost, right? We cannot do that. So what we can do, right? Store the memory of index plus 1. Okay, you're saying store the memory of index plus 1. That is already over here, right? That is already over here. Okay, so we can say that this next is pointing towards here, right? Here, right? This next is pointing over here. This has the memory address over here. Okay, so we can say that new node's next part should also point towards here, which is equal to the node which you are currently on, its next part, right? In that way, both this and this will point towards this node. Am I right? If you say new node's next part is equal to the node which we are currently on, that's next part. Okay, yeah, new node's next part is equal to index node which we are on, that's next part. Then both will point toward here, both will point towards over here, right? And then you can say that the index node which you are currently on, that's value is equal to the new node. Is this clear? First, it should join over here, then this should join over here. We're doing nothing. We are traversing till here. Till here. And we know that its next part points towards here. So what we do is, we make this next part equal to this. So that both of them will be pointing towards this one. Okay, both of them are pointing towards this one. And then we may say that the next part of this point towards the new node. So can't we do it by using temp? We will be using temp, right? With the help of temp, we will be moving. How are you saying we should be doing with the help of temp? Temp to new node, then new node to rest node. Temp to new node. Okay. Okay. There is a problem with that logic. Okay. You are saying that, right. For deleting, you are right. See, so you are saying that this next part, temp, should point towards new node, right? You are saying that it should point towards here. Temp should point toward new nodes. That is what you wrote, right? Say temp 1. Okay, temp 1. What is inside that? New variable. Okay, what is its value? First we point this over here, and then we point this over here without needing of this thing. I show you the code if I have. Where is it? Delete middle, add middle. It should be there, right? Add middle, right? Okay, exactly what we are doing. Node dot next is equal to temp dot next. Node dot next part is equal to temp dot next part, and then temp dot next is equal to node. Okay, exactly what we are doing. Okay, the question is, how do you delete any any element in the middle? In the middle again, it means any element apart from first and last. How do you delete that? How do you delete that? Let's say you want to delete this thing. You want to delete this thing. How will you delete it? Or you want to delete. Let's say you want to delete. How will you delete? Okay, this one. Let's say you want to delete this one, which we are on currently right now. Stop over here. Stop over here. Stop over here and point its next value. Okay, point its next value like this. Next, point its next value to next dot next. That will be like temp dot next is equal to temp dot next dot next. So instead of connecting over here, we will write temp dot next is equal to temp dot next dot next. So this will be lost and it will be pointing over here. So this will be eventually deleted. So t dot next dot next. Okay. In that way, this will be deleted. Point temps dot next value to next dot next. Simple, right? Stop one value less and point temp dot next dot next. I was telling you a little bit more about, okay, the thing which we did, okay, the thing which we are doing right now, this is called a singly linked list. What it is called as singly linked list. Okay, singly linked list. There is data part and next part. Data next, data next, data next, right? Last point towards null. Okay. Now there is thing called as doubly linked list. Doubly linked list. In doubly linked list, it is actually like this. Along with data and the next part, it has something called as previous part also. Previous. Okay. So previous part will be pointing towards this, and next part will be pointing towards this. Previous will be pointing towards this, next will be pointing towards this. Its next is pointing towards null, but previous is pointing towards this. The first list, previous part is pointing towards null. Got it? This is called as doubly linked list. Doubly linked list. Okay. It has previous and next. Okay. So it is easier to traverse in both the directions. Head is pointing towards the first. Head is obviously like always there. So it is easier to, I can say, move here and there. Okay. In both the directions. It is easier to traverse in both the directions in this. Head does not point towards null. Previous point towards null. And next point towards the next node. Okay. This is called as doubly linked list. Called as doubly linked list. This is the theoretical part. One more type of list is there. In this type of list, it can be singly linked list, it can be doubly linked list. Okay. Choice is yours. There is head also. In this is pointing over here, this is pointing over here, this is pointing over here. Okay. The last usually points towards null, right? In this is called as circular linked list. Circular linked list. What it is called as circular linked list. In this, last does not point towards null. Last does not point towards null. Last next part points towards the first node, making it cycle. Okay, it is called as circular linked list. What is called as circular linked list? It is important for easier insertion and deletion. Both last node, next, and head point towards first node. No, head is there. Head is there. Okay, this is called a circular linked list. Now, one question I was telling you about, right? One question that we had to do. That question is actually very similar. The question is, let's say, yeah, this is the question. See, what does it say? It says that you have to tell whether there is a cycle in linked list or not. Okay, what is the meaning of cycle? When this is the first link, first node, second node, third node, fourth node, and fourth node is pointing towards the second node. Fourth node is pointing towards the second node. That means there is a cycle. That means there is a cycle, right? Need to check last node next. Okay, in that case, if you have, let's say, something like this: 0, 1, 2, 3, 4. Okay, and this is like this. Cycle is like this. Okay, third nodes next point towards first. In this case, you will not be even able to go to the fourth node next, right? How? You will say temp.next will point towards here, temp.next will point towards here, temp.next will point towards here. Then if you will try to point towards next, it will point again towards 1. Then again 2, 3, then again to 1. Then again to 2, 3, again to 1. You will be stuck in an infinite loop, right? You will not be able to get to the last node if there is a cycle in between. Okay, if let's say second last is pointing towards, how will you get to the last node then? How will you do that? We have been given one head. Okay, instead of node, they have taken here a list node. List node, same thing. Okay, yeah, fast and slow approach is also right, Shubham. Okay, but that is an advanced algorithm part. Okay, I think it is called as turtle and something algorithm, right? So what my approach was that first take a variable called as boolean cycle is equal to false, and everybody here has done the hash set or hash map, right? Hash map or hash set, hash map, or hash set, any one thing, only hash map. Okay, the solution of this can be now what we will do. First, we are on this node. Okay, and let's create a list. Let's create a list instead of hash set. We are creating a, let's say, array list. We are creating a what? An array list. Okay, there is one array list. Okay, it is blank for now. What we can do is, when we are on this, this array list is of type node. Okay, it will contain node values. Okay, addresses. It will contain address. Okay, list node or node type. When you are on this, check in the list whether you can say it is present or not. You can say, okay, you are using temp. Okay, temp is over here. Check whether this is already present in the list or not. Okay, check whether this is there in the list. Okay, if it is there in the list, then we say that there is a cycle. Else we add the address of this into the list. Okay, we add the address of this into the list. Then we do same for this one. The address of this is there in the list. No, it is not there. We add it to list. Okay, then we do same for this and we add, same for this and we add. Okay, so the address of the next part, address of this part is actually there in the list, right? Address of the next part is already there in the list, so it will actually say false. You check that, then means it's a cycle. Yes, means there is a cycle. If the address is already present in our list, meaning there is a cycle, meaning we are not able to move ahead. We will check with the addresses, right? We will check with the addresses, okay, not with the values. We will check with the addresses, okay. You are creating a hash set which will contain the value. Hash set is nothing like it is just like a list. It is just like a list only, okay, which will contain list node. While temp is not equal to null, meaning until we have not till the last value, you are saying that if set does not contain the temp value, if set does not contain the temp value, we add the temp value and we move one step ahead, okay, and then we move one step ahead. Otherwise, we are saying that cycle is true and we are breaking. I'm using set only here just for this contains method. Set dot contains, because there is no such method like list dot contains. You will have to iterate the whole list, right? You will have to make your own method to iterate through the list. So that is why I have used hash set over here, but you can definitely do it with the help of list. Improvise. Okay.
Okay. What is a stack? Okay, in real world, stack means what will you do? You will stack books on top of another, right? One after another, and you will stack things. Let's say you're stacking things and putting in a carton or a box. Okay, you're putting in a carton or a box and you're stacking things one after another. Now, first I inserted book 1, then book 2, book 3, book 4, book 5, and my carton is filled now. Now, I'm trying to take one of the books out. Can I take book 1 directly? My book 1 lies at the bottom, and then book 2, and then book 3, book 4, and book 5. Now, I'm desperate that I've placed book 2 wrongly inside the carton, and I want to take it out. Can I take book 2 directly from the box? No, you cannot, right? So what is the book which you can take from the box first? I have 4 books, book 1, book 2, book 3, book 4. Okay, I told 5. I'm sorry about it. So 1, 2, 3, 4, 5. So you can only take the last book out, right? So what is it? The one which has entered last is the first one to come out. Correct. So that is called LIFO. Last in and first out. Even though I want book 2, I cannot take it out. It all comes like I will take book 5 first, and then book 4, and then book 3, and only after that you can pick the book 2. So that is stack. Stack is nothing but ordered data, but you can only pick the last inserted item first. Okay, LIFO, last in, first out. Okay, so why do you want stack in the world of programming? Okay, I'll come to that topic later. So let's go through the stack. So what is stack? It is also a data type or a data structure that follows this pattern where whatever you have inserted last is the first one to come out. Okay. Here in the programming also, we need a data structure called stack, which is used widely in every programming thing we are using it, because you push all the functions there and then pop it out. So all your recursion and everything follows it. It is a big topic, but we can go through that later. But this is the thing. See, I was talking about books. Instead of books, let us assume you are putting some numbers. Let's say the marks which a student has got in a particular subject. So 78, 45, 89, 10. So these are the elements. Okay, this is your stack, and you have 78, and then 45, 89, and 10. This being a stack, even though I have inserted 78 first, when I want an element out of this stack, 10 would come out, not the 78. Okay, because it follows last and first out. The item which was put last into this bucket will be the first one to come out. Now let's say I want to push 32. What will happen? You can push 32 on top of 10. Okay. Now this pop says, let's say your stack had an element 66 on top of 10. Now when I'm popping out, what would come? So I want an element out of my stack. So what is the element which comes out of it? It is 66, because 66 was at the top. Now, based on this stacks thing, can you give me some real life examples, one or two? Google history. Yeah, your browser history, right? What do you do? In browser, you will go back, come forward, like you will click the browser's left arrow and right arrow, right? Which says, I want to go back and move forward. How will the browser do that? It puts everything in the stack and it goes rightwards, pops it out, and then goes backwards. So that's what it does. First in, first out. It can also be queue. Undo, redo. This is good example where when you do some typing mistakes, you want to do undo. So how does it all go? It all goes with stack example, right? The previous element which got deleted, you wanted that one, you want to undo the current one. So you put all the changes into your stack, and when you click on undo, the current change comes out. Okay, and then go backwards. So that's what. Okay, now let's move here. So real world example. So as I said, you have a pile of books. So the book you have inserted at the last will be the first one to pick. Okay, similarly, after you pick, the book you inserted first will be the last one to be removed because you are piling it on top of the stack. Okay, now let us go and think how we can implement this stack in them. Okay, there are two types of implementation. You can either implement it using linked list or using array, but the current curriculum focuses more on array. And if time permits, I can give you a walkthrough on how to do it using the linked list. Okay, so now before I go through, now for this stack, what do you think? What all things we want for the stack? Data, okay. You want a container which is a stack, correct? Like a box, carton which holds everything. The box is your array, right? The array is empty. And because we are going to implement array, you need to know the size of the box. If the box is going to fit only 5 elements, I can only put 5 data into it. Correct. So you want to know the size of the array, and you get an empty box, which is an array. And then what you want? You have to put the books, so the data you want, and what else you want. We had to know two operations, which is more important in the stack because whenever you're putting and inserting an element into the stack, that insertion is called push. Okay, because you're pushing the books into the box, right? And the next one is pop. Pop means, okay, I want to take a book out of my box. Let me take it out. So that is called, anything you move out, it is called taking out. Okay, so those are the two main operations which you have to know, which is push and pop. Okay, apart from that, for our convenience, we will check if the stack is empty. Well, now, you know the two operations, right? Now you have a container which is array, right? And inside array, which is your box where you can only put 5 elements into it or whatever n elements, we can generalize it. And then you're putting elements 1, 2, 3, 4, 5. And after that, someone tries to put 6, but your box can hold only 5 books. So what will you do? You will throw an exception. Exception means something error. No, I'm sorry, boss. Yeah, I cannot take your book in because I'm going out of memory. I can only hold 5 elements with me or 5 books with me. Okay. So yeah, you're good. It's just a stack overflow exception. Okay. Now let us go to the implementation. So now you know what are the most important operations in stack, right? Okay. Now, what are the operations in stack? So push, pop. Okay. Some of the operations like top and peek. Okay, I'll let you know what it is. Peek. What do you do? Peek means you are just peeking through someone's window. Like here, we are picking through someone's stack and finding out who's there in the stack. Which means, what will you see? You cannot see what is lying down, right? You can see only the items which is at the top. You cannot take out from the box, but you can just peek in and see what is there inside your container. Correct. So that is called peek operation. You just see what is there and come out. So apart from push pop, you also have a method called peek where you can see what is the element which is at the top of the stack. Okay. Now I want to implement a stack class. What all I need in terms of variables? First thing is you want an element to insert. So data, nav, and we also want the size of the array, correct? So that's what we have. What is an array? We want an array. We want the max size of an array. And what is the index of the top element? Okay, so whenever you are creating an array, stack based out of an array, you should always pass the size of the array. So that is why you are passing the size here. So that is your maximum size, and you are creating an array of the maximum size. Okay, and top is the position. Okay, where you are currently at. So initially you don't have any elements inside your array, so you will put top is -1. Okay, so now you're clear on why do you want all this, correct? And apart from that, so these are the main elements or the variables. And now you have a box, right? Which is your array, stack array, correct? If the stack array is empty, the top will be -1, correct? Which means, let's say I'm trying to take a book or I'm trying to pop out of the stack, but there is no book inside my cartoon or my array is empty. Then what will you do? The top will be equal to -1, which means the stack is empty. So that is why here, while we are dequeuing, not dequeuing. When you are popping the elements out of the stack, you should always check whether there are elements inside the stack. So you are checking whether the top is equal to -1. Okay, and now another thing, I'm trying to insert into an array when my array is already full, or I'm trying to put a box into the carton when it has already run out of capacity. Then you cannot do it, right? You have to throw an exception. So these are the two boundary conditions that you have to be aware of. So that's full. The top is max size -1 because in arrays always starts with index 0. So that is why you check whether top is equal to max size -1. If it is equal, which means it is full and you cannot put elements into it. Okay. Now let us go and see our peak operation, and then we'll go over push and pop. Okay. So you know the boundary conditions, how to check them. Okay, I'm creating a new class, stack using array. Okay, my class needs a method. Needs a stack, right? So let us create a class called stack. And first, what all things you want? You want an array, right? At any point in time, you want to know whether the stack is empty or full or something. So I want to maintain the index. So it is top and max size. And what is the maximum capacity of my array? Correct. Okay, so these are the important variables which we want. We'll put it here. And then after that, now somebody wants to use my stack, correct? So how will they use it? They will use it using my, you can only instantiate a class using constructor. So in the constructor, whenever someone is calling a stack, it should be dynamic enough to create an array of the size specified by the user who is passing the input. So I'm asking the user to give the size of an array, and you will initialize an array of the size which is given by the user, and you will put top is -1, which is the index, how you put check whether the stack is empty or full. And you initialize with -1, which says that the stack is empty. Okay, now these two we have done. And another important thing, what I wanted you to know is, if the stack is empty, you should not be able to pop elements out. And if the stack is full, you should not push the elements to it. So these are the two boundary conditions you have, correct? We'll go to the actual operations before that. So what I'm doing, I want to check whether the stack is empty, because if it is empty, I should not pop the elements out of the stack because it will throw me an exception. So how do I know my stack is empty? I have an index element called top, which is equal to -1. And if it is equal to -1, it says my stack is empty. And the top is always, it is rather than index, it always says the number of elements in the stack. Okay. If the top is maximum size -1, which means it is already full because array starts from 0 and it has all 0 to 4, 0, 1, 2, 3, 4. It already has 5 elements. It is already full. So I cannot push further elements into it. Okay, so these are the two boundary conditions which you have to implement. And apart from that, let's go the simple ones. Okay, go with the simple ones first. Now, let us define it. Okay, we will go because there is a public class called stack using array. I'll create a main method to run this. And here I'm telling I want a stack. So let me initialize stack S and I'm telling them I want a stack of size 5. Okay, this is where we are initializing. So before I initialize and call, I should make this data structure well equipped so that it will perform all the operations and it has all the data structures which I want. Okay. Now, another operation which is nothing but peak. What is peak? Now I have to create a class called stack for someone to use my stack, correct? So for creating a stack based on array data structure, what is the first one I want, which is an array? And next what I want, what is the size of the array, which is the max size? And I want to know at any point in time, what is the size, at what point my elements are there? At what index I've stored my element? Like I have only 2 elements or 3 elements or whatever it is, what is the position? So for that I want top. Okay. Now I have declared these variables. Now, if I'm calling it, I would say I want a stack of size 5. If someone, Yakun or some other friend of mine wanted to call this array, his size is huge, like 100 or 1000. So this is dynamic, right? So the user, whoever is calling this data structure which I'm creating for them, will call this class by passing the size they want of the stack. Okay. So once they pass the size, I will set the max size to that particular size and stack array. I'll create an array of the same size and I'll put the top is -1. Okay. How will I call this? So in order to explain now, I just put it. So I'm creating an instance of the stack S and I'm telling I want a stack of the size 5. Okay, so this code will do that for me. Now, I want to know now these are the now I want to know the boundary conditions, right? Now let's say my array size is 5 and my array is already filled with 5 elements and I'm trying to insert one more element into it. Can I insert? No, it should throw an exception, correct? So that is why before every insertion of an element, you would check whether the stack is full. Because during push, if the stack is already full, you cannot insert further elements into it. Okay. And next, there is another method called isEmpty. Why do you want it? Now I'm popping out elements from the stack and my stack is already finished. It is already empty. Then can I further go and pop the elements out? No, correct? So whenever you are popping out elements from the stack, you should always check whether it is empty. If it is empty, you should throw an exception. I'm sorry, boss. I don't have any elements in my array, in my stack. How can I give you, right? So to find these two, we are implementing these two operations. These two boundary conditions. They are not operations, but the boundary conditions which helps the stack operations. Now tell me, what are the 3 important stack operations? Now, we have implemented an operation called peak. What is peak? So now I'm peeking into the stack to find out what is the top element. Now, if the stack itself is empty, can I go and peek in and try to see what it is there? No, correct? So, if the stack is empty, you will throw empty stack exception. Okay, otherwise, you will just return the top element. You will not pop it out. You will see what is the element at the top of the stack and you will return it. Okay, so this is peak. Clear? Okay, now what are the other operation? Okay, let's say push. What does push mean? What is push operation in stack? Okay, insertion in stack is called push. Now let us implement this push operation. Okay. So this is the important operation in stack. If anyone says about stack, you should remember this operation: push, pop, and then pick. Now, push. You're pushing the elements in this stack. If while pushing the element, you should always check if the stack is full, right? So instead of checking stop -1 or something like that, you can always check if the stack is full. Okay, if the stack is not full, then you can push the element into the top element of the stack. Let's say if top is equal to -1, when you do plus top, it will be stack array of 0. Stack array of 0 will have book 1. Let's say the value is 1, then stack array of 0 will have 1, and you will print the value pushed. Okay. Otherwise, you will say the stack is full and cannot push. You can either check whether the top is less than max size -1. Max size is 5, 5 minus 1 is 4. If the top is already equal to 4, which means you already have 4 elements into this in the stack, you cannot push any more elements into it. Correct. So that is why we have done that there. So instead of that, you can also check is full. Okay, if it is not full, you can either do like this, or you can write if it is not full, then if the stack is not full, I can definitely push an element by incrementing the top, because I mean incrementing the index position. Okay, now let's say the top is equal to -1 at the beginning, correct? And I'm telling you to push an element 4, let's say we'll start push the element 1 into the stack. This is my stack. Okay, so I'm pushing 1. So before I'm pushing 1, I'll make the top increment and I'll store the data. Correct? If you do see here, stack array plus top is equal to value, so which is 0 will have 1. Next, let's say we are trying to push 2, 3, 4, 5. These are the 5 elements to be pushed. Okay, so this is my top index and this is my value. So first time when you push, I make top is 0 and array of 0 will contain 1. Next time when I push, I'll make it as 1 and I'll push it as 2, right? Now when I put 3, what am I checking is stack is not full, right? When will you say full? The top is, when the top becomes 4, you say stack is full, right? Because you can insert only elements between from 0th index to 4th index. Okay, so now 1 comes, so I put 2. Yeah, top is equal to -1 is to show that the stack is empty. Yeah, index always starts from 0. Yes, Murli, top always takes the index value. So next, but for everyone's understanding, let's say I want to insert the element. Now I've inserted 1 and 2. Now I want to insert 3 into the stack. So I'll increment the position. So in a stack array of 2, I'm putting this element 3. Now in the stack, now I want to push the element 4. So I've incremented the top value and I'm putting 4. Okay, now 0, 1, 2, 3 I have. Now I want to push the element 5 into the stack. So I'll increment top to 4 and I will put 5 into the stack. Now let's say I'm asking to push 6. What happens? Here, the top's value is equal to 4. The top is equal to the max length. So I will throw an exception and I will say, I'm sorry, I cannot insert 6 into the stack because my stack is running out of size. Got it? Correct. Now let me go to the pop operation. What is a pop operation? One-liner, please. In pop operation, you are deleting an element from the array or you are removing a book from the carton. Okay. Now, so when can I remove an element from an array? Let's say if my stack itself is empty, can I do a pop? No, you cannot, right? So you should check whether the stack is empty or not. If it is empty, throw. I'm sorry, boss. The stack is already empty. I cannot go and pop any elements out of it. Otherwise, what I will do is I will take the value of the top element in the array and then I will decrement the top. Got it? So what I will do, if there are 5 elements in the array, 1, 2, 3, 4, 5, I would see what is stack of top. Stack of top is equal to 5. So I will take the value as 5. So I'll keep the value in the value variable and I'll decrement the top. So now my index or the position of the array is at 4. Got it? Now I'm telling I want to push 1. Let's keep 0 itself so that you're not confused. The element, or we'll keep 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, and 6. Okay, I want to perform push of all these 6 elements. So as you all know, when my stack is empty, there is no element in 0th position. So the top is -1. Correct. Now, inside my array is empty now, right? Array is empty, which is nothing but my stack array is empty. And my top is -1. Correct. So initially, when I get my element, they're asking me to push 1. Then I see that the top is -1, my index is -1. So I will increment my index, which is 0. And 0 is less than 5, which is my max size. Max size is equal to 5 for me. So I say my max size is 5, top is -1. I'm trying to push an element 1 into the stack. So I will increment the index of the stack array, which is -1. If I increment by 1, it is 0. And inside the stack array of position 0, I'll push this 1. Is this clear? Okay, so once this is done, now they're telling me to push 2. So if I have to push 2, I have to increment the top 1. Okay, and I'm pushing. In the first position, I'm pushing the element 2. Now they're asking me to push this element 3 into the stack. My top is 1. 1 is less than the max size. Okay, so I'll increment 1 to 2. I can increment because I have enough space. I have not reached 5 and numbers yet. Okay, so I'll push the element 3 into the stack. So how will you check whether the stack is full or not? Your top should be equal to, if the top is equal to max length -1, because array starts from 0 to max length, right? 0 to max length -1. So if your top is equal to max length -1, which means that you cannot push any more elements, you are already full. Okay. Now we have inserted 1, 2, and 3. Now let us take 4. So 2 is 2 equal to 4? No, which means I have enough space left. So I'll increment the top position and I'll insert the next element. Now I got, they're asking me to insert the element 5. I will check whether 3 is equal to 4. No, I have space to insert. So I will increment top. Top will become 4 and I'll insert 5. And now comes, they're asking me to insert 6. Top is 4. Max length -1 is 5 -1 is 4. 4 is equal to 4, which means your stack is already full. Can you insert? No, you will throw an exception. Yes, if top is equal to max size -1, then your stack is full. So we have covered all the operations of stack, right? And this one. Now let us call our main method and run this program. So my data structure is ready. And now I'm going to insert the elements and see what is the value. Okay. Now let's say I'm pushing 5. Let me comment all this out. Let's say after pushing these, what is the answer? Okay. Okay, when you push 10, 20, 30, After your NQ operation, you have said I've pushed. Okay, 10, 20, 30, you have pushed. And now, when you do stack.peak, what is the expected output? 10 or 30. What is stack? Stack is last and first out. What did you push first? First you have pushed 10, and then you have pushed 20, and then you have pushed 30, right? So what did you insert at the last? 30, right? So when you do a peak, it will do 30. Okay, it will just display this element. Now tell me, after I did a peak operation, I'm trying to make a pop. So what will this program return now? I did a peak and then I'm doing a pop. When I do a pop, what element will be popped out? I see many giving 10, 20, 20, 10 and so on. Okay, 30 will pop. Because peak will only peak. It does not remove the element. And let's say when I'm doing additional pop, what will happen here? Yeah, you have removed 30 out, so 30 is not there. So, and next, I'm doing a stack.push 40. So, what all elements will be there after I pushed 40, 10 and 40? Now I'm pushing 50. I'm glad that you're clear. Now, I'm calling this is empty operation. So, what will this stack return? Now, what I'm going to do, I'm going to pop out all the elements from the array. So what will be the output? Empty stack. So now we have gone through stack. We all understood what is the basics of stack, how to do that and all. Correct. Now let us focus into one sample problem for stack, which is like you get an input with parenthesis, okay, and you have to check whether it is balanced or not, okay, which means if you have a open parenthesis, you should have a corresponding closed parenthesis. Okay, if you have an open square bracket, you should have one open closed square bracket, and open flower bracket, then there should be one closed flower bracket. Now, this first one is balanced because for every open you have a close. And second one is also balanced because for every open you have a close. Look at the third one. You have a open parenthesis which is a normal one, and there is a closed square parenthesis which doesn't match, correct? So the output is false. Okay, look at the second one. Now if you see here, there is an open square bracket, but there is you should have a closed square bracket and then you should have a close parenthesis, right? So, but here it is in reverse. So the output is false. Okay. So before going to this thing, can you find any few programs or use cases where do you apply stack? Whenever, let's say you are getting a problem, whenever you have a string or whatever input elements it is, whenever you want to compare first half with second half, then you go for a stack. Okay, so in any problem, if you encounter any scenario where you want to compare one half with the other half, you'll definitely go for stacks. Okay, you want to check whether a string is palindrome or not. So first half you can push it into the stack, and then the next half you can pop it out from the stack and see whether they are matching or not. Okay, so anything where you want to compare the first half with the second half, then you go for stats. Now let us see this example for valid parenthesis. Now there is okay. Now let's go to this problem called valid parenthesis. Okay, you are given with an input, and you have to write a code to find out the parenthesis is balanced here or not. If it is not balanced, you will return false. If it is balanced, you will return true. Now, so what you are doing? So what is the clue here? For every open parenthesis, there must be a corresponding closed one. Correct? So that is the thumb rule. Correct? So what you can do, all the open ones, you can push it into the stack And whenever you see a closed one, you should check the top of the stack matches with the corresponding open parenthesis of that closed parenthesis, right? Then if it matches, you can just pop it out. If it doesn't match, it is definitely not a balanced one. Okay, let us see how you're going to approach this problem. See what you're doing. Whenever you're getting an open parenthesis, you put it into the stack, correct? So whenever you're getting an open parenthesis, you'll push it into the stack, correct? Now this is an open parenthesis, this is an open parenthesis. So I will push both into the stack, and now I got a closed parenthesis. Anything which is closed, I'll not put it into the stack. So what I will do, I will compare the closed one with the open one, so I will compare this and this, and I will check whether they are same. If they are same, if it is a square closed bracket, then the top of the stack should be square close open bracket. Okay. When the parenthesis matches, which means they are valid, you can pop it out and continue. Let's say if it doesn't match, now I got a closed square, and let us assume this has a flower bracket, then this doesn't match, correct? In that case, you will say this is not balanced, I'm sorry, I'm going away. Okay, so this is the entire thing, entire story behind this. Now let us see how we are going to check for this one. Okay, now I got the first one, which is open parenthesis, so I'm pushing it into the stack. Now let's move to the next one. So in the next slide, next element is again open square bracket, so I'll push it into the stack. So whenever this parenthesis is open bracket, you will push it into the stack. Okay. Now I got a closed one, correct? Now I got this, which is a closed parenthesis. If it is a closed parenthesis, I will compare with the top element in the stack. What was the top element? The top element was this one. Okay. So this and this. So you found the corresponding open parenthesis, which means there is a match. You can pop and continue further. Okay. Now the next one I got is open parenthesis, right? Which is then again I'll push it into the stack. Now I got a closed parenthesis. So whenever I'm getting a closed parenthesis, I will check with the top element in the stack, and if it matches to what I'm looking for, okay, and then I'll pop it out. Okay. Now, finally, I have this closed parenthesis. So what was present in the top of the stack, which is again the corresponding open. So I will pop it out, and my stack is empty. So if my stack is empty after validating everything, which means that the parenthesis is balanced, and I will return true. Okay. So now let us go through the problem. Program for this. Here, instead of creating the data structure, we are using the built-in data structure, which is stack. Okay. And then now for every open parenthesis, you should have a corresponding closed one, correct? So you need to create a map, right? For every open one, you should have a closed one. Only then you can find out whether you have the corresponding open parenthesis within the stack, correct? So that is why you are creating a map. Understood? There is some problem with the codes, so I'm changing the codes. So this map is for whenever you encounter a closed parenthesis, correct, you have to find out whether the stack contains the corresponding open one, correct? If it only has, it is same. Okay, so that is why I'm creating a map to identify the match. And after that, once I get for every character which is present in the string, what I would do, if it is opening parenthesis, then you will push it into the stack. Okay, so If it is opening parenthesis, you'll push it into the stack. Otherwise, what will you do? You will find out what is the corresponding close parenthesis and you would check whether it is matching with that the element in the top of the stack. If it matches, then you will pop it out and continue further. Otherwise, you will return false. Okay. And in between, if they put any other characters inside, it will again doesn't match, right? So that is why you have the last else block. And if the stack is empty, then which means the parenthesis is balanced. If not, you will return false. Okay. Now let us execute this. Now the next one is the closed square bracket. Whenever you get a square bracket, closed parenthesis, whatever it is, whenever you get a closed parenthesis, what is your rule? You will peek into the stack and check whether it is your corresponding open one. Correct. I went into the stack for this closed square bracket and I did not find the matching open one, which means it is false. It is not balanced. Okay. Now I have this parenthesis. What is the first thing? What will I do for this one? You will push that one to the stack. Now I have second one. What will you do? Push to the stack. Now I have this closed one. What will you do now? Push for this. This is, look at this. This is a closed one. Whenever you see a closed parenthesis, you will have to compare it with the top of the stack. Will you pop? No. Before that, you will check whether they match. If they don't match, what will you do? You will return false. You will compare and return false. You will not go through the next one at all. Here itself, we know that it is false. Come out. Okay, now before that, this is my first element. So what will you do for this one? Whenever you see an open parenthesis, what will you do? Not a closed one, sorry, this is an open parenthesis. What will you do whenever you see an open parenthesis? I'm taking the first character in the string, whatever you have given. So you will push it into the stack. I've pushed this one into the stack. Okay, now I got the next element. So I'm pushing it into the stack. So I do a push. So my stack is this. Now I got this, and the next element I got is this one. What will you do? Open flower bracket. Okay, good. We'll push it into the stack again. Now, the third element I got is the closed parenthesis. What will you do? You will compare it with the top of the stack. Whenever it is closed, you have to compare with the top of the stack. And if it matches, you will pop. If it doesn't match, what is the top of the current stack? So the top of the current stack is open flower bracket. Okay. But what are we looking for? Open parenthesis, correct? But it doesn't match. So what will you do if it doesn't match? You will return false. Furthermore, you will not do any comparison. Got it? Okay, now we'll move on to the next concept, which is called queues. So, what is LIFO? Last and first out. Okay, so in stack, the element which you have inserted at the last is the first one to come out. Correct. Now, what is a queue? Okay, give some examples of queue. Any ticket counter where you are standing, right? The first person who's getting in will be the first person to collect the ticket and come out, correct? You always maintain the order, like the first person who enters is the person who comes out. So any counter or any reservation center where you go and where that it follows an order, like whoever enters first is the first person to come out, then what data structure will you follow? It is called queue, right? So in stack, you had two operations, right? Two important operations. What are they? Push and pop. Correct. Similarly, in queue, you have two important operations. Okay, it is called called NQ and DQ. NQ means you are inserting elements into the queue, and DQ means you are removing elements from the queue. Okay, so there are two main operations. One is NQ and another one is DQ. Okay, stack is always push and pop, and queue is always NQ and DQ. Now, where can you insert elements into the queue? You can always insert at the end, correct? Someone is standing at first in the ticket counter. Can you go and tell him, hey boss, move? I'm an important person. I want to go and stand in the front. Will he let you in? No. So what you have to see? You have to go to the end of the queue, find out where the tail is, and join them. So any insertion will happen at the rear end, and any deletions will happen at the front. Okay, got it? So NQ will always happen at the rear end of the queue, and DQ will happen at the front. Okay, whoever is standing front will be the first person to come out. Okay, so are you now clear about two operations, NQ and DQ, and where NQ is happening and where DQ is happening? Okay, now let us try to implement Q in Java. Okay, now let's see. So let us create a queue with all important variables. Okay, so we have input array, which is the data array. And then we know that there are two things, like for insertion, we want rear end. For deletion, we want front end. Correct. So I want two pointers or two positions which says where is the front and where is the rear. Okay. And also I want to know the size of the how at any point in time, I have to know how many elements are there in the queue. Correct. So for that, the size, and there is a capacity which says what should be the array size. Okay. So for that, you have capacity. So now, if anyone wants to try to use this queue, I have to expose a dynamic queue creation using a constructor, right? Like the way we did for stack. The same way, I'm creating a constructor for queue where the user can say, I want to create a queue of size 5. So they will instantiate queue with 5 as a value in the constructor to the constructor. Then it would create a array of size 5. And initially, there are no elements in the array, right? So the rear end will be -1. Like the top was -1 in the stack, in the queue, the rear will be -1 and the front will be 0. Okay. Front is only used for dequeuing the elements from the queue. So there you will always check, and now you have to check the boundary conditions, correct? Here again, you have to check whether the queue is full or empty. So how do you check whether the queue is full or empty? Here, as you enter the elements into the queue, you will track the size of the queue. Whenever you are doing an NQ, you will increment the size. Whenever you are doing a DQ, you will decrement the size. So at any point in time, if you get the size as 0, which means that the queue is empty. And if the size is equal to capacity, which means that the queue is full. Okay, now let us go to those boundary conditions and let us add them. Now, why are we adding this boundary conditions? Using array because ticket is limited and size is fixed. Now tell me, how do you do the boundary conditions? How will you check whether the queue is empty or whether the queue is full? The only way where you can check whether it is empty is using size. Okay, that is why we have introduced additional parameter for queue to identify the number of elements in that. Written size is equal to capacity. Okay. Now, what are the other operations which we do in stack? Can you list down the operations? It's peak. Okay. Let's start with peak and then do with NQ and DQ. Okay. So what does the peak do? Peak is always from the front side, because before you DQ something from the queue, there is no top value in queue. So there are two, only rear and front. So wherever you are dequeuing is where you will go and check what is the current, who's there waiting in the queue, right? So it is always the front. Okay. Now let us go to the main chunk. Okay. Now tell me, I want to do an NQ into the queue. What is NQ? NQ means you are inserting the value to the rear end of the queue. You can never insert into the front, right? If you go and break the queue, they will not let you in. Okay, so always remember you will add element to the rear end of the queue. Okay, now before adding the element, what should we do? You have to check whether the queue is already full. It is full on capacity. If it is full, you can definitely not add elements into the queue. Okay. Otherwise, what you have to do, you have to increment rear and then put the element into the queue. Okay. Now, why are we doing this modulo capacity? Correct? So now everyone will have a question, why are we doing this? Okay, let us go and see an example. So, as you know, when the queue is originally created, I told I want a queue of size 4. Okay, and the rear end is empty because you will put the insertion here as top is equal to -1. Similarly, rear you will put -1. And max capacity is 4. The front is 0. That's where you are dequeuing. Because the size is 0, you will not dequeue. Correct. Now, I'm asking, I want to NQ2. So when I want to NQ2, I will increment to the rear end and rear becomes 0. And you will put in the date of 0, you will insert the element 2. The front will remain as such and the size will be 1. Now, if at all they want to dequeue, the size is 1. So you have enough elements to dequeue, then you can remove date of 0 out of it, 2 will be popped out, if at all. Okay. Now let us go to the next one. I'm telling NQ3, so I'm inserting 3 here. So if I have to insert 3, I have to increment the rear, so the rear becomes 1. And I'll also increment the size, so size becomes 2. And inside the data of rear, which is data of 1, first 0, first element I'm putting 3. Got it? Now, the next one is NQ4, and I want to put 4. The front will be 0 as such. You are not going to touch any front because you're only doing NQ. NQ means you will only change the values of the rear end. Okay, so the rear you will increment and make it as 2. And you will also increment the size because you are adding element to the queue. If you are removing it, you will decrement the size. Okay. And in the date of rear, I'm putting 4. Now, NQ of 5 comes. So the front will be untouched because you're doing an insertion. You'll only touch the rear end. Increment the rear, you'll put 3. The size becomes 4. And date of rear, in the third position, I'm putting 5. Now, I say DQ. When you say DQ, what will you touch? You will touch the front, right? You will increment the front by 1. And rear will be unchanged. It will be 0, 1, 2, 3. And you will decrement the size because you have removed an element. So you will decrement the size and you will return the top element, right? So you would have returned 2 as part of DQ operation. Now let's say I want to NQ6. This end was free, correct? Now, if I increment the rear plus 1, what will happen? It will become 4 plus 1, 5. Is this a valid position? No, correct? You cannot go beyond the capacity. So what will you do? If you see the previous step, the rear is 3, correct? Which means you have an space to insert one element into the queue, but you have to insert it in 0. You should not do it in 4. So what will you do? Rear plus 1 modulo the capacity. So rear plus 1 is 4, 4 modulo 4. If you divide 4 by 4, what is the remainder you get? Remainder is 0. So modulo means remainder. For people who doesn't know what modulo operator does is, it picks the remainder after the division. So after division, whatever remainder you are getting 0. So to the 0th position, you will insert this element 6. And you will increment the size. Size was previously 3, now it will become 4. So this is an important concept for your queue. Okay. Okay, now you understood the NQ. If the queue is full, you cannot add elements. Otherwise, you will do rear plus one modulo capacity and you will add it. Now, we will do a DQ as well. It's the same, right? You might have understood by now. So tell me in what condition you cannot DQ. You cannot NQ when the queue is full. When can you not DQ? You cannot DQ when the queue is already empty, right? My queue is empty. How can you pop the element? I mean, remove the elements out, right? So the removed value, you will get it from the front. And front, you will do modulo capacity. Now you understood why we are doing a modulo capacity. And then whenever you are doing a DQ, you will decrement the size of the array or the size of the queue. Correct. And whenever you NQ, you will increment the size of the queue. At any point in time, size will give you the number of elements in the queue. Got it, guys? Now let us run this. Okay, so we will run. Now, after these selected, what is the value of what all elements are present inside the queue till this one? NQ10, NQ20, NQ30. Next, when you do q.dq, what is the what all elements will be present in the queue after you do a dq? Now we are doing a q.nq40. So what is the output? It would be 20, 30, 40 in queue, first in, first out. Okay, don't forget. Yeah, the remaining elements will be 30 and 40 after you dq. Okay.
Just a quick info, guys. Intellipaat offers a full stack web developer course in collaboration with iHub IIT Roorkee. Through this course, you'll learn tech stack like MongoDB, Express.js, Angular, Node.js, along with HTML, CSS, JavaScript, and more from the IIT faculty. With this course, we've already helped thousands of professionals transition into high-paying developer roles. You can check out the success stories on our Achievers channel, whose link is given in the description below. No doubt this course can take your career to new heights. So check out the course page link in the description and take the first step towards becoming a certified full stack web developer.
So what is stack and what is queue? Now, let us actually write some code, enough of theory. Nobody likes theories. Okay. We'll be learning stack data structure. Okay. So just write stack. Okay. Give it a name. S capital because it is coming from a class, right? So S capital, give it a name. I'm going to call it a stack only. Stack equal to new stack. That is actually wrong. Okay. I'll tell you why this is wrong. Let me just import it. Yeah. We have to give it over here integer. Okay. To tell that this will contain integer data types, right? Stack can be made from any data type, whether it is integer or character or string, any data type you can think of, it can be made with that data type. Okay, we are going to make a stack of integer data type. Okay, if I want to add an element, how will I add? We will write stack dot push. Stack dot push. What do we want to push? We want to push, let's say 10. So 10 is pushed. Okay, then stack dot push another element 20. Stack dot push 30 and stack dot push 40. Okay, these are the 4 things which we have done. If I say how to remove an element, we say stack dot pop. Okay, stack dot pop. And if I just go on and print stack, what will be the output? The implementation of this will be in form of push. 10 will be pushed like this. Show you. Stack is going to be formed like this. Okay. 10 will be pushed. 20 will be pushed. Okay. 30 will be pushed. Okay. And 40 will be pushed. Okay. If you say stack dot pop, it will pop this one and print the rest of this. That is, you can see just a second. Yeah. You can see the output on your screen. 10, 20, and 30. Okay. If you remove the pop, then You will have all the 4 elements in the stack. Okay. If I go on, let's say instead of printing the stack, I write stack dot peak. What will be the output? The topmost element, the element at the top will be printed, right? Printed, right? 40 is getting printed. If I do stack dot pop, what will be the output now? 30, because this one is removed and then we are doing peak. So 30 is getting output over here. Okay. Push, pop, and peak. Push, pop, and peak. You can also use things like stack dot is empty. Okay. What will be the output? If you write stack dot is empty, answer will be false. Why it will be false? Because it's saying stack dot is empty. Is stack empty? No, stack is not empty. Stack is filled with these elements. Stack is filled with these elements. So we will not get output as true. Okay. If stack was empty, then we will be getting true as the output. Okay. If you want to check like whether there are elements in like opposite of stack is empty, you can say if you want to check whether there are elements present, you can use this also. Okay. Stack is not empty. If you write this operator in front, that means not. Okay. Stack is not empty. It will be treated as not. Okay. Stack is not empty. You will be getting output as true now. Okay. Stack is not empty. That is true. So this operator, you can say not equal to not. This is a not operator. Okay. Saying stack is empty or stack is not empty. Okay. This was stack data structure. I hope stack data structure is clear. Let us quickly know queue data structure and then we'll do 1 or 2 questions. Queue of type integer. Queue integer, give it a name. Let's say you name it as queue equal to. Let's try to import it. Import equal to new. See, this queue data structure is actually implemented with the help of which data structure? Queue you can implement with the help of which data structure? Linked list, right? Queue can be implemented with the help of linked list. Internal implementation is with the help of linked list, right? So you will write linked list. Okay. So stack is implemented, sorry, queue is implemented with the help of linked list. Okay. Not stacks actually, you can implement queue with the help of linked list, priority queue, or I think from heap also. So there are 2-3 ways with the help of which you can implement a queue. The very easy and basic one is using linked list. Okay. With the help of linked list, that means it does not have a fixed size, right? It does not have a fixed size. That is one thing given. Let us learn a little bit about queue data structure. A collection of design holding elements prior to processing. Okay. Yeah. What are the elements available? Insert, remove, peak, offer, pool. Okay. Offer and pool are equal to add or remove. Okay. If you can use offer or pool, both are same thing, add or remove. Both will work same way. Okay. Like push and pop, here we have offer and pool. In case of, you can say NQ and DQ. Okay. Here is a little bit information about queue data structure. Queue is typically, but do not necessarily orders FIFO data structure. First in, first out. Okay. There are different ways, I can say different things written about what are the different methods. Remove and pull methods are used for removing element from the, you can say queue. Okay. Element and peak methods return but do not remove. Okay. And it is implemented with the help of linked list. Yeah, that's about it. Okay. So theory I have already told you. Let me just remove this. Okay. Now, how do you add an element? You will just write queue add and it will be added. Queue dot add 20. This will be added and this will be added. If I try to print out queue, you will get all these elements. Okay. All these are added. If I before this write queue dot remove, what will be the output? Output will be 20, 30, and 20, 40, and 60. Why? First one to get in, first one to get in, first one to get in will be the first one to get out. First in, first out. So you have your change. First in, first out. Got it? One more thing, you can use peak also. If you write q dot peak, you'll get the 20. Okay, because this is at the front. This is at the front now after removing of element. Right. Okay, I will be giving you one question and I will be explaining the question and I will be giving you an algorithm. Okay. And with the help of that algorithm, you are going to solve that question. The name of the question is called as a valid parenthesis problem. What is a valid parenthesis problem? So, what is valid parenthesis problem? Let's say you have parentheses. Okay. Not actually only parentheses. All the, you can say, brackets. It involves all the brackets. Okay. Let's say you have one opening bracket, one closing bracket, one opening bracket, same closing bracket, and closing big bracket. Okay. Now, corresponding to this is one closing bracket, corresponding to this is one closing bracket, corresponding to this is one closing bracket, is one closing bracket. Right. This is your problem. This is your problem. You have been given some parentheses. You have been given some parentheses within the form of a string or a array of characters. Okay, same thing, right? String or array of char. You've been given that and you have to tell whether this thing is a valid parenthesis or not. Okay, and let's say this is one other example. Opening bracket, closing bracket, closing bracket, and closing bracket. Okay, I don't think this is a valid parenthesis, right? This is not a valid parenthesis, right? See, you cannot do a question like this. Okay, when I got to this question and why when I did not knew about stack data structure, when I thought stack data structure was pretty much useless data structure, every question can be done with the help of array. Okay, what solution I came up with? Like this. Okay, I thought I can do this with the help of, you can say, two variables, count 1 and count 2. Okay, I can say that if opening bracket, opening parenthesis is coming, I will increase the count. And when closing parenthesis is coming, I will increase the count of, or you can say decrease the count of this. Okay, or actually increase the count of this also. Okay. And at the last, if I will say if C1 minus C2 is equal to 0, I have a valid parenthesis. It will work in this case. Right. You will see like, okay, 2 opening bracket, this will be equal to 2. 2 closing, it will be equal to 2. 2 minus 2 equal to 0. So I can solve this question like this, right? Anyone see a problem in this method? Okay. The problem is if I have like this, okay, 2 first closing brackets, then 2 opening brackets, right? Or opening bracket, closing bracket, opening bracket, right? This is working. Okay, with my method, with my, you can say, solution, which I just told you, this will work. Okay, this will say that this is a valid parenthesis, but do you think this is a valid parenthesis? No. Okay, valid parenthesis is when one corresponding to one opening bracket, there is one closing bracket. Corresponding to one opening bracket, there is one closing bracket. Right. This is called as a valid parenthesis. Okay. This is called as a valid parenthesis. Not this one. Right. It is not. Let us actually see the question and then I will show you the algorithm. Okay. Yes, this is the question. Valid parenthesis solution. Okay. What you have been given? You have been given one string S. Okay. In that it contains like this. Okay. And what else you have been given? You have to return a Boolean value. Okay. So what exactly is being asked? That this is one method. No main is there. This is one method which takes one string, which will be passed as like this. Okay. You have to return a Boolean value, true or false value, if it is a valid string. If it is not a valid string, you have to return false. Like if this is given, you have to return true. If this is given, you have to return true, like opening, closing. So this is true. For this, you have to return false. Right? It's some more example if it is there. Yeah, that is it. Okay. Some more instructions have been given over here. Opening bracket must be closed with the same type of brackets. Opening brackets must be closed in the correct order. every closed bracket has a corresponding opening bracket of the same type. Okay, these are some of the conditions given. If you want to, okay, just use this. Okay, I will not send you the link or anything. You have to solve this. You have been given this thing, and I will tell you what is the algorithm. Okay, how you have to actually implement it. Then we will write the code ours. Okay, this is the algorithm. Okay, you have been given these things. This is the algorithm. Initialize an empty stack and store the parentheses. Iterate through the each character. Iterate through the each character. Let's say you have been given this. Iterate through the each character. How will you iterate? Using string.char@. Okay. In the input of the string, if the character is opening parentheses. Okay. If the character you are on is the opening parentheses, meaning if it is this one, this one, this one, or this one, you push it into the stack. You push it into the stack. Okay. If the character is closing parentheses, meaning if it is this, this, or this, okay, then if the stack is not empty, if the stack is not empty, and the top of the stack contains the corresponding opening bracket, okay, let's say this is coming, this bracket is coming, and on the character which you are on, okay, and stack is not empty, and at the top of the stack. Okay, how do you check the top of the stack? You peek. At the peak of the stack is this bracket. Okay, is this bracket. Then pop the stack. Pop from the stack. Okay. Otherwise, parenthesis is not balanced. Meaning the character you are on is this one. Okay. And corresponding at the top of the stack, you're getting, let's say, this one. Okay. That means the stack, that means the parenthesis is not balanced. So return false. After processing all the characters, check if the stack is empty. Okay. If stack is not empty, then that is false. If stack is empty, then parenthesis is balanced, return true. Otherwise, return false. Okay, guys, this is the solution. This is the solution of this. Let us actually copy this and let us see. Okay, and discuss what is happening. Okay, so what we have been asked. Okay, we've been asked to check if it is a valid parenthesis or not. And this is our algorithm. Okay. Initialize an empty stack to store the parentheses. Initialize an empty stack to store the parentheses. What we are doing? Okay. We have been given one string. So I have okay. I've converted this into a character array. What we have done? I've converted a string into a character array. Okay. I've named it as S1. Okay. So a string is actually form of characters only. So individually I have separated them. You can do it with the help of string only. That is also fine. Okay. String is given or a character array is given. Both are fine. Int length is equal to s dot length given. Okay. We are saying that if length is equal to 0, meaning there is nothing. If there is nothing, that means valid parenthesis is true. Right. Okay. Now stack is made of what? Character. Stack is made with character. Okay. Stack is made from character equal to new stack. So a stack is made of characters. We are going through a for loop. Okay. From I equal to 0 to I length. Meaning we are going to iterate the whole thing. We are going to iterate the whole thing. We are going to iterate the whole thing. We are saying that if the element which we are on currently is an opening bracket, I can say this, big bracket, or a curly braces. Okay. Parenthesis, big bracket, or curly braces. Then we will push it into the stack. We will push it into the stack. Right. That was asked if the character is an opening parenthesis. Right. This one, this one, this one. Then push it into the stack. Push it into the stack. Okay. Right. Else if stack is not empty, while the stack is not empty, okay, and the element which you are on currently is a closing bracket. Okay, element which you are on currently is a closing bracket, and at the top of the stack, we have a corresponding opening bracket. Okay, element which you are on currently is a closing bracket, and at the top of the stack is a opening bracket. Then we will pop. Pop will pop this element out. Pop will remove this element. Right. Same we are doing with these bracket as well. while the stack is not empty, and at the top is while the you can say element which you are on currently is a closing this bracket, and while we are peeking at the stack, we have corresponding this bracket. Then we will pop. This will be removed. Okay. Same way we are doing for the curly braces. Okay. And else we are returning false. Else we are returning false. In any other case, we will be returning false. Okay. At the end, we are returning stack dot is empty. What is the meaning of this? Stack dot empty. We are saying that if stack is empty, this will return true. Okay, then our parenthesis is valid. Okay, it is a valid parenthesis if a stack is empty. Okay, otherwise it will return false. That means that means there is something still left in the stack while all the closing parentheses are gone. Okay, that means it will be false. Okay, let us run this and see if it is right or wrong. Obviously, it is right. Okay, and you can see the test case. This is a sample test case. Test case number 2 and test case number 3. Okay, it is returning false in that case. If we submit, all the test cases will be cleared only. Okay, one last question we are going to cover. That question is called as reverse polish notation or postfix notation. Okay, evaluation of postfix notation. Okay, first we will learn what is postfix notation and how do we evaluate it. Okay. Okay, I will very quickly tell you what is a reverse polish notation or a postfix notation. Okay, it is actually widely used in industry for computers to evaluate a lot of things. See, how do you evaluate things? How do you guys evaluate things? If I'm giving you 3 plus 5, okay, how will you evaluate it? You will write 8, right? Okay, if you want to convert, this is called as infix notation. What is called as infix notation? This is called as infix notation. Okay, why it is called as infix notation? The operator is in middle, right? Operator is in middle. In postfix notation, you write it like this: 3, 5 plus. How do you write it? You write it like 3, 5 plus. Okay, so you will be given a postfix notation and you will have to evaluate it. Okay, using stack. Output of this will also be 8 only. Okay, output will be same. To convert a postfix notation into infix, you will put it like this. Okay, let's see some more examples for you to understand what is a postfix notation. Okay, see, you have been given a reverse polish notation. Okay, like this. How? 2, 1 plus 3 star. 2, 1, 3 plus star. If you will convert it into a normal form, it will be like plus will be over here. This plus will go over here. Okay, so this will become 2 plus 1. 2 plus 1. Okay, now treat this as 1. Okay, and it will be like 2 plus 1, 3. So this will go over here. So it will become 2 plus 1 star 3. This is your infix notation which humans can properly read and you can evaluate it, right? 3 into 3, 9. Got it? Got it? What is infix and what is postfix notation? In postfix, operators are written afterwards. Okay. Now let's say this is given. So how will you evaluate it? How will you evaluate it? First, this bracket will go over here. Okay. 13 divided by 5. Okay. And you put bracket 13 divided by 5. Right. Now what will happen? 4, 13 divided by 5 and plus. Okay. So plus will go over to here. So 4 plus 13 divided by 5. What is answer? 6. Same way you can evaluate it. I'm not going to explain this much big thing, but they have actually done that. Okay. So what is happening? What is given to you? You have not been given this thing. You have not been given this thing. Okay. You have been given this thing. Okay. And we have to evaluate it. We have to evaluate it. Okay. How will we evaluate it? How will we evaluate it? I have the algorithm. Okay. I have the answer also over here. First of all, what is given over here? We have been given a string. Okay. Each of this item is a string. Okay. String. These are not characters, these are strings. This could have been character, but these are strings. Okay. How will you evaluate it? How will you evaluate it? This is the algorithm of this. Create a stack integer to store the operands. What is operands? 1, 2, 3, or meaning anything else apart from these operators. Okay. Those are called as operands. Okay. Any value. Now iterate through the each token in the input array. Okay. What is token? Iterate through the each value. Iterate through the each value to the input array. Okay. If the token is not an operator, if it is not an operator, token is these things, right? This is being called as token. All these values are called as token, individual values. If the token is not an operator, meaning if it is not plus, minus, multiply, divide, convert it into an integer. Convert it into an integer. See, right now, if you try to write 2 plus 1, this 2 is of type string. If you write 2 plus 1, it will become 21. No, we don't want that. 2 plus 1 should become 3, right? So, what we have been asked, convert it into a integer, right? Convert the string part into integer and then push it into the stack. Okay. That number will be pushed into the stack now. Okay. 1, 2, 3, whatever it is. If it is an operator, pop 2 elements from above. Okay. Pop 2 elements from the stack. Above 2 elements from the stack. Okay. Considering them as operands because these are operands, right? We push operands, right? Perform the corresponding operation based on the operator, right? If the value which we are on is an operator, okay, let's say plus operator, we will remove topmost two stack values and perform the addition on them. And then let's say two values were 5 and 7, we will write 5 plus 7 and then 7 value we will push back to stack. Okay. This process will continue till the last and we will get the final value. Automatically. Okay. Let's take example of this thing. Okay. Very first thing, according to our algorithm. Okay. What we're saying, create a stack, and if the token is not an operator, convert them to integer and put them into stack. So 2 will be pushed, 1 will be pushed. 2 will be pushed and 1 will be pushed. Let me just create it for you. A stack. 2 will be pushed and 1 will be pushed into the stack. Okay. We are saying that if it is token is an operator. Now next thing is an operator, right? Right. So pop the top 2 elements from the stack, considering them as operands, right? Perform the corresponding operation. Corresponding operation meaning if it is a plus, we will perform the plus. If it is minus, we will press minus, multiply, divide. Okay. So perform it. So we will perform, remove this from the stack. It will be like 2 plus 1 equal to 3 and 3 will be again pushed into the stack. So stack value will only be 3 now. Okay. 3. Now next thing is again 3. 3 again will be pushed into the stack. So it will be like, sorry for this. It will be like 3, 3. Right now stack is like this. 3, 3. Okay. Next thing is multiply. Okay. Pop 2 operands, pop 2 things. Perform the corresponding operation. Corresponding operation means multiply. 3 into 3. Pop it into the stack. 9. 9 will be popped into the stack. Okay. Now we are at the end. It is saying that the final result should be at the top of the stack. Only 9 is left. So 9 is our answer. Right. We can use pop or peek. Same thing. Okay. Let us actually see the code of this now. Okay. What we are doing? We are using a for loop. We're going from first to last. Okay. String s is equal to tokens.I. Whatever the element which you are on currently, let's call it as s. Okay. We're saying that if s is not equal to plus or s is not equal to minus or f is not equal to multiply or divide, then we push it into the stack. Okay. We push it into the stack, meaning if it is a number. We do not actually push it into the stack. We convert the string to the number. See this thing, integer.parseInt. Integer.parseInt is a method which converts string to integer value. string to integer value. We push it into this stack. We push it into this stack. We push the number into the stack. If it is not equal to plus, minus, multiply, or divide. Okay. Else, meaning if it is equal to any of these things, then we will pop two things, S1, S2, and we are saying that if it is plus, then we will do S dot push S1 and S2. We will add them. If it is minus sign, which we are on currently, then we will do S dot push S1, S2 minus S1. If it is multiply, then we will do S2 divided by S1. If it is divide in S2 divided by S1 and multiply S2 into S1. That's it. At the last, you can use stack.peak or stack.pop. Both will work. Okay, both will work perfectly. Okay.
Now, I've given you an introduction to trees. So, what is a tree? When you have two items that are connected or dependent to each other, you will go for something called trees. Correct? So, we had linked list that connects two nodes. But why did we go for trees? It is because in linked list, you can connect only two adjacent items. That is, one node can only connect with another item. It cannot connect with multiple items. So in order to do that, they introduced a concept called trees, where you can store the hierarchy. Let's say you are a parent, you have two childs, someone goes and visits your page. They can also see who is below you, like your children. So to have that kind of visibility, to have that connected notion possible, we came up with a data structure called trees. Okay, trees are always like flat, they'll not be cyclic. Okay, like you have cyclic linked list, you will not have cyclic trees. A cyclic tree will become a graph. Okay, got it? Okay, now let us go to trees. So this kind of a data structure, look at this yellow color point, where the first one, the binary, this is called binary tree because every node at any level will have maximum of two children. Okay, every node can have a children or not. Okay, but they can have a maximum of two children, and that is called binary tree. Okay, if you have n number of children, then it is called n-array tree. Okay, so you will have a binary tree, means at any level, at any point in time, any node will have only two. Okay, so those children are called, the one is left and one is right. Okay, now the topmost one is called the root node. The topmost item is called the root node. Like you can say, our human era began with Adam and Eve. See, I'm not opposing Darwin's philosophy, evolution of theory, species, but I'm telling. Let's say the evolution started with Adam and Eve. If so, then that is the root node. One person can only be the root node. Don't ask me there are two people, why there are no two root nodes. Okay. So at any point in time, there is one person who will kickstart this entire hierarchy, and that is called root node. And root node can have any number of children. But if you consider to have a binary tree, it will have only two children. One is left child and other one is right child, because by means two. You at any point in time you will have only two children. Okay, and the node which does not have any child is called the leaf node. What node it is? Leaf node. Because let us assume the normal tree which goes right, which lives a tree. So in the tree, after the leaf, so that thing is called, so the leaf node, even here in our data structure, leaf node cannot have any children. Okay, with that it ends. So, and from, if you see the first level, you had a root node and then you have two children, and then towards the left, you have two more children, right? So these can be like the branches. Okay, every root node can branch out to any number of depth. Okay, depth means as long as it goes. Moving on to the introduction to binary trees. So we had seen two trees and binary trees, where you will see the tree structure. with 2 lines presentation. So a binary tree is a tree which has 2 children. Okay, at any point in time, a node will only have 2 child. One is left child and the right child. Okay, so it can have multiple levels. Okay, like it would have started with 2 levels, like a great grandfather, and then your grandfather came, and then your dad, and then you, and then your children. So likewise, it goes on. Okay, so it can have any number of levels, like great grandfather, forefathers, and so on. But at any point in time, it will only have 2 child. Okay, so one is called left child, and another one is called right child. Okay, so and why it is called binary tree? Can someone give me the answer? Why? What do you mean by binary tree? Yes, binary means 2. It means 2 what? Yeah, it can maximum have 2 children. Okay, any node at any level can only have 2 children. One is left node and the other one is right node. It forms an hierarchical structure. Okay, I'm moving to the next slide. Can you see the slide real life example? Okay, let's say you're working for an organization. Okay, so who's the head of the organization? The CEO will normally be the head of the organization, and there will be multiple people who are reporting to the CEOs. There can be chief technical officers or chief financial officers who reports to your CEO. And every CFO will have their own reportees. Those are senior managers. And then the senior managers can have some managers, and managers in turn will have direct reportees, TLs, and TLs can have many programmers as their reportees. Okay, so the hierarchy goes on. So anywhere if you see an hierarchy which ends, which is flat, which can be ironed out, it is an example for trees. Okay, and so I've explained you something called leaf node, right? So what is a leaf node? Leaf node is the end, correct? Which means, can it have a child? Yes, it cannot have. It will not have any child node. Okay, and what is a parent node? So how can you say a node is a parent node of something? Yeah, it can have any child. Okay, so any node which has a child is called a parent node. Okay, it can have either 1 children, 2 children, or so on. But always remember, by means 2. In any binary tree, you will have only 2 children. Okay, left and right. Now let us go to properties of binary tree. Okay, so by now you would have known the basic properties of binary tree. So what is the main important property of a binary tree? Every node will have, every node will have at most only 2 children. Okay, that is called binary tree. Okay, now there is one more concept called at most 2 children. It can have 2 children, or any node can have a child, or it can be a leaf node without any child also. Okay, but the maximum it can have only 2 children. That is called binary tree. Okay, there is one more concept called binary search tree. So what is a binary search tree? A root node. Okay, so there is another variation called binary search tree, which is more organized and structured, and it will always satisfy certain property. Is there a limit to number of parents? No. You can have any number of limit to number of parents. Every child will only have one parent. Okay. When you have multiple parents, then it becomes connected and it will become a graph. Okay, when you have multiple lines that is going out and getting connected and all, it is not a tree. It will become a connected graph. Okay, so now let us go to the concept called binary search tree. So this is more like a ordered tree or a sorted tree, or it has its own organization. So how does it organize? There will be always a root node, and so whenever a node at any level, if you find the node's left child will always be less than that of itself, and right child will always be more than itself. Okay, so that is called binary search tree. Okay, in binary search tree, at any point, at any level, if you take a node, all the values in the left subtree will always have the values which is less than that of the current value. And all nodes, so at any point, the left subtree will have values that are less than that of the current value, and right subtree will have the greater value. Okay, both, and it is a binary search tree. What do you mean by binary tree? Binary tree means you can only have two child, one is left child and right child, or you can left with no child at all. Okay, you can be an orphan like a leaf node. So binary search tree means the concept of binary trees applies, like it will only have two child, but it will be in a more organized manner where the left child's values, any value which is in the left subtree will be less than that of the root, and any values which is on the right subtree will be greater than that of the root. Okay. Before going to an explanation, let me give you a sample binary tree. Okay, one second. Okay, so Shan has come back. Why we starting from left node in tree, ma'am? Okay, why we starting from left child? Can we start from in right child where we can make a tree? See, any node can have any number of children, right? Which means, what is meant by value here in history? Are we dealing with numbers only? Yeah. For our class, a tree will only have, see, like in stack, everything will have a value, right? You have defined a stack. How did you define? Int data, which contains the value, and then left pointer, right pointer, and so on, right? So everything will have a value. Otherwise, you don't need to have something, right? Let's say you're creating your ID in Facebook, then you will be given with one ID and your friend will be given with another. And how are the connections made? Your ID and your friend's ID are getting linked by a line, or which is nothing but a relationship or a pointer. Got it? So everything will have a value. Okay. So now let's say my root node is 5. Then the next element which I'm going to push to the tree is, okay, 4. So will it come 4? Now will it come in the left subtree, or will it be my left child or right child? Okay, let us form a tree now here. I have a value called 3. Okay, so my first node is 3. Got it? So this is my root node. My root node has a value called 3. Can you see my whiteboard, guys? If so, can you tell me yes? Thank you so much. Okay, so this is my node, correct? So this is my node, right? So my node has a value called 3. So I'm creating a tree. So I'll have a node, okay, tree node, and the value is 3. Okay. And I don't have any children, so my left child is null. He doesn't have any connected node, and my right child is also null. Got it. Now both my child are null, and I am an orphan. I am the root, and my value is 3. Okay. Now, suddenly, let's say I'm going to introduce one more node, or 3 needs to be connected with 4. Now, what will I do? Will I put it in the left child or will I put it in the right child? Greater. Okay, yes. So, what is the rule of the binary? See, binary tree means you will have 2 children. If it is a normal binary tree, I can put 4 here. And whatever comes next, I will put here. Okay, let's say 2 comes next, I will put here. But what is this? This is not a normal binary tree. It is a binary search tree. So what is the rule for the binary search tree? At any point in time, your left child's value should be less than that of the root node. In this case, 3 is the root node. So the left child should be less than that. But the value of node 4, is it greater than 3 or less than 3? So it will go to the right node. So I'll put 4 on the right. Now let's say we have an element called 7. So where will you put 7? A new number comes. Traversing, we can go in any order. I'll teach you about that. The child can be greater than the parent. Yes, Kunal. So if you have any
value at any point in time which is greater than that, you will put it on the right. Okay, which is less than that, you will put it on the left. Right of 4. Why right of 4? Okay, we got a new node 7, correct? Now, I'm taking the 7. What I'm doing, I'm comparing it with 3. Okay, I'm checking whether the value 7, it is greater. What if child is equal? Which is redundant. Correct. In that case, you will not form a tree. Like when you go practically, what is the use behind it? You can come up with many clauses telling, oh, I can have same value. I can think of imagine something, but come into the real use case. Where do you use it? In an org, right? In an org, everyone will have own ID. Let's say I and Kunal. Can I have ID 12 and Kunal can also have ID 12? You cannot differentiate between me and him, right? So ID is something which we should keep in mind. It should be unique. So every node, what is the unique value which identifies the node? That will be the value. Okay. Instead of 4, let's try 5 in the range. Instead of 5. Now let me explain 7. Okay, now we have a node 7. So what will I do? First, any value, you will compare it with the root or the starting node. So in any tree, you will have only one root node. So this is very important for you. 1. Okay. So this is the most important thing. You can only have one root node at any point in time. So now let's say you have the number 7. So I'll go to the root node and I will check the root node's value. Is it? I'll compare the current node with the root node. Okay, is the current node less than that of the root node or greater than that of the root node? The value 7, is it less than 3 or greater than 3? Greater. So I'll go to the right subtree. So when I went to the right child of 3, what is the node which I'm meeting? I'm meeting 4. And now again, I have to compare this value 7 with this node. So this node, I will check whether the value 7, is it less than that of the 4 or greater than that of 4. Okay. Yeah, it is greater. So I will put 7 to the right of 4. We will put 7 at 4's right. Good. Now, I got a now I'm trying to insert a number called 2. Where will 2 go? And you should also tell me how did you compare. Got it? Okay, now let us go to the implementation part. Okay. Now, are you good? Why? Okay, now you understood how will you represent a class node, right? A node at any point will have data, left node and right node. Okay, and you know why we have this constructor. Why do we have constructor? Like in stack, queues, everywhere we had constructors. Here also we have constructor where you have the data and the value you will put there. Right node will be null and left node will be null. Okay, now binary search tree. I mean, in a binary search tree, you will have multiple nodes, but there will be only one root node. So in the search tree, you are defining a good surrender it is for initializing constructor. Okay, root is in node root, you will have, I mean, binary search tree, no? This always keeps the root node handy because at any point when you get a new value, what will you do? You will compare with the root and then with its corresponding child, either left or right, based on the value. Correct? That fall into. So this search tree is needed to maintain the head node or the root node. Okay, root node. And then when you start initializing, initially the root will be null. Now, let us go to the insertion concept, right? So, now all this time we were, so I mean, like queues and stacks like yesterday we did. Now also you did, right? When I said, can you give me what are the children, can you represent node 3, which is a root? What did you do? It has value, which is int data, value is equal to 3. And its left child is what? What was the left child of the root node? So you had taken that, and what is the right child of the root node? You had taken that, right? Now, so at a node, every node in a tree will have its value, left child, and right child. And the left child, it can have either one child, or it can have both the childs, or it can have zero childs. If it has zero child, it is called as what node? Please guys answer. Leaf node. Yes. Okay, so you understood why we had three important properties of the class node, correct? One value to represent itself, and then the left child, and then the right child. Okay. And in the constructor, why do you use constructor? Constructor is to initialize the values, right? So you will initialize its ID, and you will initialize what would be its left child and what would be its right child. Got it? Now you understood the representation of class node. So now you have a node representation, but at any point in time, to insert or to traverse, you need root node handy. Correct? Correct? Because you can have any number of nodes, but you can reach all nodes from the root node. So what is the main node which you want always to have it with you for any calculation, for any traversal or any identification? That is root node. So I'm creating a class called binary search tree, and I'm putting the node root. Initially, my tree is empty, so I'm initializing it with null. Can I move to the next slide? So root is like head and linked list. Yeah, linked list is more flat. It is always connected with one node, max. But tree is something like it is hierarchical. Correct? You can have 0 children, 1 child, or 2 children. Correct? So that is why you go, when you wanted an additional connectivity, you went for tree. And by what is a binary tree? At any level, you will have maximum of 2 children throughout the tree. Okay. And what is a binary search tree, guys? Supal, it cannot have more than 2 children. It can only have at most 2. It can either have children or not, but it can be a leaf node, but it will only have 2 child. Okay. Now, what is a binary search tree? Ideal tree is a more organized tree. Okay, we'll go on to the balancing of trees later, but we can continue. What is a binary search tree? At any given level, the children in the left subtree will be less than that of the root, and the children in the right subtree will be greater than that of the root. Okay, now let's go and write an algorithm. So the algorithm for what? So all these time we were doing it at the whiteboard, right? Whenever you get a node, what happens? So that is what we are going to see here, right? So when you get the first node, what happens? It goes here and it tries to insert into the tree. So what is the first node it will compare? It will compare with the root node. In this case, the root is null. So what will you do? You will just create a node with value of whatever root node value, and then you will come out. Correct? If root is null, you will just return a node which contains only value. Let's say I'm creating a tree with root value as 3, then my root node will be 3 and it will not have any left and right children, so it will come out. Now, let's say now the next element 4 gets it. So when it goes 4, it will compare with the root. If 4 is less than 3, then you will insert it into the left subtree, right? Now the new value 4, if it is greater than the root, then you will insert it into the right subtree. Okay, and you will return this element. Okay, got it? So that is what it is happening. So now let's say now you have 3, 4. Now let's then get this. Okay, so you have a node. What did I say? Now I have an so you know at any point in time you will have a node with value. Initially, I don't have a tree at all. So my value is null. My left and right child, everything is null here. So now what I'm doing, I'm telling I'm giving a root node as well. So what will happen? You take the value 4 in the argument with root node as null. So what will you compare? If root is null, what will you do? the root itself is null. So what will you do? You will create a new node and insert the value as 4, and the left and right child will be null because you don't have any left child and right child, correct? So this will be null and you will return this 4 as the root node. Now let's say in the next node 7 comes. So when 7 comes, what does it compare first with? It will compare with 4. And 7 is greater than that of the root node 4. So I can go and insert it into the right subtree. So I'll go to the right subtree. My right is empty. So I will point this roots right. This will not be null. It will become the new node 7 and it will have its children null. Got it, guys? Now let's say another element 9 comes in. So what will I do? Now 4 has 7. Now another element 9 comes in. So when 9 comes in, you will compare it with the root and 9 is greater than 4. Correct? 9 is greater than 4. Then you will put it on the, try to put it on the right subchild of 4. What is the right subchild of 4? It will return 7. So when you get 7, you got 7 here. So when you get 7, you will compare this 9 with 7. And what is it? 9 is greater than 7. So 9 should always appear on the right subtree. Now my right is null. So I will make 9 as my right child. So at any point in time, you will iterate and find out what is the ideal position where I can put this value. So that recursive search, right, is what is explained in this code. Okay, I lost Kunal, so we'll move further. So this is what is happening here, guys. If you see here, you're doing an insert and you're comparing with the root node. If the root is null, you are creating a new node. If not, you are comparing root, if the root is not null, what you're going, you're comparing it against the root's data and you're checking if the data is less than the root value, then you can put it in the left. Otherwise, you will put it in the right. So root's left will be, you will again do a recursive search to find within the subtree, right? At every level, you will run the same thing again and again. So that is what this insertion method does. Now, you know what is the important node in a tree? Now you know how to insert. Now, what is the next step? How will you traverse? Traverse means how will you identify or iterate and find out all the elements in the tree from the root? Correct. So, there are 3 ways of traversing. Traversing means you are visiting every node in the tree. Okay, traversal means you are going to visit every node in a tree. Okay, so there are 3 ways of traversing from the root. Okay, so the 3 important ways, all these traverses I will teach you. First one is in order traverses. Okay, first one is called in order traversal. Okay. So now let's say I have a node A and my left child. Okay, this is quite confusing for you, right? Let us go with numbers because we have seen binary search tree. So we will start. There is a number called 12 and the left child is, so the left child value should be, yes, less than that of the parent. Okay, parent in this case is 12. So left child, let me put 9 here and let us put 20 here. Okay. And what is the left of the 7 is the left child. And let us say I'm getting an element called 10. 10 would be the right child. Okay, now let's say we have to put another left child. So where I can put the left child of 20. Fastest finger first. So what is the fastest finger? Can 4 be the right child of 12 and left child of 20? Tina, she likes 17, so I'll put 17. So let's see who's the winner. Ash. Okay, 22. Okay, now let us, from the root node, I should visit all nodes in the tree. 1 crore winner. Okay, happy to know. So from the root node, I have to visit all nodes in a tree. Okay, so how would you traverse? So this is in order traversal. In order traversal means you have to traverse it in order. So that is called, ma'am, can we have more than one leaf? You can have any number of leaf nodes as long as they stay connected in the graph, in the tree. Okay. So how many leaf nodes? Maximum leaf nodes, I'm telling after the first traversal. So at any levels, how many leaf nodes you can have? At any levels, if you have any node, it can have maximum 2 child. Okay. So if you start here, the maximum which this element can have is 2 power 0 because it is in the first level, which means it can have maximum 1 node in this level. Here 2 power 1 because it is in the level 1, so it can have 2 child. This is in the second level, so 2 square, it can maximum have 4 nodes, 4 leaf nodes. Similarly, as you traverse down, you can get to know how many leaf nodes you can have. If I delete 7, you will have 3 leaf nodes. There is no restriction like I should have only 1, 2, or like that. But the maximum number of nodes at any given level is the 2 to the power of the level of the current node. It's not into, it is 2 to the power of the level of the node. At what level the node is. That whether there can be more than one leaf nodes. So what I mentioned was there is no such. It goes in the power 2 power of n. Okay, at any level it goes to the 2 power of n. Maximum it can have 2 power of n. It can be 0 also. It can be anywhere ranging from 0 to 2 to the power of level of the node. Okay, let us not confuse with the level at the moment. Okay, now in order traversal means you will traverse it in order, which means the element should be sorted and it comes. So if it has to be sorted, which will be the first element? So you have to always take the left child and then the root node and then the right child. Okay, left, root, right. Okay, in order means left, root, right. So in order means you will always print the left child and then the root and then the right child. Okay, now what is the important node in the tree, which is the root node? You should always start traversing from the root node, correct? At any point in time, you will get and handle only to the root node. Okay, so you always start from 12. Okay, so what is the rule here? You should display the left child first. So what is the left child of 12? Node 9. Correct. So node 9 is your left child. Now I go to the node 9. Now this acts as a parent. What is the ground rule of your in-order traversal? Left child first. So that applies to every node. So to the node 7 also this rule applies and it goes and finds the left node. So what is the left node of node 9, guys? Node 7. Okay. So to the node 7 also again this rule applies. Left child. What is the left child of node 7? Null. Unfortunately, you don't have any data. So you will not print null, you will skip it. And then what is the second one? First is left and then the root. For the node 7, it acts as the root node. So 7 will be printed first. Okay. Does 7 have any right child, guys? Does 7 have? No. So the next rule is left, root, right. So no right child. So you will not print anything. And now the traversal goes. So the 9 was waiting for all its left children to be printed. And after that, it will print itself. So what is the ground rule? You finish processing of all the left nodes and then print your value, which is 9. Now after that, what it has to do? It has to print the right node, which is 10. So you got it? How you are printing 7, 9, 10? Okay, and once the 7, 9, 10 is printed, it returns back to the root node 12. So for 12, the left has been processed. So it will insert its value 12. Yes or no, please? So it will print the value 12. And after it is printing 12, what is the thing left is done? It has printed itself. So 7, 9, 10, 12. Okay. Well, so its job is done. Then it goes to the right child. At every node, what property is applied? Left, root, and then right. So 20 goes and scans its left child. What is it? 17. 17 goes and scans its left child. It doesn't have any. What is then it has to print itself. So after 12, you print 17. And after 17, you look for the right child. There is unfortunately no. So again, the control goes back to the parent node 20 here. It has done its job of scanning all the left children. So it will print itself. So 20 gets printed. And after 20 gets printed, it goes and scans its right child. It has 22. It will print itself. 22 does not have any children, left or right child. So 22 will print itself. And then it goes back and returns the control to the root node. The root node says, I'm happy, I'm done with all the processing. So are you good with the in-order traversal, guys? Now tell me, what is the rule of in-order traversal? Left, root, and then right. Okay. Can we move on to the code? And then we'll move on to the coding part. Move on to the PPT again. Okay, now here, instead of the numbers, they've given alphabets. Can you traverse this tree and tell me the order? Okay, D, B, E, F, C, G. Okay. Okay, we'll move on to the coding part of in-order traversal, and then I'll teach every traversal, and then we can move to the coding part of it. Okay, so now you know the structure of this binary tree, right? It has its own ID, data, and left node and right node. Correct. Now let us go to the implementation of it. So let us move on to the traversal. Okay. So for any given node, if the node is not null, what will you do? You will have to go and find out whether it has a left child. Okay. And once, if it doesn't, you will print all the left, you will traverse and you will print all the left child first, and then the root, and then the right. So once you get, let's say we have the root node has come here. Okay. Should we print the root node? Should you print the nodes data? What is in-order traversal? Guys, please. I want you to answer what is in-order traversal. How do you traverse? Left, root, right. Okay, now at any point in time, what is the first node which you will take to traverse or to insert? So at any point, you will take the root node. So using the root node, can I print the root node first? Yes or no? So I will go and traverse until I find the null left node. Okay. Once if I find the left node which is null, which means I don't have anyone left on the left, then I will print my data, and then I will go and find out if there is anyone on my right. And for the right, again, you will do the same thing. For the right node, you will again go and check whether it has left node. Okay. Oh, and then if it doesn't have a left node, it will print itself. And then it will again go and traverse for the right node. So did you understand the first 4 blocks here? Did you understand this? Now let's say we have a tree. Okay. 4, 5, 6, 7. Okay, now I got this. This is my tree. So what I'm doing here, what is the rule? You will always get an handle to the root node. From the root node, what will you do? You will go and iterate and find all its left child, and after that only you will print its data, and then you will iterate the right child. At every given step, what is your rule? You have to go and find out its left child. Now you got the handle to 4. So what is the left child of 4? Which is 5. So again, For this node, what will you do? You will go and find its left child. Unfortunately, it doesn't have any left child. So what is the next step? Okay, now tell me what is the next step. For the node 5, I went and found there are no left child. So what will I do? You will print the right data, good Anjali, and you will move on to the right node. Does 5 have any right node? Didn't write a binary search tree, right? So please consider this as a search. Okay, I'll give another example. Didn't quite get this code. So we clear this and then perfect. It's not keyboard. Okay, so these are the students. Okay, now this is fine, right? Now let me explain this code with this example. Okay, now you are given with an handle of node 10. Okay, now the node is not equal to null. You have to go and traverse and find out its left child. So what is the left child of a node? So we are doing this first step here. Okay, left child is 7. So what they are doing? They are asking you to traverse its traverse. I mean, this is called recursion. You are calling this function again by passing 7 as the root node now. Correct. Now again, 7 is coming here. So what is the job of 7 here? This is again a node. It has to go and find out whether it has a left child. So the node is not null. It goes and traverses to find whether it has any left child or not. So it will pass nodes left. What is 7's left? Null. Okay, when you do a traversal, when you do node not equal to null, this is not true. So it will go and come out. And what is the next step in the now node 7 has finished the traversing, correct? It will print the data 7. Okay. And then what is the next step? It has printed 7. Now 7 got printed for you. I'm writing at the bottom. 7 got printed for you. What is the next step? It has to go and traverse the right child. So what is the right child here? 9. So it is asking go and traverse with the root as 9. So 9 took charge now. And what does 9 do? 9 is not null. So it goes and scans its left child. So 9 delegates the job to the left child, go and traverse. Now because it goes and checks the 9's left is null. So the first condition is not satisfied. So it will come back in the loop. And what is the job of 9 now? To print the value. So 9 gets printed. And then it goes and traverses the right child of 9. So right child of 9 is null again. So null means do nothing, he will come out and the handle will be returned to the node. So now 7 did its job of scanning the right child also. So 7 returns the handle back to the calling node 10. So what is the job of 10 now? 10 has finished scanning all the left child. So it will print itself. So 10 has printed itself and it delegates the job to 15 to scan and so on. So what will be the output after scanning? Can you all type the output for this tree? I mean, I want the output for this entire tree. It is 7, 9, 10, 12, 15 and 17. Okay, good. Okay, let's go to pre-order traversal. So on the whiteboard, now what are we going to do? Pre-order traversal. Okay, so pre-order. Okay, so what is the important node in your binary tree or a binary search tree? Root node, right? So so the root is printed first, and then you go to the left node, and then you go to the right node. This is called pre-order traversal. Okay, earlier what did we do? What is in-order traversal? What is LRR? Maybe after dinner. Okay, so now in pre-order traversal, the concept is same, that but it will print the root first, and then it will scan the left child, and then it will scan the right child. Got it? Now let's move on. Let's consider a tree. Well, left child is 9, right child is 17, and the left of is at 7, and the Right of it as 9. I'm going to put 14 here, and then I'm going to put 20 here. Okay, guys. Now let us. So, what is pre-order? Pre means you will give priority to root first. Okay, root, and then you traverse the left child, and then you traverse the right child. So, print the root first. So now in this tree, what will be printed first in pre-order traversal? 12, correct, because 12 is the root. Print the root first, and then what is your next job? Traverse the left child. So now the handle is written to the left child. Here also the same thing applies. What? Print the root first. So what is the root value which has to be printed now? And 9 is printed, and what is its job? Now it has to traverse its left child. What is the left child? 7. So the control goes to 7. So what will happen? 7 also follows the same protocol. It prints 7, and it goes and finds its left child. The left child is null. So it will come back. And what is the next protocol? You have to scan your right child. Right is also null. So it will keep quiet. And then the control is sent forward to 9 again. From the node 9, it has printed the root, it has traversed the ref child. What is the next job of 9? Yes, find the right child of 9. What is the right child of 9? Node 11. So the control goes to 11. 11 also follows the same protocol. Print the node's value first, and then find the left and right child. Unfortunately, 7 does not have left and right child. Correct. And then what happens? So 11's job is over. It goes back at 9 to 9 and says my job is over. 9's job is also over. So it returns the handle to 12. 12 has printed itself, scanned its left child, so we go to the right child. So now what happens? The control is given to 17. 17 follows the same protocol. It goes and prints the root node, which is 17, and then it scans the left element. So left child is 14. 14 follows the same protocol, prints itself, scans for the children. It doesn't have any, so it returns back to 17. 17 has printed itself, scanned all the left children. It goes to the right, and right follows the same protocol, print itself, scan the children. Now, if we have to write a program for this, how will you write? So what is the first step? You have root here. Root here. So what is the first step? What will you do? So what is the first step? What is the protocol in pre-order traversal? Print data first, right? So print root dot data, roots data. And what is the second step? This is pre-order. Okay. So you do so what is the second step after printing itself? You do a traversal of roots left. And then what is the next step? After you finish the traversal of left, what will you do? Roots right. Good. So you will go and do a pre-order traversal because you have to follow the same protocol. Roots right. So when will you do all this? You can do all this when the given node is not equal to null. So you will check whether the node is not equal to null before doing all this. So now, can you all type what is in-order traversal and what is pre-order traversal, please? In-order is left, root, right. Pre-order is root, left, right. Good, sir. Pre-order is root, left, right. Okay. Now let us move on to the concept called post order. Can you guess what a post order could be? If you know the pre-order, what could be the post order? Pre or post, everything relies on the root node. So post order means you will scan all the left child and the right child, and only after you do all that, you will print the data. So this is called post order traversal. Left, root, and then right. Okay. Now, because you know all this, I want you to give me the answer for this tree. Yes, first you have to traverse the left node. So what is the condition here? Traverse left, traverse right, print root. Correct. This is the condition. So when I get the control of node 19, which is the root, I have to go and traverse the left. Left is 15. Again 15, when the control goes to 15, 15 also follows the same protocol, traverse left. So 12 goes. Now you got the control over 12, and 12 also follows the same protocol, traverse left. The node is null. So traverse right, the node is also null. So you will print the root 12. Now control goes to 15. 15 has done traversing left. It has to do the traversal of right. So what it happens? 17. 17 also follows the same protocol. Traverse left, no, empty. Traverse right, empty. So print 17. So 12, 17, and then 15 has finished its job of traversing left and right, so it will print itself. Now the control goes to 19. 19 has done with traversing left, it has to traverse the right. And when it goes to the right, it will go and check whether it will go to the 25th node, and 25 also follows the same protocol, traverse left. So it goes to 23. 23 follows the protocol left, right, which is empty. So it prints itself after traversing. And after that, you find out the control is reached to node 25, and 25 traverses to the right. So it prints 27 because it doesn't have both the children. And then control returns over 25. 25 does its job. So it will print itself. And then control goes to 19. 19 did the traversal of left and right. So it will print 19. So the answer is 12, 17, 15, 23, 27, 25, and 19. I want you to write the code for this one now. Okay, now let us go to this pre-order traversal, guys. So in pre-order traversal, what will you do? First condition is the node should not be null. Pre-order means root should be printed first. So print the data and then traverse the left node and right node iteratively. So this is called recursion. I think now many of you guys understood what recursion. Recursion means calling the function by itself. If you see pre-order traversal, it is calling itself with different values until a condition is reached. What is the condition? Root should not be null. Okay, so this is called recursion. So now we have covered recursion also. So for whomever you don't know what a recursion means calling the method by itself until a base condition is reached. So what is the base condition? Node should not be equal to null. Okay, now let us move on to post-order traversal. Okay, now let us go to the post-order traversal. So what is the post-order traversal? It's again the same. What will you do? You will post. Post means root should be printed at the end after traversing left and right child. So what will you do? You will if the node is not equal to null, you will traverse the left child and then you will traverse the right child, and after that you will print the data. So this is again a recursion because you are calling the method by itself until the node is not equal to null.
Just a quick info, guys. Intellipaat offers a full stack web developer course in collaboration with iHub IIT Roorkee. Through this course, you'll learn tech stack like MongoDB, Express.js, Angular, Node.js, along with HTML, CSS, JavaScript, and more from the IIT faculty. With this course, we've already helped thousands of professionals transition into high-paying developer roles. You can check out the success stories on our Achievers channel, whose link is given in the description below. No doubt this course can take your career to new heights. So check out the course page link in the description and take the first step towards becoming a certified full-stack web developer.
Now, graphs. So what are graphs? Okay, I'll tell you. You know tree. Tree is a flat structure, right? Quite familiar with trees, right? What is a tree? Tree will follow a flat structure like similar to the organization hierarchy. But there are some use cases where every node gets connected and forms a cycle, okay? In those cases, we need to have a cyclic connection kind of a data structure. So graph is similar, the one which caters it. Okay, it can have any number of child and it can get connected. Okay, so there are two main important things for a graph. One is the vertex. Okay, so this is my vertex V1, V2, or these are called vertices V3, V4, V5. Okay, like every product has product ID, every vertices has its own ID. Now, so in graph, there are two important concepts. One is this vertices and the other one is called edges. What is that? Edges. Edge is the one which connects two vertices, which says whether this vertex is connected to other ones or particular edge has an arrow which says the connection is unidirectional, which means okay, you didn't get this. So first thing in a graph, what is important? Vertex, correct? I told you in graph there are two important things. One is vertex, okay, and group of vertex are called vertices, and the other one is edges. So this brown color line, this is called edge. Okay, so this is edge. So how are the vertices getting linked with each other, linked to each other? So they are getting linked to each other using edges. Okay, or the relationship between the vertices are identified using edges. Okay, in graph, the most important concept is vertex and edges. Okay, now if you see this graph and the another nearby graph, so the only difference which you can see, this is arrow mark which says the direction of the connectivity between vertices. Here the vertex V1 and V2 is connected using a arrow, okay, which says from V1 I can reach to V2. Okay, but there is no another direction showing from V2 I can reach to V1. Okay, it is only unidirectional connection and it is called, we name the vertex V1, V2 to ourselves, or it is like that only. I mean, vertex can be anything, like in your tree, how did you identify every node? With node ID. Okay, node ID. So every object will have its own ID and it has its value, right? Similarly, in the graph also, you will have numbers 1, 2, 3, 4, 5. Okay, and so every node is called as a vertex. For your understanding, I'm numbering like V1, V2, V3. Okay, but in reality, you will have like in tree, what did you have? So what are the properties of trees which you did? Tree has value, correct. And what else did you have in a tree? Left pointer indicating the left child and you had a right child, right? Similarly, in graph, you will have a value and you will also have now what all vertices this particular vertex is connected to. Okay, there is no rule like V1 should be greater than V2, V2 should be greater than V3. So there is no such rules at all. Okay, there is no rule like V1, this is my first vertex, it should be less than 2. This is my third vertex, it should be greater. There is no such rule. It is all connectivity. Okay, let's say, okay, I'll give you a practical example of this one. Let's say I'm going from any two places. Let's say I'm going from Chennai to Delhi. Okay, or Delhi to Bangalore. Okay, let's say I'm going from Chennai to Delhi. So in between, there is something called Bombay. So how am I going to Delhi? From Chennai, I go to Bombay and I go to Delhi. There is no rule that Chennai should be a smaller city and Bombay should be bigger than Chennai and Delhi should be bigger than Bombay. There is no such thing. Okay, got it? So this is called graph. And why there are unidirectional lines? So you have a flight which goes to Delhi but it has a transit in Bombay and then it reaches Delhi. So what is the total time taken for a person to reach from Chennai to Delhi? It is the time taken for him to travel from Chennai to Bombay plus the time taken for him to travel from Bombay to Delhi. Correct. So for identifying the shortest path, shortest route, and all such things, we make use of graph. So that is graph. There is no ground rule like Chennai should be here, Delhi should be there, and all. So, like our location, which is getting calculated, all that thing is done using graph. Even your Facebook page, right? You are a person, and you have a friend, and you have and friend. There is another friend which is linked to your friend. So how the connection goes? So he's your second connection, third connection. How did Facebook identify or LinkedIn identify the link the connections and list you with friend suggestions? All that is using graph. Okay, yeah, even the mutual connections. So every person will have the ID, and once you are connected to the other person directly, then it is called mutual connection. So this one here, in this case, vertex 1, 2, and let's name him 3. So vertex 1 has mutual friends 2 and 3, but vertex 1 has an indirect friend or a second level connection for social media identify how the connection happens. Now coming to the directed graph. The relationship is always one way. Like you're following a person, right? Which means you are following. Now let's say this is a guy. F is a big boss, or let's say he's a leader or someone. He is followed by so many people. Okay, so all his feeds are shared with these people 1 and 2. But when you see the person 1 is he's listening to the feeds of this big boss F, but the boss is not listening to the feed of this guy 1 because it is not important to him. So that becomes directed graph. Like you have an Instagram, right? If you don't follow someone, you will not get their feeds. But you will allow everyone to this big boss. He's accepting everyone's follow links, and he's telling the person 1 and 2 can read his feeds. Okay, but I am not going to follow them, so I will not read the feeds of the boss, will not read the feeds of 1 and 2. So this is an example of connected graph, directed graph. Okay, not that a graph is always connected. I mean, it can be connected or it cannot be connected. That is altogether a different story. But this is the story behind directed graph. Are you hearing any echo? So, are you clear with the directed graph, guys? Please explain the connections of directed graph again. Okay. Now let us go to the undirected graph. Undirected graph. Graph means you will have vertex and edges. That is all common. Okay, now let me rename, name the vertices 1, 2, 3, 4, 5. Okay, it can be of any order. There is no rule like binary search tree and so on. Directional graph means you can see this arrow, no? It says a node can reach another node, but not vice versa. Node A can reach node B in this case, or node F in this case, but node F cannot reach node A. The connection is not, it's like a one-way route. You can travel only in one direction. Yes, it is like a one-way route. If you go, you cannot have two ways. So from A, you can only reach F. From F, there is no road to go other way. Okay, but in undirected graph, it is like our normal 2 lanes road. From A, you can travel to B. From B, you can travel to A. So there is no direction here. How in linked list, how two nodes are connected using next pointer. Likewise, can we have a next pointer for a graph? But to clarify him, now A can connect with F. Let's say, okay, now you have a node A, B, C, D, E. Correct? Yeah, directed means one-sided, but undirectional means it is mutual. It can be connected both the ways. Okay. So now, in linked list, how will you say from A you can reach B? You will have a pointer from A which reaches B. Now, let's say my graph from A, I will reach B, I will reach C. From A, I will reach D. So what happens? You will have to create so many next nodes, right? Node 1, node 2, node 3, node 4, it becomes clumsy, correct? So what is the coolest way of handling that? You can create an adjacency graph. Okay, I'll teach you how to create one. Okay, we'll try that adjacency graph first. Now I'm creating so many vertices A, B, C, D, E. Let us go with the undirected graph now. Let us not keep any directions for time being. Let us create a undirected graph now. Now, let us define this node A. Node A has value A, correct? So this has a value A. Now, what is the other thing which we have to know? From A, what all nodes can you reach, right? So for that, let us draw this graph. From A, I can reach A. Okay, A to A is always possible. Okay, B, C, D, E, correct? From A, I can always reach A. So I'll put 1. From this graph, can you reach from A to B? Yes, right? So I'll put 1, which means the connection is true. I can establish a connection. From A to C, can you reach from A to C directly? No. So I'll put 0. From A, can I reach D? From A, can I reach D? Yes, I'll put 1. From A, can I reach E directly? No. So I'll put 0. So for my node A, what I want to know is list of nodes which I can connect from A, correct? So for any node, I can have one value, and I will also have the list of adjacent nodes that can be reachable via me. Okay, so what all nodes will be in the list of node A? So from this graph, if you see, A can reach A, so you need not add yourself directly. So what are the other nodes you can reach? You can reach B, you can reach D. Okay, so now instead of next pointer here, you will always have list of adjacent nodes which you can reach. Okay, now can you fulfill the adjacency matrix for the node B? From B, can you reach A? Yes. Why can you reach A? Because there is no direction mentioned here. It is not a directional graph. It is undirected graph, which means two-way road. You can go towards B or you can go towards A as well. Okay, so from B you can reach A. B to B is always 1 because B is already there. You're already there, so you have reached. From B to C. From B can you reach C? Yes. From B, can you reach D? No, I cannot reach D directly. Can I reach E? Yes. Now, can you guys form the adjacent B's node structure with value and the list of adjacent nodes? Yes. So the value is B and my list will have nodes A, C, and E. Now, likewise, you have to frame the adjacency matrix of everything. Now, did you get any vague idea like how this data structure is getting represented? If you know this, you're good at basics. Okay. Okay, from this, okay, now for this graph, can you give me an adjacency matrix for node A? For node A, I want this list of nodes that can be connected via A. Can you form the matrix? From A, you can only reach B, the rest are 0. So can you form an adjacency matrix? I will type it in a notepad and I'll send it across so that guys, whoever has time, create the matrix for the entire graph and let me know. So I want you to frame an adjacency matrix for this graph and paste it here. Not like this, the way I did. Like from A, you make A, B, C, D, E, and 1, 0. That kind of matrix, can you make it and paste it here? So a small exercise to keep us active. Not for undirected graph, for this particular graph. Is this directed or undirected? For this directed graph, I want the adjacency matrix. Yes, here direction matters. You see an arrow, right? Which means it is a directed graph. Direction, it is a one-way road. You cannot go both the ways. Okay, now let us come to the search. Now, see, there are, you see on LinkedIn, Facebook, Instagrams, and so on, right? And the moment you search any person, your first connection comes up first. The names which matches to the your first connection comes, and then the two first level connection, second level connection, third level connection. So how does it come? Okay, so and for all this search to work, you need an algorithm, right? So the easiest way to connect. So for that, there are two ways of iterating and finding whether a person exists or not. Okay, one is called depth first search, and the other one is called breadth first search. These are very important topics. Most of your graph questions will only be on this depth first search. Mostly you'll get depth first search, and few will be on breadth first. But these are the most important traversals. First is like your depth first search. So depth first search means you will start with the root node and you will reach as bottom as possible. So this is called depth first search. You will go deep down. You will dig your connections to connections. So the moment you go to one connection, you will dig deep into his connections and go down. So this is called depth first search. You're going in deep of every connection until you find that particular person is present or not. Now let's say you're searching for an node called 4, for a vertex called 4. So what happens? So when you do a depth first search, one will go, so there is this node 1. So now this will have adjacent nodes, right? Or your adjacency matrix. So one's adjacent matrix will be 2 and 5, correct? Because from 1 you can reach 2 and you can reach 5. So what will 1 do? 1 will iterate all its adjacent nodes and it will pick the first node. So let's say 2. And what it does, it goes again and it tries to find its adjacent nodes and go on. It goes on until it finds them. And let's say if it is not able to find. So now what does 1 do? 1, although has 2 and 5, it took the first element 2, and from 2, it is going further down, right? It is calling this same thing again. So 2, what will 2 do? 2 will list down its adjacency matrix. So what does 2 have? 3 and 4, correct? Now what happens? So 2 will pick 3. Okay, I'm seeing some comments. So let me answer those. DFS, BFS 1 to 4S. And now 2. So you got it right. First you'll pick a node which is 1. So you will list down all its neighbors, which is 2 and 5. And what will you do? You will go and dig your first neighbor first. So now I picked 2. So what will happen when you pick 2? It will go and dig. It will go and find out what all neighbors it has, 3 and 4. And it will pick the first neighbor and it will go and check 3 now. So what does 3 do? 3 will go and it will list down its neighbors. No, it doesn't have any neighbors, right? So it doesn't have any neighbors. It means it cannot dig down further. It would have compared whether the value which we are searching here, the value which you are searching is 4. So 3 is equal to 4 or not? No, it is not equal to 4 and it does not have any further neighbors. So it will come out and return the control to 2. 2 already has searched, 2 is not equal to 4. It went to 3 and 3 also didn't find any. So 2 will pick the next element 4. Okay, now 4 comes. Now the value which you are searching is 4 and the node's current value is 4, which means you will return true. Oh, you got this element, I'm returning 4 to you now. So now what happened? You went 1, 2, 3, you didn't find. So what did you do? From 1 to you identified 4 and you formed the path. Okay, this is how it identifies the shortest path using depth first search. Okay, so now can you give me from node 1 I want to reach node 6. So if I'm doing first search, what all nodes would I have visited? 156 is the shortest path, but what all nodes? Okay, 156. There is another way also. Oh, gee, yeah. From 1 you will reach to 2, 2 to 3, and then you will reach 4. You didn't find, and then you will iterate the next adjacent neighbor 5, and then you will reach 6. Okay, now let's take another example. Now tell me what happens in this case. I want to again search for the element 6. Okay, I'm trying to search from 6 and adjacency matrix says of node 1 says 2 and 5. So what will happen here? And here I have established another directional link from 4 to 3. Why not 156? Let's say if in your adjacency matrix, if you have stored 5 first and then 2, then 156 is possible. I'm not telling Aditya 156 is not possible. If in your array list, if you're storing 1 and then so to the one's adjacency matrix, if you're storing 5 comma 2, you will find 5's child first instead of 2's child, because you iterate all the neighbors and go in depth for every neighbor. Okay, so I'm not denying the fact that 156 is not possible. 156 is also not possible. It'll stuck in a loop. What happens? 1, you reach 2, you reach 3. What is from 3? You don't have any other connection, so you reach 4. From 3 to 2, from 2 you go to 4. From 4 again you are going to 3. Again 3 doesn't have neighbor, so it will go back. So this looping continues again and again. So in order to avoid this loop, we have to keep one more matrix which is called visited. Okay, so what will you do in a visited is for every node 1, 2. So how many nodes are there? 4, 5, 6, 7 nodes, right? So you have such a big visited matrix, and first 1 has reached itself. So you have reached 1. So you will enable the flag which is true. You have visited, so you'll enable it as 1, and then you will find the neighbor of adjacency neighbor or the adjacency matrix of 1, which says let's say in this time, let's say I've stored it as 5 comma 2. Okay, so what happens? When you iterate, the first element is 5, so 5 becomes the actual node now. So 5 is visited, so you will put 1. Okay, and then you will go and see the adjacency matrix of 5, which says 6 comma 7. You will pull 6 and you will make it as 1. 6 is equal to 6, so you found 6, you will come out. Now let's say on the other side, I have kept the adjacency matrix as 2 comma 5. Okay, 1 has visited itself, so it becomes true. 1 has visited 2, so it becomes true. And From true adjacency matrix, we got 3. So 3 is visited true. From 3, there is no children or no adjacent neighbors. So the control goes back to 2, and 2 still has one more neighbor to iterate. So the control goes to the 4th node. So the 4th node is visited now. So it becomes 1. And we dig through the neighbors of 4, which is 3. In this case, because 3 is higher, visited already, you will not visit the children of 3 again. Okay, let us go to the implementation. Now, what are the two important properties of two important elements of a graph? Vertex and edges. Now, when you define a graph data structure, so what is the important thing? You should know the vertices and the adjacency matrix. Correct? Yeah, for every vertex, you should get a list of its neighbors. So that is why it is a list of neighbor array. Because if there are 10 vertex, you will have 10 array, and each array will have the list of neighbors. Okay, you want me to use VS Code? Okay, yes. Okay, now we have graph, correct? Now, for any graph, what are the important things? Vertices and edges. So, you want vertices and its adjacency matrix for every element, right? For every vertex. So, that is why you need list of integers or list of neighbors for every vertex, which is represented like this. Are you okay with this? See, a code is a code no matter whether you're running it in Eclipse, VS Code or IntelliJ. You must be flexible. You're learning data structures. So now what is the next step, guys? You have your vertices, you have your adjacent matrix. So what is the next thing which you have to do? You have to initialize your constructor. Initially, you make an empty array list, right? For every node, you don't know what the neighbors are, so you're keeping it empty. Okay. And now, when there is a connectivity between two nodes, you will have to add an edge, right? So we need to create a method that says the connectivity between the nodes. Okay. Now let's say vertex V and W are reachable, then adjacency vertex from V you can reach W. So for V you will add W. This being a directed graph, you will add from V to W alone. If it is an undirected graph, what will you do? Edges are imaginary lines, correct? So that is why you don't specifically mention edge. Because using edges, you're making the adjacency matrix, which is important to us, right? So that's why adjacency matrix of 1, you will add the first node 2, and then you will add the node 3. So that is why, so this is how you are adding the edges. Now, for directed graph, we will only create adjacent vertex. So if you can reach from 1 to 2 in directed graph, it is one-way traffic. You will only add adjacency of V or adjacency of 1 will have W. But if it is undirected graph, you will add both the ways. Which means if it is an undirected graph, you will add both, right? Because it is two-way connection, right? In undirected graph, there will be a lot of loops if you don't have this visited map. Now, let us implement our DFS search. Okay, so while you're doing the DFS search, what is the most important thing to avoid loops? I'll give you a hint. To avoid loops, what is the most important thing which you have to have? I'll put the visited array, and I will also have I'll just print the value which is getting visited just to see. Okay, it's not the answer, but just I want to do some debugging, so I'm just printing the value. And next, what is the next step? Next step is to
visit all your neighbors. Okay, so visit all your neighbors. So you visit your first neighbor and then do it. So this DFS, this algorithm this is printing all the nodes from a given node. Okay, but the example what I taught you was how to search for an element in the graph. Okay, but this example will print all the nodes in the graph using DFS traversal. Next, now our problem. Now there must be someone who should call this DFS, right? Which means from a given node, I need to identify whether I can reach the other node or not, right? So for that, we have a method called DFS traversal. So which will check from the given node whether I can reach the other node or not. Good. Now we have another class called main. From here we are calling this. I'm creating a graph with 5 vertices and I'm telling what all edges it can have. Like from 0 I can reach 1, from 0 I can reach 2, from 1 I can reach 3, from 2 I can reach 3, from 3 I can reach 4. Okay, and I'm going to do a depth first traversal and I'm going to print all the values. Now let us run this code. Okay, and if you see here, I'm printing every visited node here. Okay, and look at this condition, the beauty of this condition here. For every node in the adjacent vertices, I will do a DFS only if that node is not visited. I'll try to delete this. So now if you see this graph from 0, I'm reaching 1. Let us see this example here. Okay, from 0, I'm reaching 1. From 1, I'm reaching 3. From 3, I'm reaching 4. Okay, and 4 does not have any adjacent matrix. So it traces back to 3. 3 doesn't have any adjacent matrix. So it goes back to 2. 2 and it prints 2. Okay, from 0 to 1 it goes. From 1 to 3 it goes. From 3 to 4 it goes. Okay, 3 is visited and 1 is 3 does not have any further levels, right? 4 is already visited. And it goes back to 1 and 1 doesn't have any neighbors. It goes back to 0. 0 has next neighbor 2, so 2 gets printed. I'll make a graph for you so that you will understand it better. Okay, from 0 you can reach 1, correct? From 0 you can reach 2. From 1 you can reach 3. From 2 you can reach 3. From 3 you can reach 4. So when you do a depth first traversal, from 0's first neighbor is 4, right? From 0 you will go to 0's first neighbor is 2. So from 0 you will go to 0's first neighbor is 1. If you see here 0, 1. So 0's first neighbor is 1. So from 0 you will go to 1. From 1 you will go to 3. From 3 you will go to 4. 4 does not have any neighbors. Control reaches to 3. 3 does not have anyone else other than 4. So it goes back to 1. 1 does not have anyone other than 3. 3 is already visited. We just visited, right? So the control goes back to 0 and 0 prints 2. Okay, now I'll show you what the edge method. Edge method does nothing but it will populate your adjacency matrix. So when you do adjacent of 0, you'll get a linked list, right? You will add this vertex to that list. Like you are adding all the neighbors to the list of the vertex. Okay, now let us go to breadth first search. Okay, in the depth first search, from 1, you digged all the nodes within the node. Correct. Okay, from 1 it reaches to, and now, okay, now you all read about depth first search, right? Depth first search, you will dig down. Okay, no problem, Anshu. Now, in breadth first search, what you will do, once I visit node 1, I will visit 2, I will visit all the adjacent neighbors of this node before digging further. This is called breadth. So, level wise, you are traversing the first level, the second level you are traversing, and then you are traversing the third, fourth, and so on. This level order traversal is called the breadth first search. Now I want you to print the output of both DFS and BFS for this graph. So whoever has typed S and whoever is listening will do the DFS and BFS for this graph. Both depth first search and breadth first search. In the depth first search, what will we do? You need not find any element, Anjali. You just traverse. In depth first search, what happens? From 1, it will go to 2. From 2, it will go to 4. And then it will print 5. It will go to 5. And then it will go to 3. From 3, it will go to 6. And then it will print 7. Correct. Printed first. It is in the first level. Next, the neighbors of 1, 2, and 3 will get printed. And after that, 4, 5, 6, 7. So it goes this breadth wise, level wise. Can you print, can you tell me what is the output if you do BFS for this? Breadth first search is level order traversal. So 1 is in the first level, so 1 gets printed. What is on the second level? 2 and 3. So 2 and 3 will get printed. Shubham, what is in the last level, third level? Now let us see how will we implement this. Okay, I'll give you an example here so that it will be easy for you to understand. Okay, now what happens is for breadth first search, you will use a data structure called queue. What is queue? Queue is, answer guys, what is queue? Yes, first and first out. Okay, now let's see how we are going to print the values. Okay, and so what will happen the moment you visit a node, you will put that in the queue. So the 1 will be in the queue. Okay, in the queue, you are putting 1. And until queue is empty, you will iterate through every element in the queue. So this will be repeated. Okay, you will repeat for every element in the queue. Here, the queue is not, until the queue is not equal to null, you will implement, you will iterate this method, all this. So what will you do? You will pop the element or dequeue the element and you got 1 now. Correct. So what will you do? You will dequeue. This is your first step. So once you dequeue here, 1 comes out. And what will you do? You will put all the child's elements of 1 or so see everywhere you have this adjacency matrix, right? So whatever adjacency matrix you have, you will push it to the queue now. So now you have popped 1 out of the queue or you have taken 1 out of the queue. The queue is empty now. Can you tell me the second step is add adjacent elements to. So what all elements will go into the queue? 2 and 3. Okay, so I have added 2 and 3. Okay, and now, so whenever you do a dequeue, you will print the value. Here, I will print it. Okay, I'll print. So what is printed now? 1 is printed. Okay, now, and you have added 2 and 3 to the queue. Is queue null now? Is queue null? No, queue has 2 and 3, right? Now, when you do dequeue, which element comes out? When you do a dequeue, which elements comes out? 1 is over. See, initially the first node you will put into the queue and you have taken it out and you have inserted, you have dequeued, you have printed 1.
So 1 went out and you have put 2 and 3 into the queue. And now which element will come? 2 is inserted first, so 2 will come out, not 1. So 2 will come out. So 2 will come out. Okay, once 2 comes out, you will print 2. Okay, and you will push all the adjacent elements of 2 into the queue. So what gets added? 4 and 5 gets added. Okay, now again you will check q is not equal to null. Which element gets dequeued now? 4, exactly. So now you will dequeue 4, you will print 4, and you will add all the sorry, which one will you dequeue? It is 3, it is not 4. Q is always first and first out. So you will dequeue 3 and you will print 3, not 4. Okay, guys, not 4. You will print 3 and then you will add the adjacent elements of 3 into the queue. So when queue, always insertion happens at the end. So 6 and 7 gets added to the queue. Okay, and now 3 is dequeued, right? So cross it out. Now what is in the front of the queue? 4. The queue is not equal to null. You will remove 4. You will print 4 now. I have removed 4. I have printed 4. What are the adjacent elements of 4? 4's adjacent matrix null. Correct? So you will not add anything. So you will add 4. Okay, and 4 doesn't have any adjacent node, so it will leave it. Okay, and now when again you will check q is not null. When you dequeue, which element will be dequeued next? 5, correct. So you will dequeue 5, you will print 5, and what are the adjacent elements of 5? Null. So you will not add anything into the queue. Now again you will check q is not equal to null. So you will pop out what elements gets dequeued? 6. Does it have children? I mean, does it have any adjacent nodes? No. And then what is the last element to be popped out? 7. Okay, now did you get how you are doing level order traversal? DQ, yes, DQ first and then find the adjacency matrix of the DQ'd element. You should always follow the same rule. DQ first, print the value, and then iterate the adjacency matrix. Okay. So what is the important data structure which you will use when someone gives you breadth first search? Okay. Whenever you hear BFS, put it into the queue. We'll move to the code. I'll directly go to the now. For any graph, what are the two important things? Vertices and their adjacency matrix. Okay, and you need a constructor to initialize their values. Initially, adjacency matrix will be empty. That is what you're doing it here. This is all same, whatever we have done so far. And as usual, when you're adding an edge, whenever they say there is an edge, means there is an connectivity. For undirected graph, you will put only one entry. For a directed graph, because it is a two-way road, bidirectional, you can connect from V to W and also from W to V. Got it. Now comes the BFS. So in BFS, what is the first thing what you want? As usual, we want the visited, right? We need not keep visiting the same things again and again. So that you will make use of visited. And you need a queue, right? So you're putting a queue here. And once you visit something, you will mark it as true. So the first node, whatever they have given, you will mark it as true. Correct. And you will add the first element into the queue. And you will iterate the queue. What we have done, right? You will iterate the queue until the queue is empty. So what is the first step while iterating the queue, guys? So while iterating the queues, what is the first step I told? You did the 3, first is dequeue the element from the queue. What is the second step? Yes, second dequeue from the queue. You will print the value and you will explore, you will add the adjacent element into the queue. Okay, you will add the adjacency list of that element back into the queue. Got it? So that's what it is happening here. If you see here, you are dequeuing from the queue
you are printing the value, and if at all the dequeued element have any adjacent matrix, and if it is not visited, you will add it to the queue and mark visited as true. Okay, and remaining as same. So now I'll teach you one more concept of queue. Okay, you know what is a queue, right? What is a queue? FIFO, first in, first out. But now in first in, first out, whatever comes first, you will insert, and that will be the first person to get popped out, correct? Or get dequeued out. But there are certain use cases in real world where you want to assign certain items by priority. Let's say a person with rank 1 should come out first, rank 2 should come second. Okay, so based on certain criteria, you want to order them, or let's say employee. Okay, an employee, I want to sort them based on name, and then, or I want to sort them based on ID, and I want them to pop out of the queue, like whoever, which ID is the lowest will come first. So similar to that, you want to assign priority, and you want to push them top to the list so that they will come out first, they'll be given priority. So queue also offers you a way to assign priority, and the queue itself sorts it according to the priority with comparator interfaces. Okay, many who knows Java will know about comparator interfaces. Comparators are nothing but you have comparator. Comparator means it is kind of a tool. Assume that it is a kind of a tool which helps to compare and order the elements in the queue and reorder it. Okay, so that's what priority queue does. Priority queue will sort the elements based on the priority. It can be sorted in ascending order or descending order. So the elements with higher priority will be dequeued before the elements with lower priority. Priority will always be assigned by the person who writes the code. Let's say I want the elements with the highest frequency, like I have list of elements, 5, 4, 2, 1, something of that kind. Okay, but any point in time I want to find the frequently occurring element first. So something like that, or anything where you want to assign a priority and do, or what you can have an employee object, right? Employee can have name, um, salary, ID. Okay, let's say I want to give preference to highest salary, the person who is receiving highest salary. Then what I will do, I will to the priority queue, I will assign this employee object, and in the comparator, I will say I want to compare the salary of the employee. Okay, and the person who receives higher salary, I want to sort it in descending order. So I will tell the comparator, do a reverse order sorting. So whoever writes the code can assign a priority queue. It's Java util has already provided you a class called priority queue. So you need not write your own queue. Instead, you can make use of that. Let's say in the priority queue, I want to sort the elements based on some ascending order or descending order. Okay, so I've implemented it. So this is kind of comparator implementation. This one, A comma B, B minus A. So it comes in reverse order. Okay, so this is what comparator does for you. Okay, and I'm putting elements 10, 30, 20, and when I peek it, what is the maximum element here? 30. Although I've inserted 30-second, the normal queue will give 10 as output, but this priority queue will give 30 as output, because here you have told the way you want to uh, sort the elements. Okay, I want a priority queue. Okay, so you know that priority queue sorts the elements, and by normal, if you don't put this one, right, if you don't put this, it would have sorted based on ascending order. Okay, if at all, if you do like this, let's do it like this, okay? I'm just initializing a priority queue. So now what you're going to do, you're going to insert the elements into the queue. Forget about heap. Let's say I'm inserting the elements into the queue. Okay, heap makes you confusing, so let us insert some elements into the queue. Okay, I've inserted 10, 20, and 30. Now I'm trying to dequeue an element from the queue. Can you all guess what will be the element that will come out when I run this program? Okay, so priority queue by default sorts the elements in ascending order. Okay, now I want to sort the elements. Now, instead of ascending order, I want it to be sorted in descending order. So what I have to do, I have to write a comparator like any point in time. If I get any element in the queue, what will I do? I will compare the two elements. So any point in time you get any two elements, which is A, B in your queue, you would compare them and at any point in time. So B minus A, instead of doing A minus B, you want to do my second element minus first one, and always the maximum element should come first. Okay, so this kind of implementation is called comparator interface. You have overridden and you have made sure that you should always get elements sorted in descending order. So as you put the elements into the queue, it will run this comparator for every element. It will run this comparator, compare the two elements and find out which one is greater, and accordingly it will readjust the queue such that always you will get the maximum element. So now let's say when you do first, the queue is empty, you will put 10 and you will compare. There is no previous element, so null comma 10. So you do null comma 10, you compare. So you the 10 is maximum, so 10 will be the first element in the queue. Okay. Now when you put 30, what it does is to every element in the queue, it will do a 30 minus and it will identify which one is greater and accordingly it will sort. Previously it was 10. Now how will it change? Because whenever you get a new element, that element will be compared against every element in the queue and it will do a minus. If it is equal to 0 means it is of the same value equal, it will push to the next position. If it is greater means it will take that element in that position and move further elements down. And the moment it identifies its position, right, it will stop comparing. What is 30 minus 10? 10 is 20. 20 is always greater than 0. So 20 is greater than 0 means this element is the biggest element. So it doesn't check what is the value. It always compares the result with the three values, -1, 0 and 1. Which means whether the values are negative, equal or greater, and accordingly it will sort it. But in second iteration, A is equal to 30 or 10. So A will always be the elements which is present in the queue and B will be the elements which you are adding it newly. It is greater. Greater means it gets higher priority. Okay, in comparator, we usually put A, B and A will always be the default. First argument is always the existing values and second one will be the new one. So that's how comparator knows what value to use as B. Okay, I will try to find some more examples for comparators so that you will understand. This is basic Java. For now, you can assume that it is of this way, right? So the normal priority queue will sort it by descending order. If you want to do a reversal queue, you will pass two arguments. First argument will always be the elements in the queue and second one will be the one which you are passing. And when you do second one minus first one, it will always sort it in descending order. Okay. Yeah, you can have any variable instead of A and B. You can have an object. Let's say I'm passing an employee object, then let's say EMP1 is my object, then I will say EMP1 dot, if I want to compare by salary, emp1.salary, comma, emp2.salary. Like I'll pass two objects, emp1 and emp2. emp2 will be the second one, and I'll compare it like this. emp1.salary, emp2.salary. If I wanted to do it in descending order, emp1.salary. So this is how I do. Okay, if you are passing an object and you want to compare based on one particular attribute in the object, then you will do like this. But here you are passing integers, right? So anything is fine. Like instead of A and B, I'm putting C and D. And we will do D minus C. Okay, so those are variables which you can know. Okay, now you got the maximum elements. So what is the maximum element? 30. Now let's say you had a doubt, right? Why did you do D minus C? Why can't you do C minus D? C minus D is your normal implementation, how it sorts. And what will happen when you put C minus D? Any guesses, guys? If not, I'll run the program. See, C minus D, if you do, it will sort it based on ascending order. Okay, when you do D minus C, it will always sort it based on descending order. Okay, got it? Why do we use this notation? This is the standard way of doing it. These are called templates which you pass, generics, okay? So this says the type of the element which is present in the queue. Now when I passed integer, I've told to the priority queue, whatever input I'm passing is only integer. Now, if I want to pass any object, I will change this integer. I told you another example, right? I want to compare based on employee salaries, then I'll pass employee object. Then here in offer, you should do new employee of, initialize those values. Okay, what does peak means? Peak means you will just look into someone else's window. Okay, you will not pop any element out of the queue, but you will just look what is the top of the queue. Can priority queue have duplicate value? Yes, you can. Let us try that as well. This is a max heap, right? So let us put 30 again and run it. What is the output? C minus D, the existing value has to be larger than 10. No, C minus D will always make it in ascending order. And when you do a reverse D minus C, it will always make it in descending order. Yeah. Peak means you will not remove the element from the queue. You will just see what is the element which can be dequeued. I mean, the element will not be removed from the queue. It will still exist, but you can see what is there. Just like you're peeking into someone else's window. You don't take anything out of it. You're just looking. Okay. Now let us do poll. Okay. So can you tell me what will be the output now? See, only sets will not have duplicates, okay? The only data structure which will not have duplicate is set. Others, everything will have a duplicate. You can push duplicate items. Peak means you just look into the top of the queue. You can guess what is poll. Okay, poll means you are removing the top element from the queue. Now I have removed the top element from the queue. I'm going to remove one more element just to see. See, first time when you peeked into the queue, you found 30 and then you polled, which means you have removed an element from the queue. The top element for 30 got removed. Again, you removed 30. Guys, always remember the only data structure where you don't allow duplicates is set. It can be any set, hash set, tree set, anything. Okay. To get filtered first, not filtered. Filtered is not the correct term. To set the priority to DQ, correct? Right. I mean, or you can say you want to sort the elements based on some order, right? Based on some priority, you want to sort the elements either in ascending order or in descending order. Okay, what is the default order in which the elements get sorted in priority queue? Ascending order. If you want to sort it based on descending order, what will you do? Comparator, right? Can you give me an example? Yeah, the code example, like what will you give in the bracket? C minus D, okay, but can you give me the entire expression, please? I'll stop sharing. Okay, how can you define custom class? Okay, we'll write an example for that as well. Okay, we'll create a custom class called employee, and I'll give them let me put it as integer. Okay, now I have an employee class and I'll create a constructor. Okay. Okay, guys. Now I'm telling instead of integer to the priority queue, I will pass employee. Okay, and I'm passing two objects. Let's call it as you can name anything emp1. I'm calling another emp2. And I want to sort them based on their salaries in descending order. Why did I put two string? I wanted, see, by default, when you print a custom class, right, you will get the object ID. Okay, but I wanted a meaningful convention to understand which object it is. So that's why I've overridden two string clause. Okay, now let us run this. Can you guess what will be the output? Yes, right. To print the object in a more readable or the way where you, how you are defining. Correct. See here, I've sorted the elements based on descending order because I did second object minus first object. Okay, so based on salary I've sorted, and that's why even though the third element with employee ID 3 is the one which I've inserted at the third position, it got peaked first and it got removed first. And next priority is 500. Why don't you print the entire element? Entire element in the sense I'm already printing the employee ID and salary. Entire queue, then you pop out every element and print the queue. Or use an iterator. You can use an iterator and print all the elements in the queue. Okay. I'll print the remaining elements. Okay. I've popped certain elements, so I'll print the remaining elements. Why are we using integer instead of int? You can use int as well. Try that and let me know. Difference between int and integer, probably you'll have to go to Java class to understand what auto boxing, wrapping and all that is. Here we are reading only data structures. Okay. Okay, got it, guys. I got an error. Okay. Do that, please. Why are we using integer wrapper class of int? Okay. Processing unboxing. Okay, good, Aditya. I got an error while trying to run the code. The method offer in the type priority queue is not applicable for the. Yeah. Why did you put the type as integer? The type should be employee, right? See, when you are in the generics, whatever type of the object you are inserting into the queue should be the same as the one you are inserting. Here I am not inserting integer, I am inserting employee. Okay, Yakul? Yeah. Please print the entire element. Entire element is already printed. We can't use max heap. Why can't we use max heap? Now, let us go to the concept called heap. Okay. So, before I explain the PPT, let me stop sharing and I will use a whiteboard. Okay. So, let's say I'm going to create a heap. Okay. Heap is nothing but at any point, you'll say heap of values, right? Means a lot of data will be present. But I want heap to extract At any point in time, I want a minimum value from it. Then I'll go for min heap. From the heap of values, I want to get the minimum element. Okay, that is called min heap. And at any point in time, I want the maximum values out of the heap. Then you will implement max heap. Okay, so when do you use heaps? Let us say there are some kind of searches where you want the maximum element out of the array, or you want to find the minimum element out of an array. Then you will go for heap concept. Okay, you will either implement min heap or max heap. Now let's say we have a heap. So the first element, I have an element. So first time let us implement min heap first. Okay, we are going to implement min heap. So first time I'm pushing the value 2 into the queue or to the heap. So 2 will be the root. So this is 5. Next I'm pushing 5. Okay, so first value to be entered is 2. And next I want to enter 5. Okay, so what will I do? I will see 5. 5 is greater than 2. So 2 is the minimum element. Okay, so I will put 5 here. Okay, so at any point in time, a given node should be the minimum when compared to all its children. So that is the concept. Okay, now let's say we are going to put 1. What happens? So what is the next free element, guys? Free space here. I'm trying to put 1 here. But then I'm comparing, so I want to put 1. So I'm comparing 1 with 2. 1 is smaller than 2. So I'll put 1 and I see this is an empty node. So I'll push 2 here. Okay, so any element you will compare with the root element and you will decide which track to take. Okay, so likewise, if you do a maximum heaps comparison, then it is max heap. Okay, so now what happens? You have inserted, first you had 2 and then you put 5 within the empty space. Now 1 came, so what you did? You compared the 2. 1 is the lowest, so you have assigned 2 to the right because the space is empty. So what did you do? First you put 2. Okay, when you got this array, the first element was 2. So 2 became the root. The next element was 5. So you compared with the root. 5 is greater than 2, which means the root element is lesser. This is a min heap, right? So the root element should always be smaller. Yeah, it is not a BST as such. Yeah, good. But it always follows that the given node at any place, it should be smaller than its children. Okay, now 5 had come. So you compared 2, whether 2 is less than 5, condition is true. So I can insert it as a child. I don't have any issue because I'm always smaller and this is a min heap. Okay, it's just a binary tree, but not a binary search tree. Okay, so that is why the ordering can change. See, the first element is 2, so I have inserted 2 as root. So what is the criteria of min heap? At any point in time, the root element or the parent node should be less than that of all of its children. Okay, so the first node is 2. I don't have any children, so I inserted it as a row. Next node is 5. So what is the condition? The parent node should be less than that of the child node. So 2 is less than 5, condition true. So I'll put it as a child. This is not a binary search tree. So the left child should be small, right child should be great. It will not be of that kind. Okay. Now you got an element 1. Okay. So what will you do? You got 1. What will you do? What will be your first step? I got 1 now. What will I do? I'll compare 1 with the first element. Is 2 less than 1? The condition is false. So 2 can never be the parent. So what it will do? It will rearrange the queue itself. So 1 will be pushed on the top. Okay, 1 will get 2's position and then one will wait for it. What to do next? Okay, its right child is free, so it need not worry about compare the subchilds. So it will put it into the right. So 2 comes here. Okay, now if you see 2, it doesn't have any children, so 2 is uh, the minimum element here, so it is fine. Now 5, it is the minimum element, so it is also good. Q be stored in a binary tree. It is all internal implementation. In case of 4 elements, the implementation, right, internally it works differently. At every point, it compares and gets the minimum elements, but this is what it happens. Okay, add after 2 and 5, if we add 7, then okay, now let us run the algorithm. Supal wants to add 7. Okay, now 7, 1 is less than 7. So I'll go and compare 5 and 2. 5 is less than 7. Here also the condition is satisfied. 2 is less than 7. Here also the condition is satisfied. So, but in 5 itself, the condition is satisfied. So I'll not go and check the right child. To the left of it, I'll put 7. This is always a balanced tree. Okay, so I'll all see the left positions and then I'll fill the right position. What are the conditions for 5 and 2 to have children? Yeah, 5 is also checking. 5 is less than 7. Okay, then only we are putting it. Now let's say we are trying to add another element called 4. Why not under 2? Because it is a balanced tree. You will come from left and then go to the right. See, when we will put on right, if you get any element which is smaller than 2, right? But greater than the root element, then we will reorder this. What if same value comes in? We can put it to the right. So any given value, it will be compared with left child and right child. And then accordingly, you will do it. See, this min heap and max heap is a concept. You need not go into detail of implementation and do a peek and a poll of it. Okay. In real world scenarios, where for your interviews and examinations, you will not be implementing the min heap and max heap using data structure classes. Okay. If it will be done only for PG graduates who are doing their MTech, correct? For all others, you need not know the implementation, but then understand what is the concept of min heap and max heap. The concept is at any point, the given node should be less than that of all its child nodes. If any subtree, if you take, 2 should have the minimum value of the subtree. If any subtree, if you take here, 5 should be the minimum value here. Got it? So this is the concept of min heap. Similarly, for max heap, at any position, a given node should be maximum node when compared to all of its children. Now, let us implement max heap. I got the element 2, my Q. I'm sorry, guys. So, my Q is, or my heap is already empty. So, I'll put 2 as my root element. Now, 5 comes in. When I compare for max heap, this is max heap. What is the rule of max heap, guys? Yeah. See, when you get the lower element right, you will always start from the root, find the lower. See, if it is a lower value, you will compare the left child and right child. Okay. And you will check whether the left child's value, whichever is lower, you will take that route and then reorder. Okay, because only then you can fit the lower element. But if you get a max heap, you will get the, see, you will decide left or right based on what is the value of the element in the left or the right. So now you got 2 and next you got 5. So you will check 2 is greater than 5. In this condition, it is false. So you will put 5 at the top and then you will put 2 as its left shell because both left and right are empty. Now you got 1, right? So what will you do? You will compare 1 with 5. Okay. You compared 1 with 5, and you will check 5 is greater than 1, the condition is true. So now it goes to the left and right child. Because the right is empty, you will put this 1 here directly. There is no check at all. Now let's say you are getting an element called 8. Okay, now I got an element called 8. So what will I do? I will compare 8. I'll compare 5 is my root. So 5 is greater than 8. The condition is false. So I will remove this 5 and I'll put my 8 here. So now I got to know. Now see, in a heap, the topmost element is always maximum, right? So I know I can take this 5 out and 8, because you will not have any maximum elements down the line. Maximum can be 5 only. Now you will take this 5 and compare with 2 and 1. Which one is greater? So 2, right? So you will replace this 2 with 5 and you will push the 2 to the left because left is empty. Again, left or right, it will decide by taking the maximum element and it will put. Okay, that's for max heap. For min heap, it will decide left on right by picking up the minimum element. Okay, this is how internally it works. But for your code, this understanding is enough. But you will always implement this using priority queues. We'll go to an example. 2 is added. 2 is added. So you have a tree here. 8, 5, 1, and 2. You have reordered and you made this. Now you got 2. At any point in time, it should be maximum, right? So 8 is greater than 2. It's fine. 5 is greater than 2. It is fine. Here 1 is less than 2. Here the left node is empty. Or if you want to take the right node, it will put 2 here and it will change the 1 to its left child. Okay, because it compares and sees 2 is greater. So it will put 2 here and it will pull the 1 down. Now let us go through the slides. It talks about the same thing. So what is a heap property? For a given node, its value should be greater than or equal to that of its children's. That is called max heap. If it is less than or equal to of its children, then it is called min heap. Why we are going for what is the need for min and max heap? Any use cases? Ordering I can do it. I can do collections dot sort itself, right? It will do the ordering. Why do I want min heap and max heap? Yes, for storing large amounts of data. For storing or for what? Large amounts of data, but min c minus t. Finding minimum or and maximum in a given data, right? So that is the use case for min heap and max heap. Let's say I want to extract top 5 elements from a given list. I'll go for min heap. If I want the like top 5 small elements from the list, top 5 maximum elements in the list, or the frequently occurring characters, top 5 frequently occurring characters in a given list. Okay, so these are some of the use cases. Okay, yeah, so all these are the same thing which we have discussed. Is now there is a given use case and there is a question, right? Find the k most frequently occurring elements in a given array. So how will you solve this? Mode. Okay. So another way is, like, for every element you will maintain a heap. Okay, like 3, I got 3. So initially I will say 3 occurred once. Next 1, okay, I'll put it in a map. Okay, like the value and the frequency. Okay, so this is the value and this is the frequency. So 3 appeared once, so I'm putting it in the map 3 1. Okay, now I got the element 1. So the element 1 is not in the map, so I'm defaulting the frequency 1 here. Okay, yeah, you are right. The dictionary, the same thing. So now I got 4. 4 is not in the map. So I'm inserting the frequency 1. Next again I got 4. So I have incremented the frequency. Now 4 became 2. Now 5. What will happen? What will I do to the next element? 5, 1. For the next, for 2, 2, 1. Good. 1. And next 1, correct. For 1, you will increment. Because 1 is already there in the map, so you will increment. Now what you want? Top k frequently occurring elements in the given array, right? So now let's say here they have said k is equal to 2. So what is the output? So what are the two values? It is 1, 4. You're right. So how will you do that? Now first thing I've given you a hint. You will put it in a map with iterating every value and its frequency. Next, what will you do? I want the top frequently occurring elements. So what data structure will you use here? See, you're putting map. Map is correct, okay? Map, you're putting it in and updating the values. Okay, you're putting... so now I got a key as a value. In map, the key will be the item number and value is frequency, correct? So key is your value 3 and the frequency is the number of times it has happened and you got the map. Now I want the top 2 elements, top 2 frequently occurring elements from the map. So what will I do? Yes, you can put it into a max heap. How will you implement max heap in Java? At any point in time, it will give you the top 2 elements, correct? We'll use a priority queue. Inside the priority queue, you will first create an object with values, key and value, right? And what will you do? You will insert into the priority queue this particular object. Let's say max heap object. Okay, match object. And you will create this template and you will put the value here. Can you implement this priority queue and give me an example, guys? It's not val2 minus val1, Yakub. Please correct your code. See, I've told you are putting into a map. You are iterating every element in the map. Your map has two integers. One is key and the other one is value. Val is the frequency. Okay. Now you have key and value. So you are putting it in a custom object and then you are sorting it. So how will you implement the custom object? What I'm telling is, this is a key value pair, right? There is a class called pair. Okay, there is a default class called pair, or you can also create your custom class called pair. And inside pair, you have two numbers. One is key and one is value. And you are keeping priority queue of pair. And here, you want it based on descending order. So what will you do? You will write a new priority queue of all that you have find, right? And you will put some generic spaces and then you will pass object 1 pair 1 comma pair 2 and then what will you do? Object 1 comma object 2. Okay, let's say object 1 comma object 2. I'm typing in the chat window, guys, so that and what will you do? Object 1 dot object 2 dot frequency, because you want it in descending order. So object 2 dot frequency minus object 1 dot frequency. Shall we move to the next greedy algorithms? Okay, so greedy algorithms. Greedy algorithms means you want to find an optimal solution for a given problem by doing some tricks, or you are applying some kind of algorithms to a given subset and you use it and you are greedily finding what value it is. So this is type of an algorithmic paradigm, or I don't want to explain this jargons as such. You are going to find an optimal solution for a given problem, okay, by taking some chances, which will give you the good results. Okay, so that is called greedy algorithms. Okay, optimal substructure means at any given point, if you even take any subset, okay, you will always get the optimal solution. No matter you run it for the entire array or to the subset of the array, you will get the optimal solution. That is called optimal subtraction. Greedy means instead of doing a linear search and finding an value, you will carefully make the choices. Like I will only search in the first three values in an array, and I'm sure that I will get the value. You make some choices, and you are sure that the choices are right to get a optimal solution. Okay, that is called greedy. Instead of wasting your entire money in traversing the entire list, let's say you have a sorted list, you want to find a maximum element in an array. Okay, it is already sorted. The first element is always maximum. So that is kind of a greedy choice. But you're sure that that is an optimal choice. Okay. So there are a few greedy algorithms for your understanding. One is fractional knapsack, other one is Huffman coding. So this a fractional knapsack, instead of going through the theory, what is greedy algorithm? I want someone to answer. Okay, now let us see what a knapsack problem is. Okay, knapsack means this problem applies like this. Okay, you will be given a value. Okay, and weight of choosing this value. Okay, you will get a value. Let's say my value is 20, or let's say you will get some profit. Okay, instead of value, let us rename it to profit so that you all can understand. Okay, so profit is 20. For earning a profit of 20, you should lose a weight of 6. Okay, and knapsack means you have a sack where you can put these values. Okay, this is your sack, and this sack is of a particular capacity. Okay, it is of a defined capacity. Let's say the capacity is 20 kgs. So it can hold a weight of only 20 kgs. So what you have to decide is you need to earn maximum profit in the sack. Okay. So what is given for every profit value? What is the maximum? What is the weight? If you want a profit of 20 rupees, you have to put 6 kg into this sack, then you will get a profit of 20. So if you put the 6 kgs, so the result will be 20. Now how much weight your sack can hold? You have already put 6 kgs weight into your sack. So what is the remaining capacity of your sack now? 20 minus 6 is 14. W is weight. Profit is what profit you are attaining. So the aim is to get maximum profits, which means you want to get a maximum profit by filling this sack. Okay, so now the capacity got changed to 14 because you have put 6 kgs weight into it and you have earned a profit of 20 rupees. Okay, put in 18 kgs. Yeah, you can put 18 kgs or whatever it is. Okay, now let's say what is the next element? 30, 13. So what it is telling, next profit you can get 30 rupees. I mean, for your understanding, I'm telling in terms of rupees. So you will think you want to greedily get maximum profit. Okay. And I'll put 13 kgs weight. So what will be the remaining capacity now? What will be the remaining capacity, guys? 1. Why 1? 14 is the maximum capacity of this sack because you have already put 6 kgs into it. Now I've loaded 13 kgs. Now maximum how much I can put? Only 1 kg. Now let's say I'll give you a profit of 15 and maximum weight for this is 5 kgs. Okay, but I want only 1 kg out of it. Okay, So what can I do? What is 15 by 5? You will get 1 kg's profit, right? So plus 3. Now your sack is full, correct? You are putting 3 rupees instead of 15 rupees because your sack can hold only 1 kg. So I'm getting 1 kg's profit and I'm putting 1 kg from this. Okay. But if you see, there are other elements also. It says 25, 10. Okay, for 10 kgs, you will get 25 profit. Here you see the best one. You will get 10 rupees profit for every 3 kgs. Okay. Do you think this is the optimal solution if I follow this approach? Like I'm putting 6 and then I'm putting 13 and then I'm putting 5. Now, even though, see, instead of for you'll earn 30 rupees if you put 13 kgs into it. Instead of that, let's say I'm picking this. Okay, so what will happen? 30 kgs means you will put 9 kgs weight only. Okay, but you cannot put because there is only allocated is only 3 kgs. Okay, 13 by 3 is very bad, right? It is occupying the maximum capacity of your sack. So it is not giving you the maximum profit. Now let's say I know that this will not give me the maximum profit. So I will skip this. If I skip this, how will I do? So I'll put the 6 kgs weight and I earned 20 rupees profit. Now my capacity will be 20 minus 6, which is 14. Correct. Now next, I know that 30 is a very bad weight to choose. So I will not choose that. Let me choose 50. I'm very greedy. I've looked at this guy. This guy is not giving. So how do you decide? An easy way to decide is divide the profit by weight. You will get the ratio. So how you can decide this? Divide what 20 divided by 3, what 6, what is the answer? Guys, 20 divided by 6. Now let us find the ratio here, okay? 3.3. Okay. Now what is 30 divided by 3? 3. Okay. 30 divided by 13, the next element, 2.3. What is 15 divided by 5? What is 10 divided by 25? 2.5. What is 10 divided by 3? 3.33. So, if you were to choose, how will you choose? Which elements will you choose first to fill in the stack? Will you choose 30 by 13? Yes, you will choose 3.33. So what are the weights you will choose? So 20 and 6 first you will choose. And then what is the next profit to weight ratio which you will choose? 10 by 3. Okay. What next? 20 by 6, 10 by 3, and then 15 by 5. And after that, what will you choose? 25 by 10. Okay, after that, guys, at last, only you will choose 30 by 13. Awesome. So, you are greedily making the choice to choose which one to take first. Okay. Okay. Now, from where does this measurement came from? Tell me from where I identified I should choose 20 by 6 first. From this ratios, right? From this ratios only, I reordered which elements could be my priority. Instead of picking the order in which I'm getting the elements, I've reordered greedily by identifying the ratio. I mean, for example, I'm telling, I've taken a problem where to earn a profit of 20 rupees, the weight you have to consume is 6 kgs. For a profit of 30 kgs, 13. So these are your sample input values. Okay, it will change dynamically based on the problem which you are getting. Yes, just random values. Okay, now you have identified the ratio. Okay, from the ratio, I have reordered this profit weight map in such a way that I will always get an optimal solution. This is a greedy algorithm. Now you understood what is greedy thing? You are making your choices optimally such that you will earn maximum profit. Now you must tell me, for a capacity of 20, what is the maximum profit I will get? Let's say I have a sack whose maximum capacity is 20 kgs. Okay, now I want you to find an optimal solution from this. Okay, so let's say the capacity is 20. Okay, so we have reordered this. So we know that we will always, the first item is the one which will give you more profit. Okay, so what will you do? I will I'll put 6 kgs of first item and I've earned a profit of 20 rupees and my capacity became 20 minus the first element, which is 6. And this 20 is my profit. Okay. So now 20 minus 6 means what is the remaining capacity? Remaining capacity is 14. Correct. Now the 14 is the remaining kgs. And what I'm telling, I'm earning a profit of 10 and I will put 3 kgs into it. So when I put 3 kgs into it, 14 minus 3, what is it? 11. And I got a profit of 20 plus 10, which is 30. Okay, now the sack is not empty. I can still hold some more values. So I will take 15. Now to earn a profit of 15, what will I do? I have to put 5 kgs into it. So I will do a minus 5. So what is 11 minus 5, which is 6. 6, right? 6. And then next I'm seeing for a profit of 25, I have to put 10 kgs. Oh my God. Unfortunately, are there duplicates? Where? Okay, let us skip what is there in the chat. Let us go through what I'm doing. Now 6. What is the next element to be picked, which is 25, and maximum you can put is 10 kgs, but my sack only has 6 kgs. So what will you do? 25 by 10 into 6 will give you 6 kgs profit. What is this? What is 2.5 into 6? 15. Okay, so I'll put 15 and I will minus 6 kgs from it. So 6 minus 6 is 0. So what is my maximum profit here? Yes, 60. Now you understood what is the maximum profit here. Now let us say my maximum capacity is 25 kgs. Then what is the maximum profit I'll get? Can you calculate and tell me? Guys, clear? Anyone, any queries? Now can you find out for a maximum of, we can't use twice any, no, you cannot use twice because it has given maximum capacity itself, that is the weight. You cannot use twice. Okay, my last question is, for a capacity of 25, my sack has a capacity of 25. So what will be the maximum profit? So what will I do? I will pick the first element. So the capacity becomes, what will be the value of my capacity, guys? 25 minus 6. Yes, 19. My capacity becomes, okay, my capacity becomes 19 and profit is 20. Now I'll pick the next element because I've already ordered and I'm very greedy. So what will I do? 19 minus 3. What is it? My profit is 10. Next, I will add 5 kgs. So this is 11 and my profit is 15. I'm 11. I add 10 more kgs. So remaining capacity is 1. The profit is 25. Now I want to add 1 more kg. So what is 30 divided by 3? 13, which is 2.3. So my profit is 2.3 and my capacity becomes 0. So what is the answer? 72.3. Did I do something wrong? Why is it 73.3 for others? It is 72.3 lakh. So you're clear, right guys? So this is knapsack problem. Now coming to the implementation. Okay, now coming to the implementation. So this is the same thing what I've explained. So how will you implement this, guys? So maximize the total value in an abstract such that you are not exceeding its weight capacity. Item can also be taken in fractions. So what will you do? You got a class with value and weight. Okay. And in the priority queue, you will order it by the ratio of value by weight, such that the values are in descending order to get the maximum profit. You know what we did, right? For a given values, you did the ratio and you have identified the maximum profit um, by doing it in descending order. Okay, so that is what here we are doing. So you have got weight and value. So weight is weight and value is something like I told profit, correct? Because I want you to understand it easily. So I've mentioned a word called profit. And now what I'm doing, I got this entire items and I'm sorting it. Okay. Either you can do arrays.sort or you can put it in priority queue and you can do this logic. A comma B you can pass and B minus A, no, the same way you will do I dot value by I dot weight minus J dot value by J dot weight. If J comma I you have. Yes, knapsack is also a greedy algorithm. And once you get that ratio, what will you do? For every item from this priority queue or from the sorted list, until you have the remaining capacity, you will maximize, add the profit and minus the weight. If at all the weight is less than the remaining capacity. If let's say if you have to take the fraction of it, then how will you do? You will divide the value by remaining capacity into item weight and get the value for that. Shall we move on to the next? The code is there in the sheet, but if you understand the way I'm solving the problem, it will help you to write the code by yourself instead of saying that. Here they've used arrays.sort. Instead, you can put that in priority queues as well. Okay. Now, and then we'll go to Huffman coding. Now, there is something called Huffman coding or encoding. Okay. You know, every character. So for every character, how is every character stored at low level in terms of bytes or bits, right? So for every character, let's say for A it is 100, and then B it is 101, and for C it is 102. Then for Huffman encoding itself, I have to write a very lengthy character, correct? And it will consume most of my space. So everyone was worried about it, how to save the space. Okay, instead of putting it for every character and clubbing it all together, it is so difficult and it keeps it keeps growing. So they wanted to compress the way of storing the characters using an encoding algorithm which is called Huffman coding. Okay, now I'll show you an example how Huffman coding works. I'll take the same example what you have in PPT. They have a character called A5, B9, E16. Okay. So let us do this. So it starts from the frequently occurring character. Like for in a given string, let's say A is occurring 5 times, B is occurring 9 times, C is occurring 12 times, D13 and E16. It wants to find an easy way to compress and find an algorithm. Okay. For a given occurrence of a, let's say in any given string, let's say A is occurring 5 times, B 9 times, C 12 times, D 13 times, and E 10 times. They want to store it in a compressed way such that you can easily store and retrieve the data. Okay. So what in that algorithm they do first is they've taken the frequently occurring elements. So what is frequently occurring? 16, right? So let's say I'm putting 16 first. So what is the next frequently occurring element, which is 13? So I'll put 13 next. This is T, this is C. See, I want you to listen for some time. After that, I'll answer your queries, okay? So I put a D here and E value was 16, so I put it here, okay? Now, what I do, I create one internal character which is the sum of 13 plus 16. What is 13 plus 16? What is 13 plus 16, guys? 29. Okay. So I'm forming a tree with the frequency of occurrence of a character by first choosing the frequently occurring element and then the next one. Okay. And then I'm trying to build the tree on the top. So what is the next element what I will choose? Because this is already summed up, so I will just see the root is always the sum of the two elements. Okay. So now this is my right subtree. So I need to have a left child. So which element will I pick next? Based on this arrangement. 12, correct? I'm picking it based on the frequency. So I will pick 12 next. Okay. So now I'm adding 12 to the left of the subtree and what will be my root? My root will be some internal node whose value is sum of left child plus right child. Here, what is the sum? 29 plus 12. So what is it? It is 41. Okay. Next, I will pick the next node. So this is my right subtree. I have furthermore characters. Then I will pull the next element, which is my next element at 9. Okay, I'll put 9 here. And what will be my root node? It is some internal node with value of 9 plus 41. What is it? T. Okay, what will I do next? This is my right subtree. I still have elements, so I'll consider this as my right subtree. And I will take the next element, 5, and add it to the left. And I'll make the root as sum of my right child's value plus left child's value. So 50 plus 5 is the value 55. And now what I'm doing, because right is my subtree, anything that comes on the right, I will assign the bit 0. Okay, I will assign the bit 0 to 41, 50, 55. This is 0 here. And E, because it's a right child, it is 0. Anything with the left child, I'll assign the code 1. So C is 1, B is, if it comes here, it is 1. Now A comes 1. And because I have added from the right bottom, I will always calculate the value of A from the right. Okay, for any given character, if it is E, D, C, B, A, anything, I'll calculate the value from the rightmost element to how will I traverse and reach this element. Okay, so if I do that, what is the value of E? To the rightmost element, what value will I give? 0. To the leftmost element, I will give 1. So in that case, what is the value of E? For E occurred 16 times, and if I want to store E, I will use 0. So for frequently occurring element, you got the minimum binary value to store, correct? If you are storing it ordinarily, you will convert E to binary value. It will be a very lengthy code, but you have greedily identified what code will you use for frequently occurring values such that you can retrieve this value. Okay. Now for D, what will the value be? Start from the right and then go to the left. So my right is 0 and then my left is 1. So for D, the value is right is 0 and left is 1. So D is 10. 1 0. It is not 10, it is 1 0. It is a binary code. Now have 12. You will start from the right node. So what will happen? What is the value of my right node? 0. And then go to the left 1. And then go to the top internal nodes doesn't have value. So 0, 1, 1. So what will the value be? Right node has 0 and then D has 1. I have to climb the tree by visiting every node. So C gets the value 1, 1, 0. Traverse from the bottom and then go to the top. So it is 0 and then 1, 1, 1. So what will be the value? 0, 1, 1, 1. So now it is easy to store data, right? What are the ways to store the data? You can store it in memory, you can store it in database, right? So you can store the data everywhere, but the problem is how will you optimally search? Let's say in terabytes of data, you're going to run a query and get the results. If your search query is taking more than 1 minute or so, will you wait for the response from a chatbot? No, you will tell that it is not responsive, right? It is not responsive. I'm not getting the response. Okay, so what is the main important thing what we want? Store the data and access it such that I can easily fetch the data. Okay, so we will discuss on the various type of search algorithms. So one of which is a linear search. Okay, so okay, so it is an important thing for us everywhere, right? So we will discuss about the different searching algorithms, okay? And I'll also tell why are we sorting the data as well, okay? So first is linear search, okay? So there are elements 20, 15, 25, 16, 45, 60, and 20. Now let's say we are searching for an element 60. Okay. I will give you the huge input list and I want you to find an element for me. So what will I do? I will take the first element in the list. I'll compare which is 60 or not. Or no. Then I'll go to the next element. No, it is not 60. I'll go to the third element. I'll see, no, this is not 60. And then 16, no, this is not 60. Then I'm searching, no, 45. So, and then I'm finding 60. So basically what you're doing, you are iterating the array from the index 0 to n minus 1. Correct. Here you have 3, 6, 7. So from this is index 0, index 1, index 2, index 3, 4, 5, and 6. Basically what you're doing, you are iterating every element and you're seeing whether that element is equal to the target. And if you are iterating and if you are not able to find that element, you will return no, the element is not found. Otherwise, you will return the index of the element. Okay. In the linear search, what you're doing, you are iterating from 0 to array length minus 1 or less than array length, either ways. And if array of I is equal to target, you are returning the element, which means you found the element, just return the position of it. Otherwise, you are going to return minus 1, which means, sorry, the target is not there in the list. Okay. And you're calling that program, you're initializing the input here, you're assigning the target here, and you're calling the search algorithm. And if it is index is not equal to minus 1, which means you found the target and you will display the index position. Otherwise, you will say, sorry, we are not able to find the element in the array. Okay. Now let us go to binary search. Okay, so this is all about linear search. What about linear search? This is very expensive, right? Let's say you are having petabytes or terabytes of data. You have to go and scan till the last element and find that out, right? It is very expensive for us. So how do you think? Yeah, it is time consuming. What is the time complexity of this? You are scanning through every element. So let's say in the worst case, if the element is at the last, it is equal to the size of the array. So it is order of n. Okay, guys. Now, how will you mitigate this problem? I don't want to do a linear search because every time I'm going to scan it. So what do you think? Binary search. In order to implement binary search, what is needed? You have to sort the array. Okay. This is so time consuming for me. So I wanted to find an optimal solution instead of this one. Correct. So what can I do? I can sort this array, and if the element is ordered, I can do an easy trick. Okay, that is called binaries. Okay, so let us sort this array. Well, 14, 16, 20, 25, 45, and 60. Right? Now I got these numbers. Now, what did I do? From the unordered list, I have ordered it. Okay, now I'm going to run my search algorithm. How am I going to run? So 12 is in my 0th position. 40 is my first position. This is in 3rd position. 24 and this 60 is in my 6th position. Okay. I'm going to split this into two equal halves. Okay. So what I'm doing, what is n? N is 6 here. 6 by 2 is 3. From 0 to 3, minus 1, I'm taking it as one array. And the remaining one, I'm taking it as another half. And this is my mid pointer. What is this? Mid pointer. And this is my left pointer. What is this? Left. And this is my right pointer. Okay, I'm assigning 3 pointers to it. Okay, and I'm dividing the entire array into half, and then I'm searching for the element. Now, what is the element which I'm searching for? It is 12, correct? No, I was searching for 60. I'm sorry, guys. I was searching for 60. So what I'm doing, I'll compare whether my middle element is equal to 60. Okay, what is my middle element here? 6 by 2 is 3. I'm checking whether this A of 3, what is this? 20 is equal to 60 or not? No, it is not equal to 60. And you know that the value is greater than that of the middle element. Okay, the value is not equal, which means this is not the element which I'm trying to find. But what is the hint here? I know that if the value I'm searching for is greater than that of the mid, definitely it should be in the right side of the mid, right? It should not be in the left side. So I can leave this. So what will I do? I will take this 25, 45, 60 and I will what will I do? I'll take this pointer. So my right will stay as such and my left will become middle element plus 1. What will my left become? Mid plus 1. Okay. So now this has become my mid. I'm not changing anything else. Right? I'm leaving it as such because anyways I have to search in that subarray. But the left, instead of this one, I'm moving this left to this position, which is mid plus 1. Okay, now my left has become 25 and my right has become 60. So what is the position? 4, 5, 6. What is left plus right by 2? Which is 4 plus 6 divided by 2. What is 10 by 2? 5. Right? Now 5 is my middle element. Okay, got it, guys? How am I getting the middle element? Okay, first one was 0 plus 6 by 2, which is 3. I got the middle element. Here it is left is 4 and right is 6. So 4 plus 6 by 2, 5 is my middle element. Now from the middle element, I'll come. What is the element to be searched? 60. I will check 45 is equal to 60 or not. No, it is not equal. So, and then the next step is whether it is less than the middle element or greater than the middle element. It is greater. Okay. So, greater means what will you do? You will go to the next subarray. Okay. So my right pointer will stay as such because it is greater. So you need not disturb the right pointer. Left pointer will be mid plus 1, which is 5 plus 1, which is equal to 6. Okay. Now, how long you will do this changes? Only until left is less than or equal to right. The moment left becomes greater than right, or right becomes less than left, which means that the element is not found. I'll explain that later. Now let's see this. Now what is my mid? Mid is 5. So right pointer will stay as such because the element is greater. Left we have to adjust, which is mid plus 1. Now what is left out? 6. My left pointer is also pointing to the 6th index and right pointer is also pointing to the 6th index. So what is left plus right by 2, which is 6 plus 6 by 2, 12 by 2, again it is 6. Okay, so now mid element is a array of 6, which is 60 is equal to the target element. So you will return the index mid. Okay, so now this is fine. Now let's say you are searching for 60, but the 60 is number 60 is not there and number 70 was, let us assume like that. Now the number 70 is there in 6th position. Okay, let us take the sorted array. Okay, and let's say I'm searching for an element 65. Okay, so now here, if I take this array, what will be my left pointer and what will be my right pointer, guys? Left pointer is in 0th position and right pointer is in 6th position. So where will my mid element be? 3. Mid is equal to left plus right by 2. Okay, this is my mid. So here, what is my left index? 0 plus 6 by 2, which is 3. Okay, now I got my middle element. What is the next step, guys? You will compare middle element with the target element. So what are you comparing in terms of values? First, you're comparing equal to comparison, right? 65 is equal to 45 or not. Is it equal? No. If it is not equal, now what is the next check you will do? Whether the search element is greater than the middle element or lesser than the middle element. What is the value here? Is it greater or lesser? It's greater. So which array you'll have to search? Now right array. So what will you do? Will you change the left pointer or right pointer? We will not disturb the right pointer, but we will assign the left pointer to mid plus 1. So left becomes 4 and right becomes 6. Okay. Now for this subarray 60, 70, 80. Okay. Now how will you find the middle pointer? Mid pointer is left plus right by 2. But what is the value? It is 4 plus 6 by 2. The answer is 5. Okay. Now this is my mid pointer. Now what is the next steps? Array of mid is equal to element. Is 70 is equal to 65? Are you checking that? So is it same? No. So what will you do? Will you disturb the right pointer or left pointer? You will not do anything to the left pointer because the value called 65 is less than that of the mid. So you will take this right pointer and make the right pointer is equal to mid minus 1. Okay. Now, what is my left pointer and right pointer now? So if it is mid plus 1 minus 1, which means 4. So both my left and right pointer are pointing to this element. Oh, binary search. Okay. So you will implement binary search only on sorted list. But how will you sort the list? There are many ways of sorting it. So what does a binary search do? It repeatedly divides the list into half and compares the middle element with the target. Okay, guys, it's the same. Compare the target with the middle element. If they are equal, return the index. If the target is less than that of the middle element, search in the left half, otherwise search in the right half. Okay, so the same thing is explained here, and this is the code, which you know, right, already. Until left is less than or equal to right, you can do the same thing, repeat the same thing. The moment right becomes less than that of left, which means you have already searched all of the elements and you can come out. Okay. So now we are going to see different ways of sorting, okay, such that you will choose the best optimal algorithm and then you will continue. Okay. So now I got a list of elements, right? I got a list of elements that are to be sorted. Okay. Now what you will do first, you will compare the first two elements. Now you will compare 13 with 32 and you will see is 13 smaller than 32, right? You will compare adjacent elements and go on. Okay. So this is called a bubble sort. So you will compare 13 with 32. 13 is lesser than 32. So you will not swap. You will leave it as such. So after the first comparison, you will compare every element with the remaining elements. Okay, until you get a sorted list. Okay, so 13 and 32 is compared and you find that 13 is smaller than 32. So you need not swap, you left it as such. Now, in the next iteration, now we will pick the next two elements. Okay, so when you pick the next two elements, what will you compare? 32 and 26. So is 32 lesser than 26? No. So you will swap 26 and 32. Okay, got it, guys? Okay, 32 is less than 35. So you will not do any swapping, and then it will remain as such. In the next iteration, after you compared, what did you get? The remaining elements as such: 13, 26, 32, 35, 10. Because when you compare, you need not swap, so you leave it as such. Now, take the next elements. Now, 35 will compared with 10. Okay, 35 gets compared with 10. 35 is greater than 10. So, you will do a swap. So, 35, 26, 32, 10 and 35. Okay, guys. So, you did the first pass by comparing from start till end. Now, first pass is over. Okay, in the first pass, you compared every adjacent element and you came up with this. Now, let us move on to the next pass. So, this is my first pass. This is it. Move to the next pass. Here, as usual, you will start with, in the second pass, which two elements will compare? Again, you will do the comparison between two elements, right? So you'll compare 13 with, again you will start. 13 will be compared with 26. So it is small, so you need not do any swaps. So it will be 13, 26, 32, 10 and 35. Okay, so what is the next comparison then? You will compare 26 with 32. It is also 26 is smaller, so you need not do any swaps. So it will again follow 13, 26, 32, 10, 35. Okay, got it. So what next? 32 will be compared with 10. Why don't we compare right to left? That would be more optimal. Let us follow the same strategy. I mean, now you know the input. That's why you are telling right to left. In reality, you will not know how the input will be. But you can do either way. So it is the same comparison. 13, 26, 32. When you compare 32 with 10, 10 is smaller. So 10 and 32 get swapped. Then you get 35. And next you will compare 32 with 35. There will not be any change. So I'm not writing it again. So the second pass gets over. Okay, now we will move on to the third pass. Now here you have 13, 26. It depends on the n size, right? Based on that, it will change. Yes, n minus 1 pass. But you can at any point, if you are not doing any swaps, which means your array is already sorted. So that is the end point. How do you determine the number of iterations? Usually it is in the order of n square. If there are 5 elements, right, you will do 5 passes. And in every pass, you will compare the adjacent element. Okay. Okay, now you took and you'll compare 13 with 26. There is no change. So first thing will be as such 10, 35. Okay. Okay, so the maximum element gets pushed. In the first iteration, you found 35. And in the next iteration, you found 32, the next maximum element, and you have stopped here. Okay, got it. So likewise, it will sort it. If you see, the next pass 26 will come here. Okay, guys. Likewise, it will identify the correct position of the maximum element. Okay. So now 13 and 26 is compared. What are the next two elements which you will compare? 26 and 10. When you compare, they are not ordered. So 13, 10, 26, 32 and 35. So you know that in the last iteration, 35 last position is the correct elements, the maximum elements position you got fixed. Now second but is fixed. So which means you need not go and compare 26 and 32, but you can stop it. Okay. We'll go to the next step. Okay, now you will compare 13 and 10 and you will swap it. So what's the result? 10, 13, 26, 32, 35. Okay, now in the next pass, you need not do because you have already done everything. In the next pass, if you do also, there will not be any comparison checks, which means you have already sorted the entire list. So what is the size of the array? 5. And how many checks we will do? 4. Got it? So this is the algorithm for bubble sort, okay? You will start from 0 and you will do 4 passes. I told you, right? If there are 5 elements, you will do only 4 passes. 5 elements means from 0 to 4th position. You need not do the 4th iteration at all. You can reduce it to 3rd position itself. Okay, so you will do this less than n minus 1 passes. So this check says the last element is already sorted, so you need not check. Or the last but second element got sorted. So this one will help you to pause till where you can do the comparison. And you will check whether the j is greater than j plus 1. If so, you will swap. Otherwise, you will do nothing. Okay, if there is any iteration, sometimes you get a sorted array itself. At that time, this algorithm should not keep running again and again, right? So in those cases, we will set a flag swapped is equal to false. If there is no swapping happening, which means the elements are sorted already, then you can come out of this this entire loop. Okay. Okay, guys, let's move on to next one. The heading as selection sort. Okay, what did you do in bubble sort? You have identified the maximum element and you have pushed it to the end of the array or end of the pass. Correct? Here in selection sort, you will identify the minimum element and you will push it into the front position or accordingly. Okay, so let us see how we are going to do it. So first thing what you will do is you will compare 12 with 29. 12 is less than 29, so you need not do anything. 12, 29, 25, 8, 32, 17 and 14 will come as such. Okay, now initially you will always think the first element as the minimum element. Okay, so you have assumed 12 as the minimum element and you are comparing 12 with every other element in the array. Okay. So now 12 and 29 comparison is over. What will you do? You will compare 12 and 25. When I compare, they are same. So I need not do anything. I'll put it as such. Okay. Now the next iteration comes. You will compare 12 and 8. So 12 and 8 when you compare, 8 is smaller than 12. So you have to swap it. Okay, got it? What you're swapping, you have identified a minimum, which is actually not a minimum element. So you are swapping it. Now my minimum becomes 8 instead of 12. So what is my new minimum? 8. Now 8 you have compared with 12 and you have swapped. Now you will compare 8 with 32. When you compare 8 with 32, 8 is smaller. So 8, 29, 25, 12, 32, 17 and 40. Correct. So in the next iteration, what will you do? You will compare the next minimum with the next element 17. Okay. So when you compare 8 is smaller, so you will paste it as such. And again, now in the next iteration, what will you compare? The identified minimum 8 with 40. And you find 8 is still smaller. So you have done the swapping. Now you have identified the global minimum element. Okay. This is my first pass. Now shall we move on to the next pass? 8, 29, 25, 12, 32, 17, 40. Now 8 is the minimum element. So skip by 8. The next minimum is 29. So I will make 29 as my next minimum element. And then I will do the comparison. So how will I compare? I'll compare 29 with 25. When I compared, what did I identify? 29 is greater than 25. So I have to swap 25 and 29. So I did. You swapped to 25 and 29. Now what is my global minimum? 25. Now you will compare this 25 with next element 12. When you compare, what happens? Tell me what is the result, guys? 8, 25, 29. You have to do a swapping. So 12 comes here, 29, 25, 32, 17 and 40. And what will happen in the next iteration? Now what is your global minimum? It is 12. 12 you have to compare with next element 32. Now what is the result, guys? Now the next comparison is between 12 and 17. Now what will you do in the next iteration is? So 12 you will compare with 40. So 8, 12, 29, 25, 32, 17 and 40. Okay, so now end of this pass, you have compared all the elements, right? Okay, now let us go to the third pass. The third pass, what will happen? You found the global minimum for first two iterations. Now, what is the minimum element for this iteration? Yes, you will start with 29, the next element. Okay. So the next element is identified as minimum element. You will compare with the remaining element. So what happens here? Swap. Awesome. 12, 25, 29, 32, 17 and 40. Okay, next what happens? Comparison between the third position and the... So when you do here, there are no changes. So I'll leave it as such. Okay. Now when I'm comparing 25 and 17, what happens? You will have to do a swap. Okay. Only swapping positions we will do, guys. Others you see the arrow. What is the next comparison between 17 and 40? When you compare, 17 is less than 40, so there is no swap. Now, top three elements are ordered. Okay, in the next pass, what is the minimum element? Minus 20. And you will compare 29 with 32. There is no change. So you will move on to 29 with 25. Swap is required. 17. When you swap, 25 comes here and 29 goes here. Okay, now what is my minimum? 25. Okay. 25 you will compare with 40. It is less, so I'm not worried much. End of the iteration. Okay, now let us do the next one. Now, first four elements are already sorted, right? And now we'll go to the next element. Oh, 32 is my minimum element. So 32 I'll compare with 29. So I have to do a swap. So I'll do a swap. 29 will come here and 32 will go there. And what is my minimum now? Instead of 32, 29 is my minimum. I'll compare 29 with 40. Okay, it is, you need not do any swap, so I will leave it as such. This is end of this iteration. Now, in the next iteration, 8, 12, 25, 29, 32, 40, right? What will I do? In this iteration, I'll pick the next minimum. What is the next minimum? 32. You will compare 32 with 40. Is this sorted? Yes. So you will leave it. Will you move on to the next iteration? No, it is not required. Last element will always be sorted. See, find the minimum element, swap it with first element of unsorted part, and move the boundary and repeat the steps until the entire list gets sorted. Okay. So you know you will do n minus 1 passes because the moment you reach the last element, it is already sorted. You don't have anything to compare. Okay, so less than n minus 1 you will do. This is the number of total count of passes, and in every pass you will compare the adjacent element, which is I plus 1th element. Okay, and you will compare it with and you will assign the minimum index to this position if there is a value which is lesser than this global minimum, you will do a swapping. Okay, so here what will you do? As usual, you'll compare first two elements. 12 and 31 are already sorted, so you will not do anything. Now 12, you have already thought 12 is already compared, so you will highlight 12 like this. Okay, and then what you will do, you will compare 31 with 25. So 31 you will compare it with 25. Okay. And what will happen? 25 is less than 31. So you will swap 25 and 31. Okay. After you have swapped, now 25 and see, now listen carefully, guys. So this is an important thing in insertion sort. You can compare 25 with 31, correct? And 25 is less than 31, so you have swapped. So the moment you have done a swap, you should always compare with all of its previous elements. And if at all you have, again you have to run a comparison and reorder. Now here there is only one element called 25. So you will compare, and here 12 is less than 25. So it is totally fine. I can keep it as such. Okay. So this is fine. Now here this is my sorted item as usual. 25 and 31 is done. So 25 is also done because you have done a swap. So 25 is also colored. The moment you do a swap, which means that these two elements are the previous elements and you are running the index after that. Okay, so you will compare 31 with 8. So the moment you encounter that a swapping is necessary, you will have to compare with all the previous elements and then reorder the position. Now you have got 8 and 31. Now it is done. Now 8 has to compare with all of its previous elements and swap. So when you compare in the first iteration, what happens? 12, 8 and 25 will get swapped. Then 31, 32, 70. Okay, now this swapping is done. Next, you have to compare 8 with 12. Okay, you did the comparison and then 8 is smaller, so you do a swap. And now 8, 10, 25, 31, 32 and 17 are the elements. Okay, now 3 passes are over. So I'll highlight the colored ones. Okay. 8 is done, 12 is done, and now the third position also we have compared, so I'll highlight all that the positions are colored. Okay, now let us move to the next one. So when you swap, what will you do? 31 you will compare with 32. There is no swapping. So you will leave it as such. 8, 12, 25, 31. 31 and 32 are compared. Swapping is not required. So you will leave it as such. Okay. Now what will you do? Next, 31's thing is also done, which means the fourth pass is also completed. So I'll color that. Now what is the next iteration between 32 and 70? So when you compare what happened, you found that they must be swapped. Correct? So you will swap 17 and 32. The moment you swap, what you have to do, you will have to compare the 17 with every element before that, compared with all the previous elements. Not only with previous element, you have to compare all the way to the top. So in the first iteration, what happens? 8 and 17 is compared. If there is no change, I will leave it. But 17 and 31 when gets compared, 8, 12, 25, 31, 32 and 17 are compared. So it becomes 17 and 32. Once the swap is done, 17 has to be compared with all of the previous elements. Right? We will do it one after another now. So what will happen? When you compare, first we'll do 17 with 31. So you will change it 8, 12, 25, 17, 31, 32. Okay. So in the next iteration, you have to compare 17 with 25. So when you do, 17 comes here, 25 comes after that, then 31, then 32. Okay, now what you have to do? 17 you have to compare with the previous element 12. There is no change. You have to compare with 8. There is no change. So we will leave it. Okay, so now so far how many iterations are done? 8 is done, 12 is done, third position is done, fourth position is done, and fifth is also done. Which means sixth is also done. So now you got a sorted array. Clear, guys? So what will be the condition to check the element with previous element? So the moment there is a swapping between adjacent elements, then you have to check with all of the previous elements. Okay, so that's the condition. The moment any swapping happens, you have to compare with all of the previous elements. See, now let us take this iteration, okay? So in this iteration, I've compared 31 and 8. So I've swapped 8 and 31. So the moment a swapping happens, I have to compare with all of its previous indexes. Okay, got it? Okay, we'll go to the code section, coding part now. So insertion sort, right? Start with the second element, compare with the previous element. If the previous element is greater, then shift it, swap it. So repeat the comparison until, so it's the same thing. So let us go to the algorithm. You will do the iterations from until n. At every iteration, what will you do? You will compare whether the previous element is j greater than 0. An array of j is greater than key means that particular element, and you will do a swap. So this will happen only when you do a swap. Okay, then we'll go to the next sorting algorithm. Okay, so the next sorting algorithm which we are going to see is about the merge sort. Okay, it is similarly like merge means you will divide the given array into subdivisions, and each subdivision you will again divide until you do a sorting of individual elements, and then you will merge it. Okay, that is why it is called merge sort. So now here you got this entire list. Now, what is the middle? It starts from 0, 1, 2, 3, 4, 5, 6, 7. So 0 plus 7 by 2 is 3, right? So I'm dividing this entire array into two subarrays here. So this part becomes one subarray and this part becomes another subarray. Okay. So 12, 31, 25 and 8 is my one subarray, and my another subarray starts from 32, 17. So every half you will divide until you have one element. Now again, let us divide this subarray. So it is 0 left plus right by 2, 3 by 2, which is 1. So you divide it into half, 12 and 31 will fall into one subarray, and 25 and 28 will fall into another subarray. Okay, so 12 and 31 here. Okay, in another array, you will have 25 and 8. Okay, here in another array, you will have 32 and 17. And what will the other array have, guys? 40 and 42. Good. Okay, now again you will divide this into half. Okay, let us divide this into half. What will you get? You will get 12 here and 31 here. And you will get 25 and you will get 8. You will get 32 and you will get 17. You will get 40 and you will get 42. Okay, now these are independent elements. Okay, now once you get the independent elements, compare the first element in the array with the first element of the next array. And whichever is smaller, you will put it in the resulting array. Now you got two arrays as input. Okay, so now what will you do? 12 will be compared with 31. 12 is smaller, so you will put 12. Okay, now you are merging these two. So till now, okay, till here you are dividing. Okay, now after dividing, you have to conquer. Now what you do, you have two input arrays and now you are merging. Now the process of merging comes. Okay, now what you will do is, you will compare the first element in the first array, which is 12, with first element in the another array, 31. 12 is less than 31. So to the result array, you will put 12 first. And then, because you don't have any other elements in the first array, you cannot compare first array with second array again. So you will see whatever is the remaining element in the second array, you can put it as such. Now you have merged and 12 and 31 came. Okay, so this is your first subproblem. Now let us go to the second subproblem. So now first merging has happened. Now let us go here and check what is the second merging. Okay, so now guys, what will happen in 25 and 8? 25 is one array and 8 is one array. And now we are doing the process of merging. So what will happen? You will compare 25 with 8. 8 is smaller, so you will put 8 in the result array. And then you have, you cannot compare 25 with the next element, because in the second array, it became empty because the element 8 you have pulled it here. So whatever are the remaining elements in the first array, you can put it as such. So 8 and 25 you got. Okay, now go to the third one. Tell me guys, what is the third subarray's answer? 17 and 32. Clear? Okay, now 40 and 42. What will be the resulting subarray? You have two arrays, 40 one array, 42 is another array. When you merge, 40 and 42. So in merging, what all you do is, you will compare first element of in first array with first element in second array. Okay, you will compare which one is smaller, you will put it in the resulting array. Okay, so and then you will put in the resulting array. Likewise, you will do collect result array and repeat until elements are left in both the arrays. Okay. Okay, the once one of the array becomes empty, what will you do? One of the array becomes empty, the next array's elements will be added to the resulting list as such. Okay, so now you got 12, 31, 8, 25, 17, 32 as an array, 40, 42 as an array. So now take these two and form a resulting array. So what will you do? You will take the first element of the first array and you will compare with the first element in the second array. Correct. So you are doing a comparison between 12 and 18. So once you do, let us do the resulting array. In resulting array, you will have 8. Correct? Because 8 is lower, so you will have 8. Next, what will happen? Now you will increment the position of the second array because you have pulled an element from the second array. So you'll increment the position of second array and you will compare with the first element in the first array. So now what is the next element, guys? When you compare 25 and 12, what will you put? 12. So now you put 8 and then 12. Now what will you do? Still array, there are elements and you will increment the position of first array. Okay, now the position of first array is 31. Okay, now the position of first array, you have 31 and you have 25 in the second array. You will compare 25 and 31. And what will you do? You will put 25 into the list because 25 is smaller. And now if you see 31, you don't have any other element in the second array to compare. Do you have? No. So what will you do? The remaining elements, you will add it to the array. So what is remaining? 31 is the only element remaining. So you will add it to the array. Okay. Now let us come to the other two arrays. 1732 is my first array and 4042 is my second array. Okay. In this case, what will you do? Which two elements will you compare? 17 will be compared with 40. So 17 is smaller. So 17, I'll put it in the resulting array. If I put 17, I have to increment the pointer in the first array because 17 is gone. It is no more there. So what will you do? 32 you will compare with 40. When you compare 32 with 40, what will happen? 32 is smaller. So you will 32 here. Once you put 32, you will take 40. Okay, once you put 32, now you have a second array as a whole. But do you have any first array? What can we do now? You can just put the second array as such because you know it is already sorted. So I got 40 and 42. Now I have two arrays, which is this is my first array and this is my second array. Now let us run a merge sort on this one. 8 will be compared with 17. So what will come in the resulting array? 8. And you will compare 12 with 17. What will be the result? 12 with 17? 12. Next, you will compare 25 with 17. What will be the 17 will come? Okay. And after that, what comparison you will do? 25 with 32. So what will come in the resulting array? 25. Awesome. And now, next, what will you do? 31 with 32. Which one will come into the resulting array? 31. Okay. Now, can we compare 32 against any element? The first array is empty. So what will you do now? I don't have anything to compare. I know that my second array is already sorted, so I can add the remaining elements as such. So 32, 40, 42. Guys, did you understand merge sort? Because you're doing a dividing and conquering and you're doing it for n times, it is all the complexity is order of n log n. Okay, what is the complexity of this, guys? Order of n log n. Okay, so the same is explained over here. First you will divide. So everywhere you are finding the middle element and you are dividing it. Okay, every array you are subdividing into multiple small arrays. And finally, you are running a merge. So when you run a merge, what will you do? You will compare the first element in the left array with the right array. And if left array's element is smaller, you will put that into the result array. Otherwise, you will put the right array's element in the result array. Okay, once any of the array becomes empty, then this while loop will not execute. In that case, you have to identify if first array is not empty, then copy all the remaining elements there. Otherwise, copy the second array's elements. Okay, got it, guys? So that's the same code. Okay.
Just a quick info, guys. Intellipaat offers a full stack web developer course in collaboration with iHub IIT Roorkee. Through this course, you'll learn tech stack like MongoDB, Express.js, Angular, Node.js, along with HTML, CSS, JavaScript, and more from the IIT faculty. With this course, we've already helped thousands of professionals transition into high-paying developer roles. You can check out the success stories on our Achievers channel, whose link is given in the description below. No doubt this course can take your career to new heights. So check out the course page link in the description and take the first step towards becoming a certified full stack web developer.